So now let's start data structures and algorithms. So in DSA, I am going to teach you different kind of concepts here. Your big O notations, okay, your sorting algorithms, time complexity, space complexity. I am going to teach you all of those concepts here. Okay, but before all of that, we need a code editor so that we can run some programs as well in order to understand these concepts. Okay, so that is the first thing we are going to do here, is that we are going to select a code editor that we are going to use. Now you can use any code editor, but what I am going to do here, I am going to use Google Chrome developer tools. Okay, as you can see on the screen here, I have opened Google Chrome browser. I have downloaded and installed Google Chrome browser in my computer. Okay, and I am going to use the developer tools of this Google Chrome for running my JavaScript programs so that I can help you understand these DSA concepts easily. Okay, so that is the first thing we are going to do here. We are going to see that how can you use this Google Chrome developer tools here. Okay, so for that, first of all, you have to install Chrome browser in your computer. So please do that if you do not have Chrome browser installed. Then after your Chrome browser installed here, you can open it like this. And then what you can do, you can go to these three dots. Go to these three dots, okay, on the top right corner, and come to this option, more tools. Come to this more tools, and here you will find this one, developer tools. Okay, so click on this developer tools. So this side panel will open in front of you. Okay, so this is your developer tools of Google Chrome. Now first of all, what I am going to do here, I am going to make this side panel as a separate window. Okay, because all the programs we are going to write here, all the concepts that we are going to understand, we will use this Google Chrome developer tools. Okay, you can use any code editor, but I am going to use this one. And if you want to follow me as closely as possible, then try to do the same as well. Okay, so first of all, this is my Google Chrome developer tools as a side panel, but I want this side panel as a separate window. So what you can do, click on these three dots. See these three dots, this one, click on these three dots, and here you will find all of these options here, side panel, like this one. Now you will find this one, unlock into separate window. See this option, unlock into separate window. So click on this one. So this separate window will create in front of you. See this one, a separate window will be created for you. Okay, and you can maximize this one. Okay, so this is the Google Chrome developer tools in a separate window. Now what you can do, first of all, I am going to change the theme of my this developer tools window here. So what you can do, you can click on this one. You can click on this one, this settings, click on this one, settings, and then click on this one, theme, system preferences. Click on this theme here and select the dark one. So I will select the dark one here, and it will change my entire developer tools into dark one. If you want to follow me as closely as possible, then please do the same as well. Okay, then click on this smaller cross here. So this will be gone, settings, and now we are here. Now after changing the theme of your developer tools, now what you can do is that you can come to this tab. See this one, sources. Come to this tab here, sources. Okay, and when you will come to this tab, sources here, then you can click on this one, workspace. Click on this workspace here, and you will come to this place. Now here what you can do, you can click on this arrow. Okay, and click on this one, snippets. Click on the snippets here, and see it will change to snippets. Okay, now when it will change to snippets, so here you can create your new snippets, and in those snippets you can write your JavaScript programs. You can run those JavaScript programs here. Okay, so I am basically using this as a code editor for running my JavaScript programs so that I can help you understand the DSA concepts. Okay, for example, here you can create new snippet, and see a new snippet will create for you, and here you can write whatever you want to write here. Let's say DSA1. So I will write something like DSA1. I will press enter. So by the name of DSA1, a new snippet has been created. Now what you can do, here you can write a simple JavaScript code. So whatever you want to write, let's say console.log, and here I will write here, let's learn DSA. Okay, something like this. So whatever you want to write here, you can write here, and you can press Control plus as well if you want a little bit of zoom in here. Okay, that is something you can do as well. And then After writing your JavaScript code here, what you can do, you can click on this one. See, you can click on this play button, or you can press Ctrl plus enter. Okay, so click on this button. So what it will do, see, it will run the program for you. Okay, so that is something you can do here. That is how we are going to use this developer tools for running our JavaScript code here. Okay, so this is the place where we will write our code, and we will try to understand the DSA concepts. Okay, if you want to create a new snippet, you can click on this one plus again, and see, another snippet will be created for you, DSA2 or something like this. Again, one more DSA3. So no matter how many snippet you want to create here, you can create in this place here. You can remove them as well. Right click and you can remove as well. Okay, so that is something you can do here. That is how you can use your Google Chrome developer tools as your code editor. Okay, so this is what I am going to use here. If you want to use any other code editor, then you can use them as well. But if you want to follow me as closely as possible in order to understand everything, then you can use this Google Chrome developer tools as your code editor. Okay, so first of all, let's start with BigO here. So it is essential that you understand BigO when you are going into some technical interview, because it absolutely comes up. Understanding this will also make you a better coder. Okay, so what is it? So think of it like this. We have two sets of code. We have code 1 and we have code 2. How do we determine which one is better? Okay, now both of these are going to accomplish the same thing, but they have written differently. Is code 1 better? Maybe it is easier to read, or is code 2 better? Maybe there are other things about that make code 2 better. Okay, well, BigO is a way to mathematically figure out which of these two is better. Okay, which one runs more efficiently. Okay, so obviously we can't measure this with a scale, so I'm going to bring in a stopwatch to make the point. Okay, let's say we run code 1, and when we run it, we start a stopwatch and it runs for 15 seconds. Okay, then we reset the stopwatch and we run code 2, and code 2 runs a lot longer than 15 seconds. Well, obviously we want our code to run as quickly as possible, be as efficient as possible. So by this measure, code 1 is the better code, right? This is what is called time complexity. Okay, but we don't measure time complexity in time. We measure it in the number of operations. And the reason we do that is, if you look that same code and we ran it on a faster computer, obviously it would complete in less time, but the number of operations would be the same, right? So either way, on the fast computer or the slow computer, the time complexity would be the same. Okay, the number of operations would be the same. Also, with BigO, we measure what is called space complexity. Okay, space complexity is the amount of memory that something uses. So let's say code 1, while it's very fast and runs in 15 seconds, are comparatively fast, maybe it uses a lot of memory. Okay, and then we reset all of this and we look at code 2, while that runs a really long time, the full minute, maybe it uses less memory. Okay, and if this is what's most important to you, maybe code 2 is better. Okay, we are going to look mostly at time complexity, but space complexity will also come up in interviews. Okay, they will ask you, okay, you wrote this code in such a way, maybe during a whiteboard session, okay, or something like that, and they say that you have optimized for time complexity, but what if we care about space complexity? How would you write it? Then you will have to understand both concepts. Okay, but what we will focus on mostly in this section, DSA section, will be time complexity. Okay, so when you are dealing with this kind of notations, there are 3 Greek letters that you will consistently see. They are omega, theta, and omicron. Omicron is better known as O, or as in BigO. Okay, and BigO is the one, of course, that you are going to see most often. Okay, so to explain this, I am just going to bring up an array. Let's say we are going to build a for loop to iterate through this array until we find a particular element. If we are looking for the number 1, this is our best case with the least number of iterations. Okay, through the array, right? This would be our worst case, and for would be our average case, this would be average case. The best case, okay, so this best case is represented with Greek letter omega. Okay, the average case is represented with Greek letter theta, and our worst case is represented with omicron, or you can say big O. So big O is always going to be the worst case. Okay, and I want to point this out because it is very common for people to say things like okay, that's our worst case big O, what's your best case or average case? Okay, well, technically there is no best case or average case big O. That would be omega or theta. Okay, so when we measure big O, we are always measuring worst case. Okay, so now we are going to look at our first big O notation, and I start with O of n, not because it is most efficient or least efficient, but because I think it is the one that's easiest to get your head around. So I'm going to explain this with a function. Okay, so and I'm going to call this function log items, and we are just going to console log out some items. Okay, so we are going to run a for loop, and the for loop is going to run n times, and there we are going to console.log out from the for loop. Okay, and that's it. Pretty simple code. So let's go look at this in Chrome Dev Tools. Okay, so there is our function. We are calling it with the number 10. Okay, and let's run this. Okay, so and you can see that we have console logged out 0 through 9. Okay, so let's go back over to our other section. So this is on operation, O of n operation. Okay, so to put it in another way, we pass the function the number n, and this ran n number of times. Okay, so we pass it a 10, and it ran 10 times at output 10. It thinks that's what O of n is. Okay, so let's take a look at this on a graph. O of n is always going to be a straight line. It is proportional. The number of operation is going to be proportional to wherever n is. Okay, so on this graph, this axis represents n, this axis represents the number of operations. Okay, so that is our first big O notation, and we'll be adding to this graph with the other big O notation, so we can compare one against another. But for now, that is O of n. Big O has several ways in which we simplify the notation, and it makes things easier. The first thing that we are going to look at is called drop constant, and you will see it referred to as remove constant. You will see it both ways. Okay, so to explain this, I am going to start by bringing up the code that we had in the O of n. Okay, but I am going to add a second for loop that's identical to the one above, except that we are going to use j instead of I, and both of these for loops are going to run n times. Okay, so let's take a look at this in dev tool. Okay, that's our code, and we are going to call this with the number 3 now. So let's run this. So, and our output is 0 1 2 from the first for loop, and then once again 0 1 2 from the second for loop, right? So let's go back to over here. So our code ran n plus n times, right? That means 2n. Okay, so it makes sense to say that this is O of 2n operations, but this is where that simplification comes in. It doesn't matter if it's 2n, 3n or 100n, if that's a constant. Okay, 2 is a constant. We drop the constant and we say that this code is O of n. So our first rule for simplifying our big O notation is drop constant. Now we are going to look at our next big O notation, which is O of n square. So we are going to start this off with the code that we used in last section where we had a for loop. Okay, following by another for loop. So but I am going to change this, and we are going to remove this console.log, and we are going to nest one for loop inside of the other. Then our console.log is going to be I comma j inside of the 2 for loop. So let's get over to our dev tools, and That's our code. We are going to call this with the number 10. Okay, and if you run this one, so, and if we scroll up to the top, we start with 0 0. Then we go, if we scroll down to the bottom, we go to 9 9, right? So we have output 100 times. We have output 100 times. So let's go back over here. The number of items that were output in this case is n times n. Okay, that is n square. Okay, and that's where we get our O of n square. Now let's take our code and add one more thing to it because we want to simplify this notation. Okay, so let's take our for loop one layer deeper. Then we will console.log for that for variable ijk. And let's take a look at this in DevTools. That's our 3 for loops. Okay, once again we are going to call it with the number 10. And we will run this. So we end in 999 at the bottom, and if we scroll up to the top we have 0 0 0. So we had 1,000 things that were output in this case. Let's go back over here. So we had n times n times n operations, all 10 times 10 times 10 since we passed it the number n10. So this is n cubed, which would be O of n cubed. But it doesn't matter if it is n to the power 3, n to the power 4, n to the power 10th. We are still going to write this as O of n square. We are going to simplify this. Okay, so let's take a look at this on a graph. So if we had two sets of code that accomplished the same task, and one was O of n square and the other is O of n, the O of n code is better because it is going to complete the task in fewer operations. Okay, so this is our first opportunity to see how it is that we could compare one code set against another. So an O of n square is generally considered an efficient code. If you can write your code in a way that is going to become O of n, it is going to be much more efficient. Okay, so that is of n squared. Now a drop non-dominance is another way that we simplify big O notations. Okay, so to explain this, bring up some code here. Okay, this is our nested for loop that we saw in the before example. What I am going to do, add to this is an additional for loop that comes after the nested for loop. Let's take a look at this in DevTool. So there's our code, and we are going to run this with the number 10. I am going to scroll up to the top to begin with. So we have output here 0 0, and this goes through to 9 9. This is our nested for loop. That second for loop that follows, it goes from 0 to 9. Okay, so let's take a look at this over here. That nested for loop ran O of n square times. Okay, the second one ran O of n times. When we add these together, this becomes O of n square plus n. So if you think about this in terms of n was 100, in n squared would be 10,000, where the single and that added to it in the equation is only 100 more operations. It's not really affecting the number of operations, right? So n square is the dominant term and n by itself is the non-dominant term because it is not affecting that much. So you can remove it. So drop non-dominance. Now our next big O notation is O of 1. So let's start out with some code. Here we have a function called add items, and all we are going to do is we are going to return n plus n. There is only one operation here, and that's the addition. So it doesn't matter if n is 1 or n is a million. The number of operation is going to be 1. Okay, and that is O of n. Well, what if we add another addition? Well, now that is 2 operations O of 2. And as you may have guessed, we are going to simplify this and make it O of 1. So O of 1 a lot of times is referred to as constant time. Okay, so this situation here where we have two additions, it's two operations that is constant. No matter what n is, the number of operations does not change as n changes. Okay, so let's take a look at this on the graph. Okay, just a flat line across the bottom. It is the most efficient big O. Nothing is more efficient than O of 1. Okay, remember you will also hear this referred to as constant time. So if you hear that phrase, that is O of 1. Okay, so the last big O that we are going to look at is O of log n. So I am going to explain this with a sorted array. Okay, and in order to do what I'm about to do here, you have to have sorted data. Okay, let's say you want to find a number in this array, and we are going to look for the number 1. What would be the most efficient way to find that? What we are going to do here is we are going to take the array, we are going to cut it in half and say, is the number 1 in the first half or the second half? Well, it's not in the second half, so we don't even have to look at any of those numbers. And that may not seem like a big deal when you have an array with 8 items in it. But if you have an array with 1,000,000 items in it, you just made it where you have 500,000 items that you don't have to look at. So then we do this again. We cut this in half. It's not in the second half. We are going to remove that, and then we do it again. And now we have found the number 1. Okay. So this is a technique called divide and conquer. Okay. So let's bring everything back here and count the number of steps that we went through to find that. Okay. To find that item. It was 1, 2, 2 here and 3. Okay. And remember, we have 8 items in the array. And 2 of the power third is 8, right? So I am going to turn this into a logarithmic, and if you are not a mathematic person, don't worry, we are not going to go in deep into this, but look at the 3 numbers we have here, the 2, the 3 and the 8. So log sub 2 of 8 is equals to 3. And we back this up, we get this. And we will look at this again. So log sub 2, 8 equals 3. We are basically saying 2 to the what power is equals 8. 2 to the what power equals 8. Okay, that is basically what we are talking about. Well, that number is 3. 2 to the power 3 is 8. To put it in another way, if we take the number 8 and we repeatedly cut it in half and we divide it by 2, how many times do we have to divide it by 2 to get down to 1 item, and that is 3. 3 times. We have to do it 3 times. And the real power of this is when we get to a very large number, let's say we have log sub 2 of this number and this is over 1 billion. How many times would you have to cut this number in half to get down to 1 item? Okay, and that would be 31. 31 times. To put it another way, 2 to the 31st power equals this number here. That's over 1 billion. So if you have an array with 1 billion items in it and you are going to iterate through that array linearly to find something and say what you were looking for was the last item, you would have to look at 1 billion items to find it, right? But if you use divide and conquer, you could find any item in that array in 31 steps. Okay. So, and that is the power of log n, O of log n. Okay, so now let's look at this as a graph. You see that this is a very flat, not as flat as O of n, of course, but very flat, very efficient compared to O of n and O of n square. At this point, I want to show one other thing on the graph. I'm not going to talk about this in a lot of detail, but I just want to show this, and that is O of n times log n. That is used in some sorting algorithms, and this is the most efficient that you can make a sorting algorithm unless you are sorting only numbers. Okay, but if you are going to sort multiple types of data, you are going to sort strings. Okay, this is as efficient as you can make a sorting algorithm. We will talk about this and how we can come up with n times log n when we get to those sorting algorithms, but it will make more sense then. So that's why I'm not going to talk about it now. I'm going to take this back out. So for the rest of the section, everything that we look at is going to be one of these four. Okay, so that is O of log n. Now let's talk about different terms for inputs. So different terms for input is a very popular technical interview question. Okay, and to explain it, I am going to bring up some code that we have seen here. What we have, a for loop followed by another for loop. Okay, and if you will recall, each of these ran n times, right? And it was O of 2n, and we dropped the constant and it became O of n. So the trick interview question is that instead of passing this n, we are going to pass it two variables. We are going to pass it two variables here like this, and the for loop runs. First one is going to run 8 times, and the second term is going to run b times, a times or b times. Now here is the kind of now there is, you don't know about something, this is one, that this one is for loop for us, and a single for loop is of O of n, and we are going to add these two together and drop the constant, and this becomes O of n. But that is not correct, because you can't say that A is equal to n and B is equal to n. Okay, you cannot say you can't have both variables be equal to n. Okay, and what if A is 1 and B is a million? Okay, those are very different for loops. So what you have to do is say the first for loop O of A, or whatever the variable might be, and the second one is O of B. Okay, and when you add these two, you will get O of A plus B, as far as you can simplify this. Okay, similarly, if these were nested for loops, this would become O of A times B. Okay, you can't use n, you actually have to use different terms for input. That is the main point I want to tell you. Okay, now we are going to talk about the big O of arrays. It's important to understand this so we can compare arrays to the other data structures that we are going to build. So I am going to start with an array, but I am going to present it like this. Okay, so we have the indexes there, because this will be important for explaining the big O of arrays. So we are going to start with an array that we have already created, that we call my array. And then we are going to push an item to the end. So my array dot push is going to push this number 17 on to the end with that index of 4. Okay. The important thing here though is that we do not have to re-index this or this or this all of the way down to the beginning. You do not have to do that. Likewise, when we remove this item with a pop and we pop that off, okay, we don't have to re-index anything, and because of that, push and pop are both of one operation, or you can say O of one operation, but it's different on the other end of the array. So let's bring up my array dot, and we are going to shift that first item of the array. When we remove this, the problem we have is that this index is incorrect. First item is in the array should be 0. So this has to be re-indexed to 0. And the next item has to be re-indexed to and to the next item, like that. Likewise, if we do not and unshift and we bring that 11 back, we have to re-index everything in the array all the way down just to be able to bring this back. Okay. Not a big deal when we have a small array like this, but if we had one that had thousands of items, that is a lot of re-indexing. So this is O of n, where n is the number of items in the array. Okay. Very important with arrays to understand that on this end, it is O of adding or removing are both O of 1. On the other end, removing or adding anything because of the re-indexing, okay, and bringing it back because of the re-indexing are both O of n. Okay. Now let's look at adding something into the middle of this array. So we will say my array dot splice, and if you haven't seen this before, what we are saying this is that we are going to put something in at the index of 1. This means we are not going to remove any items, and this means we are going to add an item with a string that says hi. So let's open up that index of 1, drop that new item with the starting string in there at the index of 1. And when we do that, this index is incorrect. It will, when we have to reindex this and this and this and this all the way down, since we have to reindex all of this. Okay, this is O of n, and you might say we are putting that in the middle. Wouldn't that be O of half n? See, there is two problems with that logic. First is that big O always measures worst case, not average case. The other problem is this: even if this was a 1/2 of n operation, 1/2 is a constant. 1/2 is still a constant. Okay, so you have to drop it, and we drop constants. So either way, this is O of n. So likewise, when we go to remove this item, we are going to have to reindex everything all the way. Okay, all the way down. So it doesn't matter if you are adding or removing somewhere in the middle of the array. That's going to be O of n. Now let's look at finding an item. Let's say we are going to find the number 7 in this array. To do that, we have to start at the beginning and say, is that 7? No, no, no. And then we finally get to 7. It's yes. That means that if you search by value, this is O of n. But if you search by index, you say, tell me what's at the index of 3. Those indexes allow you to go directly to that place in memory as O of 1 operation. Okay, this is one of the big advantages of array, is that we can find something in an array with a million items in it, and go to item 400,000 say, and it is an O of 1. Still it is O of 1. But those indexes are also a disadvantage for those arrays if you are adding something at the beginning, as we just saw, because you are going to have to reindex everything. So the big thing that you have to look at when you are looking at a data structure is that what you are using this for. If you need to access things by index, arrays are a great data structure by index. But if you are going to adding and removing a lot of items from the beginning, maybe not the best data structure for you, and maybe you should look at a different data structure if that is your use case. Okay, but either way, you are making your decision based on big O. Okay, so I just want to wrap up our section on big O by looking at how these time complexities compare to one another. So I'm going to bring up the graph, and let's say n is equal to 100. If n is equal to 100, what are all of these going to be equal to? Well, O of 1 is always going to be equal to 1. O of log n is going to be approximately 7 if n is 100. Okay, obviously n is gonna be equal to 100, and O1 square is going to be equal to 10,000. So you can already see a big disparity between these numbers. But let's say we increase n to 1000. O of 1 is still going to be 1 of O of log n is going to be approximately 10. So 2 to the 10th power is 1024, which is close to 1000. So log of n of 1000 is going to be approximately 10,000. O of n is going to be 1000, but O then square is going to be million. So you can see that 1 is going to grow very, very fastly. So there are different words and phrases that you will hear used with each of these. So O of n square is going to be loop within a loop. O of n, you will hear the word proportional. O of log n, you will hear the phrase divide and conquer. Okay, and O of 1, you will hear the phrase constant time. Okay, so these are our big 4 that we are going to look at in this course, in this section. So now I'm going to take us over to a website that is, I think, is great here. It is a big O cheat sheet. So at the top of the page you have this graph. These two we are not going to see in this course. In fact, O of n factorial is really something that can only happen if you are writing a bad code on purpose. Okay, so unlikely that you are going to see this, but you can see O of n squared is in the horrible category. See, O of n square horrible category. Remember, O of n times log n is going to be when we are using some certain sorting algorithms, and down here what we want to stay most of the time. So let's scroll down a little bit. Has these are tables. So these are common data structures. Okay, so we have time complexities here, and it's broken down into average. Notice these are all beginning with the Greek letter theta and worst, which begins with the Greek letter omicron or O or big O. And space complexities over here, notice they are all the same except for one of them, which we are not going to build in this section in this course, but everything O of n except for that one. So everything that we are going to build for data structures have identical space complexities. Space complexities are identical, and this is one of the reasons why we are going to spend more time on time complexities rather than space complexities, because for data structures space complexity is all same, but it's different when we scroll down here to the sorting algorithms. Okay, this one for the time complexity we have, which is best, which is omega, average, theta, worst, O, big O. The space complexities are also different. So you have something like selection sort that has had terrible time complexity but great space complexity, versus merge sort which has great time complexity but not as nearly as good as space complexity. So these time complexities down here only work if you are sorting numbers. If you are going to sort strings or different kind of data other than numbers, the best time complexity you can get for a sorting algorithm is O of n times log n. I will also include a link to this site. This is a great resource. You can go to this website here, bigocheatsheet.com. And with that wraps up our section on Bigo. So now we are going to look at classes. And if you are not familiar with these, a class, the analogy I like to use is this, like this cookie container. Okay, so and we are going to say class cookie. So when you create a class, you always capitalize the name of the class. So in this case, cookie. Okay, classes always have something that is called a constructor. This is what creates the new cookie, okay, if you will, from the class. So in this case, we are going to pass this a color, and that's what this is referencing, and then we are going to pass it to the particular cookie that we are creating. And we will talk more about this keyword that is being used here, but it's for this cookie that we are creating. Okay, and that right there is a valid class. It doesn't do much, but it is a valid class. Okay, so now that we have created, we can create new cookies. So this first part look like declaring any other variable, but we set it equal to a new cookie. There is a new keyword in here. So cookie 1 is the specific instance of cookie that we are creating. Okay, and we do that by using the new keyword that calls the constructor. Okay, and we are passing it a color green, and that is going to create a green cookie. Okay, so we would say that this cookie is green. This one right here, that is called cookie 1, that's where this keyword applies, because we can have multiple cookies that are created by this. That this keyword is going to refer to a specific one. Okay, specific one. So to expand on this, let's create another cookie. Okay, so we will say cookie 2 equal to new cookie, that is blue. So cookie 2 is a specific instance of cookie. This one is blue. Okay, that is this cookie. Okay, is blue. So now we have created a class which is like a cookie. Okay, and then we have created a green cookie and a blue cookie. Okay, let's drop the cookies out of here and expand this class. Okay, So far we have created a constructor, but now we are going to create get color and set color, and these are two broad categories of methods that you create. They are getters and setters. Okay, so let's bring our cookies back here and let's look at all of this code in DevTools. So there is our simple example and the creation of our two cookies. I am just going to run this and clear this and then zoom in it at the bottom here. So if we say cookie 1 dot get color, this is where that this keyword comes in. We are getting the color for this cookie, okay, for this particular cookie, and you can see that this is green, and we can do the same thing for cookie 2. So cookie 2 dot get color, and this one is blue here. Okay, let's clear this one, and then we are going to do set color for cookie 1, and we are going to change the color of cookie 1 to yellow, and we will clear this. Now we can get color again, and see, now you have yellow color. Now cookie 1 is yellow here. So this is how roughly you can use classes. Okay, so let's come back here, and we have changed cookie 1 to yellow. So how are we going to use this in this course? Let's say we are going to build a linked list. In fact, all of our data structures are going to use classes, and this is why I want to spend some time on this. So as we discussed, we are going to have a constructor. So we are going to pass this a value to create the first node in the linked list, and the curly braces, I'm just putting a dot 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 to show that there would be code here to do whatever in this case the constructor would need to do. But I am not going to build this out, just going to do a quick overview of this. So some sort of other methods that we could create for a linked list would be push, unshift, insert an item and add an item with a particular value, remove, pop, shift, and we will create all of these in the linked list section and a few more. But let's just go over what we could do with this. We could say let my linked list equal a new linked list. We will pass it a number 23, and now we have a node with 23. We can say my linked list dot push with the number 7 and unshift with the number 3. To do that, insert at the index of 1 the number 11. See, like this, and we could remove the item at the index of 1 and remove that 11, and we can pop an item, we can shift an item like that. So these are some of things that we can do by building out the linked list class, and we have all the ability to do all of these very specific things with these data structures by using classes. Okay, now let's talk about pointers. So pointers are important to understand because we are going to use them in, I think, all of the data structures that we are going to build in this course. If you are already understood pointers, you can go ahead and skip this section. To explain pointers, I am going to start by explaining something that does not use pointers. So I'm going to have a variable. We are going to let num1 equal to 5, and then we are going to have another variable where we will have num2 equal num1. So let's take a look at this in DevTools. So here's that code here, and I'm going to run this. And then I'm just going to clear off this undefined here and show that if we do num1 that equals 5, num2 also equal 5. Okay, but if we say that num1 equal 10, now when we look at the number 1, num1 is equal to 10, but num2 is still equal to 5. That's what happens when we are not using a pointer. Let's go back over here. Okay, so when we set num2 to be equal to num1, this isn't permanent. This is just making num2 equal to 5 at the time that we declare the variable. Okay, but if we later change num1, it doesn't change num2. That's what happens when you are not using a pointer. So let's compare this to when we are using a pointer. I am going to say let object 1 equal to this value. Okay, When you set a variable equal to an object, you are saying object 1 points to this object. It is a pointer. Okay, it is a pointer. And then when we say let object 2 equal to object 1, it might look as though what we are doing is we are saying, hey, let's say object 2 is equal to another object with the same value, but that is not the case here. But that is not what is happening here. Okay, when you set object 2 equal to object 1, you are literally saying make object 2 point to the exact same object in memory as object 1. Okay, so let's look at this in dev tool, and we will run this. And if we say object 1 that equals that object with the value of 11, same with object 2. Okay, but if we are to change object 1 dot value and make it equal to 22, now if you run obj1, you will get value 22. Obviously that is going to happen because we change it. But if you do the same for obj2, object 2, still see, even for object 2, both of them are showing the value of 22. Okay, so let's go back over here. Now we have changed this value to 22, and object 1 and object 2 are both pointing to that same object. Okay, that's why they both come up as 22. That's a big difference in how pointers work versus what we saw before when we just use variables. So now I'm going to bring up another object here because I want to help you understand something. When we say let object 3 equal to this object, we are saying let object 3 points to this object. So now we can say something like obj2 equal to object 3. Now these pointers can be moved to a different place. So if we do this, object 2 is going to point to this as well. And then I want to make one more point here by just having object 1 down to that one. So like this, see, like this. Now all three are pointing down here, but we don't have anything that is pointing to this object. Okay, if you have an object that nothing is pointing to, you have no way of accessing this because you can only access this through a variable. So this is just taking up space in memory and it can't be used. So periodically what JavaScript is going to do is going to clean up things like this through a process called garbage collection. Okay, and it will remove that. And that wraps up our section on pointers. Okay, so now let's talk about linked list here. Now this is going to be our first data structure that we built. Okay, and in order to introduce linked list, I am going to compare this to the data structure that is most often compared to. Okay, and that is array. Okay, so I am going to take this array and I am going to turn this into a linked list. So one of the things that arrays have that linked list do not have are indexes. So I am going to remove the indexes. Okay, also arrays are in contiguous places in memory, but linked lists aren't. They can be all over the place. So I am going to spread these out. And then one of the things I like to do when we move to a new data structure is represented graphically in a different way. So instead of green squares, I am going to use purple circles. Okay, purple circles here. Okay. Linked list also have a variable called head that points to the first item and one called tail that points to the last item. Then each item in the linked list points to the next, to the next, to the next. And the last one is going to point to null. Okay. So you will hear the phrase null terminated list. Okay. So this is an example of that. So I had mentioned before that arrays are in contiguous places in memory. Linked lists are not. They can be all over the places in memory where an array is going to be in a contiguous place in memory. So that's just a quick overview of linked list and how they compare to arrays. Okay, so now we are going to talk about linked list big O. Okay, we are going to look at the big O of all of the things that we do with the linked list. So I am going to bring up a linked list and we are going to bring a node in from the right, that 4 node. See this 4 node. Okay, And if we were going to add that to the end, if we look at the steps that we are going to have to do in order to do this, we could just have that last item points to that node. Okay, and now that we have something pointing to it, we can say that tail is equal to that pointer like this, and then it is added into the linked list. Okay, and it doesn't matter if the linked list had 4 items like it did here before we added this, or if it had 100 items, the number of steps would be the same, which means this is constant time to push. This is constant time to push something onto the end, which means O of 1. Okay, now let's look at removing that item. It look like all we are going have to do is just do those steps in reverse, and we are going to take that off and move tail over here, and we are done. But the problem with that is, in order to have this pointer point to that 7 node, we have to set it equal to something that is pointing to the 7 node, and the only pointer that is pointing to there is this one, and we can't go backward in the linked list. That is not possible. Okay, so in order to get to that pointer, we have to start at the head and iterate through the entire list to finally get to this pointer and set tail equal to that pointer, because we had to iterate through the entire list. That is O of n. So popping something from the end of a linked list is O of n. O of n. Okay, now let's look at doing this on the other hand. Let's bring that 4 in over here. So we have to have the 4 here, and we do have something already pointing at that 11 node, that is head. So we set the pointer from the 4 node equal to the pointer from head, and that points the 4 at this node. Then we just set head equal to the new node. Okay, so O of 1, that is O of 1. How about if we take it off? Well, we need to set head equal to the 11 node, and we do have an item that is pointing at the 11, which is the 4 node. We are going to set head equal to head.next, and we will get into that when we get into the actual code, but that moves head over, and then we can just remove the 4. So removing from the beginning is also O of 1. Now let's look at inserting something into the middle of the array. So let's bring our 4 node up down here, and we are going to insert this at the index of 3. We are going to insert it after this node here, that is at the index of 2012. Okay, this 23. Okay, so in order to do that, we have to iterate through at the start of the head and iterate through this entire one. Now we want that 4 to point to the same node the 23 is pointing to. Okay, right here. So we set this equal. Now the 4 is pointing to the same node as 23. Then we have 23 point to the new node, and this is inserted. But because we have to start at the head and iterate through the list to be able to get to the point where we equal to inserting it, O of n. This is O of n. Okay. Let's see if we are going to remove that same item. We would say let's remove the item at the index of 3. We start at the head. We go 0, 1, 2, 3. To be able to get there, let's drop this out down here. We want to have the 23 point to the same node that the 4 is pointing to. So we set the 23 pointer equal to the pointer 4. We drop this out, and that is O of n, because once again we had to iterate through the entire list. Okay, so let's look at finding an item. We could find something by its value or its index. Let's say we are going to find the number 23. We have to start at the head. Is this 23? No, that one's not 23, but that one is. Because we have to iterate through, obviously that is O of n. But what about by index? This is at the index of 2. If we are going to find something at the index of 2, once again we have to start at the head and iterate through. So whether we are looking for something by value or looking for it by index, it is O of n. It is O of n. Okay, this is the difference between linked list and arrays, because arrays we can go to the index as O of n, O of 1, O of 1. So now I want to bring up a table. Let's get out of the way and bring the table. And this just shows all of these operations and how linked list and arrays compare. All of the gray items are going to be same. Okay, but we have a couple here that are better for arrays, pop and looking up by index, or O of 1 for arrays, but O of n for linked list. And then we also have couple that are better for linked list but not as good for arrays, which is adding and removing item from the beginning and shift and unshift. It just depends what you are going to be using your data structure for. And that is our overview of linked list, big O. Now let's talk about linked list under the hood. Okay, so what is this thing really made of? So I am going to start by bringing up our diagram that we have seen before, and we are going to bring in a node from the right. And when we add this, we say the 7 node points to the 4 node, and that tail is going to be set equal to that pointer and points at that 4 node, and we add this into the linked list. What's really going on there? In order to answer that question, let's pop this 4 off and take a closer look at it. Okay, in order to understand this, we have to know what is a node made up of. Okay, it is this entire thing. It is both the value and the pointer. Okay, it's not just the value, it is the whole thing. So this node is actually an object. Okay, it is actually an object that looks something like this, that has value and next. So this is what we are adding into the linked list. We represent it graphically like this because this is easier to look at, but this is what's really going on. So when we say the 7 is going to point to that new node, the 7 looks like this. Okay, so how do we have the 7 point to this other object? How do we have this 7 point to another object? We do it by just having it equal to. We just have it by being equal to the object to the next value in the 7 node is going to equal to the other node. Okay, that is how the 7 node will point to the 4 node. And the same is true, of course, for the 23 node and the 3 node and 11 node. Okay, that is how it will be built here. Since this is the first node, that is what head points to, like this. Okay, and then we have tail point over, okay, like this. Okay, so it will be something like this. It will point to last item. Okay, so we can say it by saying it equal to, you can say tail equal to this one, you can say here like this. Okay, and then points it, and that points it over to here. So this set of nested object is what this diagram is made up of. Okay, so let's move back over here, and this is what our linked list looks like. Okay, now we are going to build our constructor for our linked list. So let's start our linked list class like this. Okay, and before we get into the code of creating the constructor, I am just going to do this like this with, okay, with without the code in the curly braces like that, because I want to point something out before we get into building the constructor. The constructor has a couple of things in common with a few of the other methods that we are going to build for the linked list, and they are push, unshift and insert. So the first thing they have in common is they each get passed a value, but they have something else in common. So let's look at what each of these do quickly. Okay, the constructor creates a new node at the time that you are creating the linked list. Push creates a new node and then adds that nodes to the end. Unshift creates a new node, adds the node to the beginning. Insert creates a new node and inserts it wherever that's supposed to go. Okay, so you can see the thing they also have in common is that they all creates a new node. So we don't want to rewrite this code for different times in each one of these methods. Okay, so we are going to create a separate class for creating nodes, and we are just going to call that class. node. Okay, and then when each of these methods below for the linked list needs to create a node, it's just going to call this class in order to create the node. Okay, so just to review here, when we are creating a node that looks like this, which is actually this is what we are creating with the node class. Okay, so let's bring back our node class and build out our constructor to build that node. So the first thing the node has is a value. And what I am going to do here, so we have a little bit more room, so I am just going to focus on this constructor portion like this. So we pass the constructor a value here. Okay, that's what this is equal to, like this. Okay, and then we are assigning that to the node. Okay, to the node. Okay, so let's bring in our node here, and there is this keyword. So we are specifically saying that this is the value for this node. Okay, so let's convert this to an object so we can see what we are doing here a little bit easier. So it is this object that we are giving it a value, okay, that we pass to the constructor of for. Then we have to say this dot next equals null, because this is not pointing to any node yet. Okay, so we just say next is equal to null. So let's bring in the rest of the code, and here that is our class for a node. So when we create a node, we would use a line that looks like this: const new node, that's the name of our variable, equals to new, which calls the constructor for the node and creates a node with the value of 4. Okay, so now we are able to create one of these for our linked list, and that's step 1. So now let's start building out our constructor for our linked list. Let's bring back our linked list code, and we are going to start this with the constructor, and I'm just going to focus in on this constructor code and take the rest of that from the screen now, so that we can understand this better. So the first thing that the linked list constructor needs to do is create a new node. So we are going to do that here, and the value that we pass to the linked list constructor is passed to the new node constructor. Okay, and then we have a new node. Then we are going to have head point to that. We do that like this dot head equal to new node. So this is specifically the head for this linked list. Okay, so head equals the new node that we just created in the line above. Okay, like that. And this equal, remember, is a pointer to that node. Then we are going to bring in tail, and we are going to say this dot tail equals this dot. In other words, have tail point to the same thing that the head is pointing to. You could also write this line of code as this dot tail equals new node, just like we did with head in the line above. But if we do it this way, we are saying that it is going to point to the same thing that head is pointing to, like this. And then with the linked list, we are also going to keep up track of the length. So we will say this dot length equals 1. So let's bring back in the rest of the code for the class, and you would create a new linked list by doing something like this. And when you do this, you say new linked list. We are going to pass in a number 4. What we are doing is creating a linked list with one node with a value of 4 with head and tail pointing to it. So let's bring back in all of the code here and go over to DevTools and look at this code in DevTools. So let's zoom in here, and this is the line of code where we create our linked list. This keyword here, linked list, is going to call the class linked list. The new keyword is specifically calling the constructor in the class linked list. Okay, and if we look at this constructor here, it is creating the new node. So this calls the node class here. Okay, and the new keyword is specifically calling the constructor. Okay, calling this constructor here. Okay, so let's run this, and it's come up with undefined because none of this code returns anything. So I'm just going to clear that off, and I'm going to type in my linked list. Okay, and I press C, And you can see that we have a linked list with a head points to a node and tail points to a node, and the length is 1 with a length of 1. But if we open this one, we get a little bit more detail. You can see that node head that points to is an object with a value 4 and next is null. The same thing with tail, where node is an object with value of 4 and next is null. So they are pointing to the same object, and then the linked list has a length of 1. Okay, so it looks like we have a working linked list constructor. So now we are going to do the push method, and to explain this, what I am going to do is I am just going to walk through the steps first. Okay, so there's our linked list. Step 1 is we need to create a new node. So I am going to bring one in from the right hand side there, like that. Then we are going to have the last node in the list point to it, and then we are going to have tail point to it as well, and that adds it into the list. That's all simple enough. We do have an edge case that we have to account for, and that is what if we are inserting this into a linked list that does not have any nodes yet. In this case, instead of having the last item and the tail point to it, there is no last item, and we are going to have head and tail point to it. As always, after we walk through these steps, I encourage you to pause this video and give this a shot yourself. Okay, now we are going to get into the code itself. So we are going to start out with push. We are going to be passing it a value, and as I just said, our first step is to create a node, and we do that with this line here, and that creates our node. Okay, and I'm going to start out with our edge case first. Our situation where we have head and tail pointing to null, we want those to point to the new node like that. So I am going to change this back to these pointing to null like this, and bring up our if statement. If, so we can say if head is equal to null. Now this, if this is true, that means head is pointing to something, nothing, and we do the opposite of this. We will do this one. So not operator here, this exclamation point there, that makes it the opposite. Okay, this is equivalent to of saying if this dot head is false, or if this dot head is equal to null, because null is false. Okay, so that's this situation here. So then we say if this dot head equal to new node like that, and this dot tail equal to new node, and now they both point to the new node. Okay, now let's take this code and put it in with the rest of our code so far like this. The next thing we need to do is say, well, what if we are putting this into a linked list where it does have node? So we are going to say else, and now let's focus on the else part. So we are going to say else this dot tail dot next is equal to new node. So if you haven't seen this before, tail up here at the top is equal to this node. So when you say tail, you are saying this node, but the next, let's turn this into an object and look at what this means here. So this is tail and dot next, which is the next pointer. Okay, and in that last node that tail was pointing to. So you are saying have next point to the new node, and we point it to the new node by setting it equal to the node like this. See, like this. Okay, so let's switch back to looking at this graphically like this. That is going to just point that arrow to that new node, and then we say this dot tail equal to new node. Okay, we will move that over here, and that inserts this into the list. So now let's take this code and put it back in with the rest of our code. So far we have created a node. Okay, we have this if statement to check to see if the linked list is empty. Okay, then we have this else to insert the node if the linked list is not empty. Okay, the only thing left to do are to increase the length by 1, and then we are going to say return this. And when we say return this, we are returning the entire linked list, and we will talk more about that here in a second. So let's go to DevTools, and So just scrolling through this, we have our node class up here at the top. The linked list class has a constructor and now has our push method that we just created. Okay. Down here we are going to say let my linked list equal a new linked list with a value of 7. And then we are going to push an item on with a value of 4. And this is going to return the entire linked list because of this line of code. When we say return this, what we are saying is return this linked list. Okay, because the push method is part of that linked list class. Now it's not just returning any linked list, it is returning the particular instance of linked list that we named my linked list. Okay, so let's go over here and run this, and it has returned the linked list. So let's open this one, and you can see here that head points to the 7 node up here. Okay, that is what we created the linked list with, and then we pushed on the value 4, and that is what tail is pointing to, and we have a length of 2. So it looks like we have a working method for push. So now let's talk about linked list pop method. Okay, and now let's see the steps that we would have to go through to create a pop method. Okay, and then we will actually go through how to code that. Okay, it's a little bit more complicated method than push, and we will see why here in a minute. So with pop, we are just going to remove the items from the end, move tail over to the previous item, and return the item that we removed. So we do have a couple of edge cases. The first edge case being that we might have a linked list that does not have any item in it, and obviously we can't pop something from this linked list. But the other edge case is if we have one item, and we will go over this in some more detail in this coding. But if you want to try to code this understanding that these are our 3 scenarios, we might have a list with one and one with no items and one with one item. You have to code for all 3 of those scenarios. You can pause the video here and try to code this. Otherwise, I am going to go into some more detail about what we have to do with the pop method. So I'm going to bring our items back here, and when we move tail over to the previous item, okay, this is a little bit more complicated than moving it the other direction, because you can see linked list, all of the arrows are pointing to the right. We are making tail to the left. Okay, but once we have done that, it's pretty simple to return this item. So let's bring this back and look at what we have to do to make the tail move back 1. And in order to do this, I am going to convert this from the graphical way that we are looking at this to looking at this as nested objects. So we are going to have tail point to the previous item, right? And then we will say tail next is equal to null, which removes that for node, and then we can return the for node. So let's bring everything back to the way it was, just like this, and look at what we have to do to make tail move to the previous item, because we want to have it point here. Well, we need to set it equal to something else that points to this node, and the only thing that points to this node is the next value in the previous node, right? The only way to get to this node is by the next value in this node and in this node, and so on and so on. And this is why we have to start at the head and then iterate through this until we get to this node. Okay, once we done this, we can have tail set equal to that, and that moves tail up. But we have to iterate through the entire list to make that happen, and that is why a pop is O of n operation, where push is O of 1 operation. And once we have moved tail up here, and we can say tail next is equal to null, then remove the node. Okay, so now let's put this back in graphical format like this. So how do we keep track of the nodes before the end? So the way we are going to do this is we have 2 variables, and I'm going to call them temp and pre. Temp is going to be the variable that once we iterate through this list is going through the last item that we return. Is pre is going to point to the item that is next to last. Okay, in other words, pre is going to point to the 7 node, and then we are going to set tail equal to pre. So for now I am going to remove head and tail. I am going to move pre like this, so it is a little easier to look at. And what we are going to do is we are just going to iterate through the list, and we are going to say dot next, and that's going to be that arrow of the 11 right here. If temp dot next is pointing to another node, in other words, if it's true, then we are going to say pre is equal to temp, and in the first iteration already is, and then we are going to say temp equals to temp dot next, which moves this over, and then we do it again to this point to a node, and then we are going to have pre move up here, and again until we get to the end of the list. Now this is going to be the last time we move these up, where we have pre move up. Okay, now this is going to be equal to null, which equates to false temp. Now next is now false. It stops our loop, and this is where temp and pre end up. So for now I am going to remove temp. I will bring this back in a minute, and then we are going to say that tail is equal to pre, and the only thing we were pushing and we are using pre was for to be able to set tail equal to it. So we are done with that, and then we say tail dot next. Dot next is null, which removes that last item. And I had mentioned that we are going to bring the temp here. I was pointing at this node, and then we return temp. Okay, so that walks us through how to do the pop method, and this is for if we have a bunch of items. Obviously it is going to be very easy to write the code for if we don't have any items. If head is equal to null and length is 0, so we will just say return undefined, and then the more complicated one is going to be if you only have one item. How is it that you are going to write the code for if you have one item, because that is one of our other edge cases. But that is how we are going to solve the pop method. Okay, now we are going to code our pop method. So we will start it out like this, and remember we have 3 scenarios where we had 0 items, 1 items, or 2 or more items. Okay, so I'm going to start with the easiest one, which is an empty linked list. Okay, and the way we deal with this is just to test see if the list is empty. We can do it like this, or this dot head equals null, or this dot length equals 0. Okay, we will return undefined. So we will drop this out of here, and now let's look at as if we have 2 or more items. So we showed in the last video where we are going to create 2 different variables. We will create them like this. Let temp equals to this dot head, and let pre equal to dot head as well. Then we are going to loop through this. I am going to use a while loop. You could use a for loop here because you are just going through the entire length of the linked list. So you could use the number that you have stored in this dot length. But I like using the while loop here because we are just doing this while temp next is true. And since this is a null terminated list, we are going to go and tell the pointer is going to be null. Okay, so temp next, if you look at the diagram, the 11 node there, that's that arrow there, and that I just highlighted. Okay, and then we are going to say pre equals temp, and for the first iteration through the loop, pre is already set equals to null, so this doesn't change anything. Pre equals to temp, and then we will say that temp equals to temp next, which is going to move temp over. So let's move this down like this, and we will walk through this all the way to the end of the list. Okay, so we will say while temp dot next is true, which means there is a node that arrow is pointing to. We will say pre equals to temp. So in the iteration it is not going to do anything, and then temp equals to temp dot next, which moves temp over. Okay, and let's just walk through this all the way to the end, highlighting the line of code that is used as thing here moving in the diagram. Okay, so while temp next, we are going to move pre up and then temp over, and then check if there is a node there. Again we will do it again, and then this will be the last time and that this is going to happen. It will be true, and we are going to move pre and temp, and this time this is going to be false. This is going to be false, and this is where pre and temp are left after we run the while loop. So for now I am going to remove the temp. I will bring this back, but that's going to be pointing for node, and we want to set tail equal to pre. We do that with this line of code here. This dot tail equals to like this. That was the only thing we were using here. So I'm going to just drop this out of the diagram. We will say tail dot next is equal to null. This dot tail dot next equals to null, and that breaks the for of the linked list. And let's take a look at the code. Remember, we created these two variables, and now let's look at this with the rest of the code that we have so far. And next thing is going to decrement the length. And remember, we do have one edge case that we haven't addressed, and that is if we have one item in the list. And if we do have one item in the list, head and tail both are going to point to it. And we had said that temp and pre were going to be equal to head. Okay, so those are both going to point to this one. So let's just walk through the rest of the code here, just from the while loop down. Okay, so I'm going to back up here. So what those first three lines, we have already run those. So these are the ones that are left, and let's run through these and see what happens when you only have one item, and it will become obvious what we have to do when we have one item in the list. So we are going to run while temp dot next. So temp dot next is null. So the while loop is not going to run at all. Okay, so we can remove that, and that's all we are going to use, the temp variable. So I'm just going to drop that out of here. So this dot tail dot equal to pre, that's already pointing at the same item, so that doesn't really change anything. So we can remove that line. Then we have this dot tail dot next equal to null. So tail dot next is already equal to null, so that's not going to change anything. So we are done with, and the only thing left that is minus minus, decrement the length. It was 1 and it decrements the length to 0. But notice that head and tail are still pointing to that one node, and obviously we have popped that off. Head and tail should be pointing to null. So let's go back to our code here. And the thing that we have to change here is to say if this dot length equals 0, and remember this is 0, after we have decremented it here, then what we need to do is we need to set head and tail equal to null, which gives us this, which is exactly what we want. The only thing left to do is to return temp, which is the item that we popped off, and we returned that. Okay, so let's go back and look at our code, and let's flip it over to DevTools and look at this code over there. Okay, so here is our pop method. This if statement here at the top is for we have 0 items in our linked list. Okay, the code from here to here works if we have 2 or more items, and this will run if we have only one item in our linked list. Okay, so what I have done here is I have a linked list that is just going to have 2 items, and the nodes are just going to be 1 and 2. Okay, and I'm going to run this. So let's take a look at this, our linked list here. Okay, let's open this up. So the head is pointing to the node with the value of 1, and tail is pointing to 2. Okay, we have a length of 2. So this is going to make us easy for us to test having 2 or more items, pop that off, then having 1 item, then 0 item. So we can run the pop method 3 different times and test all 3 of our different scenarios. Okay, I'm going to clear this off. So I'm going to say my linked list dot pop and press enter. As we would expect, this return the 2 node. Now let's type our my linked list again. See, and what we have remaining in the linked list is the one node has both head and tail pointing to it and a length of 1. So that works for having 2 or more nodes. See, it is working. Now let's clear this off, and we will run pop method again, and we press enter. It returns that one node. If we look at my linked list, see, now we have an empty list, head and tail both pointing to null. Okay, So let's run pop one more time to see if this works correctly. When we have 0 items in our list and it is returning undefined, that is also correct. So all 3 of our scenarios are working, which means we have a working method for pop. Okay, so now we are going to write our method for unshift, and this is what unshift is going to look like. We are going to create a new node. We are going to want to have that new node point to the first node in the linked list. Okay, in other words, we are going to set it equal to head. We have head set equal to the new node, and that adds it into the list. Okay, so you could have a linked list with some items in it like this, or the linked list could be empty, in which case you are just going to set head and tail equal to the new node. So if you are going to code this, go ahead and pause this, and otherwise we can jump into the code. So we are going to start it like this. It's unshift. We are going to pass it a value, and the first step with unshift is that we need to create that node. So let's do this. Okay, and that we will create a new node that we are going to use. And as always, when we are going to add a node to anything, we want to start with this situation. Okay, where we have data structure empty. So we are going to say if head is null with that exclamation point, this dot, we are going to have this dot head equal to new node, and now head is pointing to the new node, and then this date dot tail is equal to new node, and they both point to the new node. So let's put this if statement in with the rest of our code and have a look at that. This is what we have so far. So our other option is that we are putting this into a linked list that already has items. So we are going to say else. Okay, else, and let's build out this else statement. So like this, else new node dot next equals this dot head, and that does this point that at that first item in the linked list, and then this dot head equals to new node, that moves that over and adds that into the list. So that's everything for our else statement, and let's put this in with the rest of our code like this. Only thing left to do are to increase the length by 1, and then returns the entire linked list. Okay, so we will look at this code in just a second in DevTools, and when we go over to DevTools, we are going to create this linked list. Then I am going to add an unshift with the number 4 and add that into the list. So let's go to the dev tool and have a look at that. Okay, so there is our unshift method, and this is going to create the linked list that I just showed in the diagram. Let's run this, see, and that is going to create the linked list with a length of 4. You can expand this one, and we have a linked list with head pointing to 11 and a length of 4. Okay, so I'm going to clear this, and then I'm going to run unshift with the number 4 like that, and we press enter, and now our linked list has a head with a value of 4. That's the item that we just unshifted onto the linked list, and the length has been increased to 5. Okay, and that is our method for unshift. Now let's do our shift method. Okay, so we are going to move head over to the next item. We are going to remove the first item, and we are going to return it. So same terminology as we used with an array when we are removing the first item. Okay, so we have a couple of other scenarios that we have to code first. The first one being if we only have one item in the linked list, and the other one being if we don't have any items in the linked list. So if you want to code this, go ahead and pause the video here and give it a shot. Okay, so we will start our code out like this. This is going to be our first scenario that we code for, is if we have an empty list, linked list, and we will just do this like this. If head is null, we are going to return undefined. Okay, and our next scenario is going to be if we have 2 or more items in the linked list, and we will code this. So remember, we are not only removing this item, we are going to return it, and if we are going to return it, we have to have a variable set equal to it, and we have head equal to it now. So we will have this variable be set equal to head. We will do that like this. Let temp equal this dot head. Then we want to move head over to the next item. So we are going to set head equal to head dot next, like this and like that, and we do that with this line of code. This dot head equal to this dot head dot next. Then we need to remove this item. This is not good enough just to return temp as it is, because if you do, you are not going to just that 11 node, but the 11 node has the 3 node connected to it, and so on and so forth. You will get the entire linked list. So you have to send temp equal to null to actually break that connection, like this. So temp dot next equal null. We will do that for us, and we will be returning temp at the end of this, but for now I'm just going to go ahead and remove it like that. Then we will just need to decrement the length by 1. Now we are going to code for when we have one item in the linked list. So what I am going to do is, if I am just going to keep those last 4 line of code, so that's going to be relevant here, that if statement, when we run this code, when we have one item, so let temp equal this dot head, that's going to have temp point to that same node that head is pointing to. Let's remove that line of code. Then we are going to say this dot head equals this dot head dot next. So head dot next is null. Okay, so this sets head equals to null. Then we say temp dot next equals null. So temp dot next is already null, so that doesn't do anything. Then the only thing left to do is to decrement the length. Okay, well, the length was 1 and this changes it to 0. So we run all this code, we gotten the length to 0 and tail is still pointing to that node, right? So we need to do is say if the length is 0, this dot tail equals to null, and that fixes the problem. Let's put this code in with the rest of our code and we have a look at this. Then I want to emphasize that this if statement for the length being 0 is after we have decremented the length here. It was 1, we decremented it, and then it is 0. And now the only thing we left to do is to return temp, which is the item that we shifted. So we will look at this code in a moment in Chrome Dev Tools. And when we do, we are going to create this linked list. And the reason for that is if we have 3 different scenarios, so we can test shifting one off with 2 or more, then we can test with one item, and then we can test running this with no item, which should return undefined. So let's flip over to DevTools and we will start out by creating this linked list. Okay, so let's see here. This is our method. This is where we create our linked list with our 2 items in it. We will zoom back out and run this. And that has created this linked list here where head is pointing to and tail is pointing to 1. So let's clear this off. Then we will say my linked list dot shift, like that. And now we have removed that 2 node. So if we type in my linked list, now the linked list only has one item in there with a value of 1. Let's clear this off and let's try this with only one item in the linked list. Make sure that works. So, and now that's returned that one node. And let's clear this and let's try this with our empty list to make sure that this is also working, and that is indeed returning undefined. Okay, so this is our method for shift. Okay, so now we are going to build our get method. The get method is pretty simple to explain. Okay, we are just going to get the node that is at a particular index, and that's it. Okay, so if you want to code this, go ahead and pause this and see if you can write this code. Okay, this is one of our simpler method, so this is a great one to try. Otherwise we will get into this. So I'm going to bring up a linked list here, and I included the indexes here because they are relevant since we are searching for something by index. Okay, so we could get anything from 0, 1, 2 or 3. Okay, from these ones. But what we can't do is we cannot return a node at the index of -1, or we could say anything less than 0, and we can't return anything at the index of 4 or greater. Okay, that is also here. Okay, we could say greater than or equal to this dot length. Okay, so we could do it like this: with the index is less than 0 or it is greater than equal to this dot length, then we are going to return undefined. Let's bring this back our linked list here, and order to able to return a node, we are going to have to set a variable equal to that node. We are going to call this temp and we will just set it equal to head, and we have to start at the beginning of the list. Then we can iterate through the list however many items we need to get to the item at the index that we are looking for. So we do that by saying let temp equal this dot head, and then I am going to remove the tail here. Okay, then we have a for loop to iterate through this list, and all the for loop does is move the temp variable forward. Okay, so say we are looking for the item at the index 2, it would return the for loop 1 2 times and then return the item. Okay, return the item that is pointing to it, it will return temp. Okay, so that is all of our code for get. The only tricky part of this method is to remember to write this if statement for anything that's out of the acceptable range. Okay, but other than that it is a pretty straightforward method. So when we flip over to Chrome DevTools, we are going to build out a linked list that just look like this where the index and the value is going to be the same for every node. So let's flip over to Chrome DevTools. So there's our get method, and this is where we build our linked list. Okay, 0 2 3 3. So let's run this and let's open this up. Make sure our linked list looks the way we expect it to. Head is pointing to a node with a value of 0, tail is pointing to a value of 3, and we have a length of 4, so that is perfect. So we will say my linked list dot get, and I'm going to pass it a value of -1 undefined. Okay, just like we would expect. Then I'm also going to try a value that is greater than our range, so 10. Okay, and that also returns undefined, so that is perfect. And then let's have a valid range. So the node at the index of 2 is going to have a value of 2. Okay, and that is exactly what we expect, and that is our method get. Okay, so now let's do our set method. Okay, so it is very similar to get, and I'm just going to bring this up like this, but instead of just getting something at an index, we are going to go to that index and change the value of the item at that index. So there is not much more to explain than that. So I'm going to say, if you want to code this would be a good place to pause this, but I would give you one clue before you do that. Okay, you can use other methods inside of a method. So you can use the get method here, or you can do the entire set method without doing that either way. The way we are going to do it is by using the get method. So I'm going to bring up a linked list like this. And one of the things that we know is if we are going through to iterate through the list, get to a particular index and change something, in order to iterate through the list, we are going to need a variable. So let's say we are going to go to the index of 1 here, and we are going to change the value of this item from 3 to 4. It would look something like this. So from now I am just going to change this back. Okay, so for now I am just going to say let temp and get set, we set temp equal to this dot head. Okay, I'm not going to do that here. I'm going to show you why here in a second. So there is a lot of similarities between the set and the get method as far as all the steps that we need to do. So just like the get method, if we have an index of -1, or we could say anything less than 0, we want this to be undefined. Anything that is greater than or equal to this dot length, we want that to be undefined. Otherwise, we want temp to point to the appropriate node, so we can do that by just saying let temp be equal to this dot get, and pass it the index that we are looking for in the set method. And that's going to either take temp and make it where it is undefined. Okay, temp is going to be equal to undefined in this case, or it is going to be equal to the node that we are looking for. So what we have to do at this point is determine is temp undefined or is temp pointing to a node. So we will do this with an if statement. We will just say if, and this is true if temp is pointing to a node. And then we say temp dot value equals to the value that we pass to the set method. Okay. And then in this case we have this equal to 4, and that changes that 3 to a 4. But there is one more thing we have to do inside this if statement. We need to code to stop running at this point. So we need to return a statement, and we will return true that we are able to change that value. Otherwise temp is undefined, which is going to cause that if statement to not run, and we are just going to return false. And that is all of our code for the set method. It is very clean because we are just reusing the code that was in the get method, and we don't have to write all that again. So we will look at this code in a second in a dev tool, but first I am going to bring this up, and this is going to be the linked list that we create when we go to the dev tools. Okay, and what we will do is we will run the set method with an index of 1 and change the value to 4 at that index. So let's flip over to DevTools. There is our set method, and this is going to create that linked list that I just showed the diagram for. I'm just going to run this, and it returns the linked list. Open this up, and I really want to look at that second item since that's the one we are going to change. So that's this item here has a value of 3 for now. And I'm going to clear this. I am going to say my linked list dot set with an index of 1 and a value of 4, and it returns true. So I'm going to clear this, and now let's look at our linked list, and I'm going to open this up and look at our second item, and the value has now been changed to 4. Okay, so that is our set method. Okay, so now we are going to do insert to describe what this does. I am just going to show this. We are going to insert a new node with a particular value that we pass this at a particular index. Okay, pretty self-explanatory. So if you want to code this, go ahead and pause this. Otherwise we will get into this. Okay, we are going to start out with this linked list, and we are going to create this node. So there are a few possibilities for different places where we can put this, and we will handle these situations differently. Say we want to put this at the index of 0. Okay, so that's going to go through right here. So we have seen this before. Okay, that this is unshift. This is unshift when you add something to the beginning of a linked list. Okay, so we can just say if the index is 0, return this dot unshift and pass it the value that we had passed the insert method. Okay, so a couple of things I want to point out here is when we are doing this, we are using the this keyword, and what we have seen when we call a method before is we would say something like my linked list dot unshift and then pass it a value. But this has to apply to any linked list that we are going to use with the linked list class. We have to use this keyword. The other thing is we are using is return, which makes us stop running the code. It's just going to return whatever unshift returns, which is going to be the entire linked list, okay, with that new code added. Another possibility is that we put this at the other end, and we have seen this before as well. So we can say if the index is equal to the length, return this dot push, and we just use the push method. Another possibility is that we try to insert this out here at an index that does not work on the index on this end or on this end. So we can say if the index is less than 0 or if the index is greater than the length, then we will return false. So let's go ahead and look at our 3 if statements here. And what we done here is what we would do if we were put at this beginning of the linked list. That this is for if we put at the end, and this is for it if it is out of possible range. Now let's look at putting this in somewhere in the middle of the list. Let's say we are going to put this in the index of 2, just like that. How would we make that happen? So let's back this up and look at the steps to make that happen. So one of the things we are going to have to do is have a variable that is going to iterate through the list to where we are going to insert this, and we are going to bring this to the spot, that is one spot, before we are going to insert this. Okay, so let's look at the code to create these 2 items. That's our new node, and this temp, we are going to say that temp is this dot get of the index where we are going to insert this -1. So it's going to be the previous spot. It is going to be the previous spot. So let's look at this code. So now notice, if on our first 2 lines of code we are calling other methods, and now we are just using the get method. So this is our 3rd time using another method inside of this method. Okay, so let's bring this back up. So the first thing that we want to do is we want that new node to point at that 23 node at the index of 2. So we can set that pointer on the new node equal to temp dot next, just like that. And we will do that with this line of code. New node dot next equals to temp dot next. Then we want to have temp dot next point to the new node like that. Okay, and we will do that with the help of this code here. Temp dot next equals to new node, and that will insert that node into the linked list. Okay, so now let's look at this code with the rest of our code, just like this. The only thing left to do are to increase the length by 1, and then what we will do is we will return true because we used a return of false in the 3rd line of code up there. Okay, and that if statement, in that if statement. So we will look at this code in a moment in DevTools, but this is going to be the linked list that we create, a 0 and a 2. Then we are going to insert a node with the value of 1 at the index of 1. So it is going to be insert 1, 1. Okay, so now let's go to the DevTools and have a look at this. Okay, so there is our insert method that we just created, and this is our linked list with the 0 and 2. Okay, now if you try to run this, and this creates our linked list with value of 0 and 2. Okay, so let's clear this off. Then we will run our insert method. So this is with an index of 1 and a value of 1. Okay, we will run that. It returns true. Okay, clear this. And now look at my linked list. So now my linked list, it starts with 0, and that is our value of 1, and then you can see here that tail has a value of 2. Okay, and that is our method for insert. So now we are going to do our remove method, and it is just going to be removing an item from a particular index. So that's pretty straightforward. If you want to code this, go ahead and pause this here. Otherwise, I am going to get into how to create this method. Okay, so I'm just going to bring up a linked list here, So one of the things that we can do is we can remove the first item, and we have seen this before. This is a shift. Okay, so if the index equals 0, we can just remove this dot shift. Okay, also we can remove the item from the other end, and we have created code for this one as well. So if the index is the length -1, we can just return this dot pop. Also, we can't return an item at an index of -1, or we could say an index of less than 0, and we can't have an index that is greater than or equal to the length. So we can create that an if statement that say if it's less than 0 or greater than or equal to length, we are going to return undefined. So here are those 3 if statements that we just created, and we will remove those. Now let's try removing something at an index that is somewhere in the middle of the linked list. We will do the index of 2. So we know that if we are going to return that item, we are going to have a variable pointing to it, and we are going to have another variable that points to the previous node, to the one that we are removing. I am going to call this before. So let's just create these variables, and we can use these with the get method. So we can say before equals this dot get index -1, the index that we are removing. Okay, so the temp variable, we could use the get method again and just say get the item at the index that we are looking for, but that is a O of n operation, right? And there is a more efficient way to do this. We can just say temp is equal to before dot next, right? Before dot next. Okay, so let's take a look at this code. So we have our if statement, and we have our 2 variables. Okay, let's bring our linked list back up here, and this is the item we are going to remove. I'm just going to move this up here. So we want to have the item at the index of 1, the one that before is point to that 7 node. So we are going to say before dot next, we are going to set it equals to temp dot next. See, like this. Okay, like this. We will do that like this. Before dot next equals to temp dot next, and that moves that arrow down to this one. Then, and that's all we are going to need to do for before variable. So I'm going to remove that. Then we will say temp dot next equals to null to break that off that list, like that. And we will do that with that line of code. Temp dot next equals to null, and now that is out of the list, we will go ahead and decrement the list by 1. So we are done with the list. I'm going to remove those, and then we can say return temp, which returns that item that we removed from the list. So now let's look at this code with the rest of our code here, and that's all of our code for our remove method. Okay, and let's look at this in our dev tools. So we are going to create this linked list as an example. We are going to create this linked list in our dev tools, and we are going to remove the item at the index of 2. That is what I will show you as an example. Okay, so now let's go to the dev tools. Okay, there is our remove method. Okay, this is our remove method, and here is our linked list 11 3 23 7. Let's run this. Let's just open this up, and we have head pointing to 11 and tail pointing to 7. Let's clear this. Okay, let's run our remove method, and we are going to pass it the index of 2, and that returns the 23 node, just as we expected. So I'm going to clear this, and we are going to have a look at our linked list, make sure that it looks the way that it should look, and it has a length of 3, then it is 11, and then it is, and 3 is 11, and then 7. Okay, so it's look like we have a working method for remove. Okay, so now we are going to do reverse, and this is a very common question, interview question, to be able to do reverse of a linked list, and this one is complicated. Okay, so it's pretty straightforward. What we are going to try to do here is just going to be a method called reverse, and it is going to reverse the linked list. So I'm just going to jump into this. So it's going to look something like this. We are going to take head and tail and switch it like that, and then we are going to do one by one, take the arrow and point them to the other way, see, like this. So I want you to notice that there is a gap here, and this is the hard part of reversing the linked list, is making sure that you keep track of where everything is while you are introducing all of these gaps all the way down the linked list and continuing to reverse it, this until it is completely reversed. Okay, so let's move everything back and move this down, so we will have a little bit more room for coding here. In order to switch head and tail, we are going to need a variable that we set equal to head, and then what we can do, we can say head is equal to tail. Okay, and now it's point to the other end, but you need that variable to get tail over to the beginning, so we set tail equal to temp. Okay, so let's walk through what we just did here. We create a temp variable, we set it equal to this head, then we set head is equal to tail, and then we set tail equal to temp. So let's look at this code. See, like this is what we have so far, and this is really the easy part, just making head and tail and switching them. Reversing all the node is going to be the hard part of reversing the linked list. Okay, so now let's bring this up, and now we are going to create a couple more variables. We need to have something after temp. Okay, I'm just going to call it next, and it will point to the next node after temp, and we will just set it equal to temp dot next, so it will point to the next node. And then we are going to have one more that we call previous, and we will start that out by being equal to null. So we are going to have a loop that is going to move these through the list as we are reversing everything. So I'm just going to move this back, and we need to create these variables. So next equals to this dot temp, like we just mentioned, and previous is just going to be set equal to null. So let's put this back here in the diagram like this. Now let's look at the code what we have created so far. Okay, we have reverse head and tail, and we have created our variables. So now we can create our for loop, and so we can say next equals temp dot next, and that already does equal that in the first iteration of the for loop. Temp dot next equals to previous. So now temp dot next, which is highlighted here, see, we are going to set it equal to previous, which is basically null, right? Like this. Previous equals temp, that is going to move that up, and temp equals to next. See, this is why that you need the next here, because it is going to enable you to cross the opening, across this opening. So you have to have something on the other side, temp, to be able to cross that opening. But look at now, the opening is on the other side of temp, so that's why you need previous. So let's just walk through this. We are going to say next equals temp dot next, and we have to do that first, because the next thing we are going to do is we are going to flip that arrow over here on that node, and next is going to allow us to be able to cross that gap the next time we leap through. Okay, and the previous equals temp, temp equals to next, and let's just keep running through this, and we will say temp dot next equals previous, previous equals temp, temp equals next, and this will be the last time when we run through this. We are going to say next equals to temp dot next, well, it is because it is null, so that will be here. Temp dot next equals previous, that will be our last one that we flip over. Previous equals temp, temps equal next, and that is our for loop. So let's put this in with the rest of our code like this, and then we are going to return the entire linked list. So we will look at this code in a second. This is going to be the linked list we created when we go over to DevTools, and then we are just going to take it and reverse it. Okay, so let's flip over to DevTools. There is our code there. Okay, and here is our linked list, just 1 2 3. Okay, and we will zoom out and run this. Now let's have a look at this linked list. Head is pointing to 1. If we open this up, the next value is 2. And if we open this up, the next value is 3. And next points to null, which means we are at the end of this one. That is our 1 2 3. And let's clear this, and we can run our reverse method. Okay, so now, and let's open up the linked list here. Now head is pointing to 3. We open that one. Next item is 2. Then the next item is 1. Okay, so that is our method for reverse. Okay, so now let's talk about doubly linked list here. Okay, so I am going to just jump in right into creating a constructor for this, and I am going to start out by comparing this to a singly linked list. It is just like like this, except we have an arrow that goes the other way. Okay, for now I am going to convert this back to a singly linked list and just look at one of the nodes like this. Remember, it was just a value and next, and our constructor looked like this. We just had to create value and next. So let's convert this back into a node, and now our doubly linked list node, this is just going to have value and next and previous. Okay, the only difference being the previous value. So our constructor is going to look like this, and the only difference in this constructor is going to be this line. Okay, now let's look at the linked list class and how it is that we build the constructor. I am going to focus in on the constructor like this, and we built a new node, and this is going to be the same for a doubly linked list. This line of code doesn't change, it's just that the node class changed. Okay, so when we create this node, it's going to have next and previous, and there is our node, except it is going to have another arrow. Okay, then we have head point the new node with this line of code, and then we had tail set to this dot head. So it is just pointing, head was pointing to. Okay, and we made the length equal to 1. There is nothing that changes in the constructor. The only thing that changes is in the node itself, and that first line of code. When we create the new node, it is calling a different node class. Okay, so let's bring back in these lines of code. The only change that we would make here is to name this doubly linked list instead of linked list. Okay, so we'll look at this code in a second in Chrome DevTools, and then we will also create a new doubly linked list starting with the node with the value of 7. Okay, so there is our code, and like I mentioned, the only difference is that the node has previous, and that we change the name from linked list to doubly linked list. Okay, so we will create our new linked list down here, and I'm going to run this, and it has returned our linked list with a value of 7. Okay, the difference here being that each of these nodes has next and previous. Okay, so it looks like we have a working constructor. Okay, so now let's look at our push method. I am going to compare this to a singly linked list. Remember, with this, we just created a node, pointed the last node to the new node, moved tail over the new node, and that added that into the list. It's going to be almost the same for a doubly linked list. The only difference is going to be that green arrow here. So we will still going to point the last node to the new node, But the difference here is that we need to take the new node previous and point it to that last node. Okay, we still move tail over and that adds that into the list. And just like with a singly linked list, you can have an empty list, in which case you are going to set head and tail equal to the new node. Okay, if you want to code this, go ahead and pause the video, otherwise we will get into the code. So we are going to say push, pass it a value, and then create a new node. Okay, so for this is all the same. So then we will start with an empty linked list. So I'm going to say if this dot head is null, we will have this dot head equal new node like this for a singly linked list, and like this for doubly linked list, but the code here is going to be the same. And this dot tail equals new node, which will do that. So let's add this if statement in with the rest of our code. This is what we have so far. So this if statement is if we have an empty list, otherwise else we have one or more item, right? So let's build this else statement out. Okay, so we will say this dot tail next equals new node. So that's tail dot next equals new node, that connects that arrow, and we will say new node dot previous equals this dot tail, which is going to connect that over here. Then this dot tail equals new node, which moves that over and adds that into the list. So let's take this else statement and put it in with the rest of our code like this. The only thing left to do are to increase the length by 1, okay, and return the linked list. Okay, so the only line of code that is different between a doubly linked list and a singly linked list is this line of code right here to connect that arrow from the new node back to what had been the last node in the linked list. So we will look at this code in a moment in DevTools. Okay, and when we do, we are going to build a linked list with numbers 1 and 2. Then we are going to push a 3 onto the end. Okay, so let's go to DevTools. Okay, there is our push method, and this is where we are building a linked list with the number 1 and 2. Okay, let's zoom out and look at this here. So this is our doubly linked list. Let's expand this, and we have a linked list with head pointing to 1 and tail pointing to 2. So I'm just going to clear this, and we will run my doubly linked list dot push with a value of 3 and press enter. And now the length has been increased to 3 and our length list, and we open this, and tail now points to 3. See, tail now points to 3, and it looks like we have a working method for push. Now let us build our pop method. Okay, I am going to bring up a singly linked list here, and if you recall, with a singly linked list, to pop an item of the end, it was an O of n operation, because in order to move tail over to here, we have to start at head and iterate through the entire list until we got to this point, and that we could set tail equals to this node. Okay, but because all of the arrows pointing forward, we had to do that entire process of iterating through the list. But with a doubly linked list, this is different, because we do have arrows pointing backwards. So what we can do is this. We know that since we are going to pop that off, we are going to have a temp variable pointing to that last item and return that. So I'm just going to bring that up here. Now instead of having to iterate through the list to have tail, go back one item, we can just go tail is equal to tail dot previous and move that right over. Once that's moved over, we can say tail dot next, we will set that equal to null, and then temp dot previous, we can set that equal to null, and that pops that off the end of the list. And then we just return temp like that. But one of the things that is similar between a doubly linked list and a singly linked list is that we have a edge case here. if there is only one item, we are going to have to write some code for that. And then of course, if there is no items, you cannot pop an item of the end of the list. If you want to give this a shot, go ahead and pause the video, write the code. Otherwise, I am going to get into the code. Okay, so the first thing we are going to code, or is if we have an empty list, link list. Okay, so we can do that like this. And this is the way we have done it before. We could say if tail is null. We could also say if the length equals 0. This is what I am going to use here. I am going to return undefined. Okay, so let's bring up our doubly linked list here. We need to create our variable. So we will say let temp equal this dot tail like that. And in order to move that tail over, we can say this dot tail equals this dot tail dot previous, and that moves that over. Tail dot next equals to null. Okay, and that breaks that off from there. And temp dot previous equals to null. So temp dot previous will be null. Okay, see? And then we just need to decrement the length by 1. So let's look at this with the rest of our code. Looks good so far. We need to also write the code for when we have only one item. So if you recall, if you look like this, it looked like this here in a singly linked list. We could it would be the same here as well. And if this looks unfamiliar to you, we went over this in detail in the pop method of the linked list. You can refer from there. Okay, and remember that this is 0 after we have decremented the length. Okay, so this applies to when we had 1. We decremented the length and the length became 0. Then we just need to return temp. So I'm going to do something different with the code. And the reason is this could be a little confusing when you are reading it, because you have if this dot length equals 0 here, and then if we have this length equals 0 here. Now this once happens after we decremented the length, but it still may not be easy to read. So what I'm going to do, I'm going to take this whole if statement here and I'm going to move it up above where we decrement the length. Now I'm going to remove some line of code here. I'm going to remove 5 lines and I'm going to bring them all back to the here like this. Okay, so I'm going to take these 5 lines out. They are all coming back in a second. So this if statement is for when we have one item in the list, right? So I'm going to change that 0 to a 1 where I move it up here. So we have if statement for when there are 0 items or 1 item, or we could say else. Okay, there is 2 or more items. We can bring these lines of code back in for where there are 2 or more items. Okay, then you can decrement the length and then return temp. So all I have done here is rearrange the code to make it easier to read. When we wrote this the first time in the linked list section, I did that in a particular order so I could explain the concepts in the order that I wanted to explain them. But a lot of times as you are figuring out how to code something, you will get to the end of it like we did here and go and you will be able to see that you can do it in different way as well. Okay, that we can move these code around up, down, and we can arrange these code according to our own comfortability here, understanding here. Okay, so it is much easier to read items like this, that we have 0 elements, 1 element, then 2 or more elements. Okay, it is easy to read this way. So now I'm going to put the code back to the way it was and just watch how everything moves here. It is the same code. And then I'm going to move it back. The only thing that I have added here is an else. That is the only thing I did. Okay. Other than that, it's all the same code. So we will look at this code in a moment in the dev tools. And when we do, we are going to start with a linked list that looks like this. So we want to make sure that our pop methods work with 2 or more items. Then we will pop an item and we will say if it works with 1 item, pop that off. We will say if it works with no items. Okay. And this is where we would expect this to return undefined. So let's go to DevTools. This is our code. Okay, this is our pop method. And this is where we build the linked list 1 and 2. So now let's try to run this. Expand this one. So we will have value of 1 and 2. and now I'm going to run pop. That returns the value 2. And if we say my doubly linked list again, see, now you have the length of 1. Okay, and let's clear this, and if I do that again, pop method again, then it returns the value 1. And now the linked list, my doubly linked list length is 0. That means there are no elements in the linked list. And now if I run the pop method one more time, now you are getting undefined. Okay, that means everything is working properly. Okay, that means everything is working properly here. So that is our method pop. Okay, so now I'm going to do unshift here. So it is going to look like this, and we are going to have a new node that we create, and then we will have the next arrow on that one point to the first node in the list, and we will have the first node point back to it, move head over, and that adds it into the list. We can also have an empty list, in which case we just set head and tail equal to the new node. Okay, so if you want to code this, pause the video here and try yourself. Otherwise, let's go to the code. So we will start with the unshift. We are going to pass it a value. We will create a new node here with that value like this. Then we will start with adding this into an empty linked list. Okay, where we just set head and tail equal to that node. So with this dot length equals 0, we are going to set head and tail equals to the new node. Else there is one or more items, and we will expand this else out, and we will bring up this list. So we will have the arrow from the new node point to that first node. We will do that with this line of code, new node dot next equals this dot head, and then we will have the arrow reach back over to the new node with this line of code, this dot head dot previous equals new node. Then we will move the head to over with this, and this dot head equals new node, and that's add that into the list. So let's put this code here with the rest of our code, and now we just need to increase the length by 1 and return the entire linked list. So let's look at this code in the dev tools, and we will create this linked list here with 2 and 3. Then we will unshift on a node with a value of 1. So let's flip over to dev tools. So there is our unshift method, and we are starting with this list here with the items 2 and 3. Okay, now let's try to run this one. So you will get this doubly linked list, expand this one. You will see we have 2 and value 3, value 2, value 3, and we have a length of 2. So let's clear this, and I'm going to unshift a node with a value 1. So now let's open this, and now you can see that heads point to the value of 1 and our length is 3, and that is our method unshift. Okay, so now let's do the shift method here. Okay, shift is going to look like this. We are just going to remove that item from the beginning of the list, and just like with the regular linked list, we have an edge case of one item, and then we also have to write code for if we have no items. So if you want to code this, pause it here. Okay, so now I'm going to start with the code. So as usual, when we are going to remove an item, we are going to start with the case of when we don't have any items in that list. Okay, so if this dot length equals 0, we are going to return undefined. So the next situation is for when we have one item, and it doesn't matter if we have one item or 2 or more items, we are going to need the temp variable. Okay, so I'm just going to declare here and just set that equal to head. But when we remove the one item, we do have the set head and tail equal to null, and I'll do that like this. If the length is equal to 1, we are going to set head and tail equal to null. Okay, so now we have written code for 0 items and 1 item. Otherwise there is 2 or more items. So else we will build this else statement out, and we will bring up our list like this. So the first thing we are going to do is move head over 1, and we will set head equal to head dot next. Okay, like this, and that moves head over here. and then we want to remove this item. In order to do that, we need to take those two arrows and set them to null. Head dot previous equal to null. Okay, like this. Okay, and then temp dot next, we will set that equal to null, and then that breaks that connection there. At the end, we will return this temp node. But for now, I am going to put this code in with the rest of our code like this. And then we are going to decrement the length, and then we will return that item. So we will look this code in our DevTools, and we will build this linked list because we want to make sure that this is going to work with two items. Okay, then shift is going to work with one item, and then it is going to work correctly with we don't have any item. Okay, so let's see DevTools. Okay, so this is our shift method, and this is the 2 and the 1 for our linked list here. Okay, now let's run this one. This linked list has head equal to 2, tail is equal to 1. So I'm going to clear this, and I'm going to run shift. So that returns that 2 node. And if we look at our linked list, we should just have one item in there with a value of 1. And we open this, and head and tail are both equal to 1, and we have a length of 1. And now we know that this works with 2 items. So we will do this again to make sure this works with 1 item. That returns the 1 node, and then we look at the linked list itself, and we don't have any items in the linked list. Head and tail both are null, and length is 0. Okay, so I'm going to clear this. Now if we run this one more time, and we would expect this to return undefined, and see, and it does indeed return undefined. Okay, so this is our method shift. Okay, so now let's do the get method, and with this one we are just going to get a node at a particular index. Okay, so if you want to code this, pause the video here. Okay, otherwise we will start building this out. So I am going to start with a singly linked list, and we will walk through this, and then we will look at the differences. So with a singly linked list, you could have something at the index of 0, 1, 2, 3. Okay, but you can't have an index over here. We could say an index less than 0. Or over here, we could say an index that is greater than or equal to the length. Okay. And this is going to be the case whether you have a singly linked list or a doubly linked list. You have to say if either of these are true, then we are going to return undefined. Okay. Let's bring our list back up here, and we are going to set temp equal to head. We will do that like this. And I'm going to remove head and tail from the diagram here just to keep temp there. And then if we were going to iterate through the list, we were going to do that with a for loop like this and say temp dot next. So let's say we are going to find something at the index of 2. We are going to go 1, 2 times through the for loop, and then we are going to return that item. Okay. So let's put this in with the rest of our code. This was the entire method for get for a singly linked list. Okay, but we are going to make some changes to this for a doubly linked list. So let's bring this up here. Let's turn this into a doubly linked list like that. And let's say we are going to get this 3 nodes here. The one at the index of 1. We would start at head, and we would get to this node. Then we would return that node. Okay, but what if we wanted to get this node? The quickest way to get there wouldn't be to start at the head, it would be to start at the tail and go this way. Okay, and that's going to be the difference when we use a doubly linked list, is we can use this efficiency. Okay, so let's bring this, so let's bring back our code here, and we are going to optimize this. So this for loop we only want to use this if we are in the first half of the list, because this just moves forward. Okay, so by going next, so we are going to wrap this with an if statement that says if the index is less than the length divided 2, in other words it is in the first half of the list, then we will use that for loop. Else we want to create a different for loop that goes the other way. The first thing we have to do is say temp equals this dot tail, and that's going to do this and move temp to the other end of our linked list. Okay, then we are going to have a for loop that is just the opposite of the one above. So we are going to start this with I being equal to the index of the last item in the list, and we are going to say while I is greater than index instead of less than, and then we are going to decrement. Okay, and then we are going to go the other way and use the previous arrows instead of the next arrows. Okay, so that is all of our code for get. Okay, so we will look at this in a moment in the dev tool, and we will create this linked list as an example. So we are going to run this get on the index of 1, which should return the node with a value of 1, and then we will run it on the index of 2, which will return the node with the value of 2. That way we can see if our method works if our node is in the first half, and then see if it is in the when our node is in the second half of the list. Okay, so let's flip over to dev tools. There is our get method, and this is where we create our linked list that goes 0 through 3. I'm going to run this. Okay, then I'm going to say my doubly linked list this dot get with a value of 2, and that works. It returns the 2 node. Okay, and then let's try this with the value of 1. It returns the 1 node. Okay, and that is our method for get. Okay, so now let's do our set method. Okay, and what we are going to do with this is we are just going to go a particular index and set the value of the node at that index equal to the value that we pass to the set method. Okay, so if you are going to code this, go ahead and pause the video, otherwise I will start coding this out. Okay, so just like we did with our singly linked list, we are going to say let temp equal this dot get, and then pass get the index that we pass to set. Okay, and let's say we are going to have that index be equal to, that's going to point temp to the index of 2, and we are going to let the get method for us here. So there is a couple of options here. Temp can either be pointing to a node when we do this, or it could be that we pass it at an index, say like the index of 4. That's not a valid index. Okay, so and in that case get is going to return undefined. So we have to determine, did the get method return undefined? Okay, or is it equal to a node? Okay, so we are going to use this if statement, if temp, which means it is pointing to a node, it is not null. Okay, temp dot value equals to value, okay, the value that we pass to the set method. Okay, and let's say that value was 99. That's going to change the value of this node to 99. Okay, and then we will just return true that we were able to change that value. Okay, otherwise we are going to return false here. Now this is exactly the same code that we used in a singly linked list. Okay, exactly the same, but the difference here is the get method that we are calling is written in a different way and doubly linked list than it is with the singly linked list. Okay, when we call this get method, if the item we are looking for is in the second half of the list, we are going to start at the tail and works backward, which is going to be more efficient. So even though the code is the same here, this is going to run in a more efficient manner than it would if it is a singly linked list. Okay, but the actual code that we are writing looks exactly the same. So let's look it in the dev tools here, and we are going to take this doubly linked list as an example here. Okay, then we will change the value at the index of 2 to 99. Okay, to 99 here. Okay, so let's go to the dev tools and let's take a look at this. Okay, so there is our set method. Okay, and this is where we create our linked list with the values of 0, 1 and 2, and I'm just going to run this. Okay, so open this, and you can see head is equal to 0, tail is equal to 2 with a length of 3. I'm going to clear this. So I'm going to run set at the index of 2 with a value of 99. We get true. Now let's look at our linked list, and tail is now equal to 99 here. Okay, so that is what you can do here. Now I'm going to run this one more time, except instead of having the index of 2, I am going to do an index of 10, because that is not a valid index and it will return false. Okay, so that is our method set. Okay, so now let's talk about insert method. Okay, we are just going to insert a new node at a particular value at a particular index. Okay, so if you are just going to code this, go ahead and pause the video. Otherwise, we will get into this. So a lot of the concepts we are going to same as with the singly linked list. Okay, I am going to bring up the new node here. And remember, if we were going to put this in at the index of 0, we were going to use the unshift. Okay, unshift method like this. The index is equal to 0. Return this dot unshift. Remember, you have to use the that return keyword. Okay. Or we can add this to the other end of the linked list like this, which is equivalent to just doing a push, and also need to use return. It is also possible for their index to be at out of range of possible indexes, right? So let's look at these 3 of line of code there. These are going to be the same with a singly linked list or a doubly linked list. Okay. The difference being that the unshift method here is going to be a different unshift method, right? This will be a different push method, and of course this line will run the same either way. Let's bring back our linked list here. Let's say we want to insert this somewhere in the middle. We are going to insert this at the index of the 2 like that. In order to do that, we are going to have a couple of variables. We will call these before and after. So let's go ahead and write that code for creating this new node and these 2 variables. So there is our code for the new node, and for the 2 variables, for before we will say before equals this dot get of the index where we are inserting it -1. And then for after, instead of using the get method, because remember get is going to be an O of n operation, it is going to have to iterate through the list to get to the particular index. With this we will set after equal to before. Okay, and that it will be O of 1, operation O of 1. Okay, so and then we are going to move a couple of arrows there. We are going to take that arrow from the 3 node. Instead of having it point to 23, we are going to have it point down here, and then we will have this line of code, and then we will have that the arrow from the new node here to the 23 node with this line of code right here. Okay, and that adds that end of the linked list, and this is going to be very similar when we do a doubly linked list. So this is our code. Okay, we have created those variables and then redirected those 2 arrows. Now just we need to increase the length by 1 and return true that we were able to insert one. Okay, so this is for a singly linked list. There are just going to be a couple of changes for a doubly linked list. Let's bring this up and turn this into a doubly linked list. Okay, like this. So one of the things we did before is we pointed this arrow down here with this line of code. We have already written this and this arrow here pointed up to the 23 node. We have already written this one as well. The only difference is we have these two arrows that I just highlighted in green, and we need to redirect these ones like this. So with the help of this code I can do this, okay, and with the help of this code I can do this here, okay. And I'm going to leave these previous pointers like this, and now let's look all of this code together with the rest of our code. So I'm going to bring up a couple of orange arrows in here. These are the ones we use here that are representing our orange keys. Orange arrows are representing orange operations, and green code is representing green arrows here, okay. So this is what you can do here, and that is how you can insert something, okay. So we will look at it in dev tools there, and this is what we will take as an example with 1 and 3, and we are going to insert a node at the index of 1 with the value of 2, just like that, okay. So the new linked list will be 1 2 3. Let's see here. So this is our insert method, and let's scroll down here, and this is our linked list with a value of 1 and 3, okay. So let's zoom out here. I will run this and just open this one, and you can see we have a linked list with a head equal to 1, tail is equals to 3 with a length of 2, okay. Let's clear this, and now I am going to run my doubly linked list dot insert method, and at the index of 1 with a value of 2. So it is returning true, it returns true. So if you type your linked list again, then now you will see here that we have a length of 3, and head is pointing to 1, that is pointing to 2, and that node, when we open this verb, you can see that one in front of it next has a value of 3, and previous has a value of 1, okay. So I'm going to clear this, and the other thing I want to do is I'm going to insert this at an index of 10, which is not a valid index, so it will return false here, okay. So that is our method insert. And for our last method for doubly linked list, we are going to do remove, okay. So for this we are just going to remove a node at a particular index and return it. So that's a pretty simple concept, okay. If you want to code this, pause the video and do it, otherwise let's get into it, okay. So just like with a regular linked list, we saw that if we remove the first item, we could see if the index is 0, we will just return this dot shift, and if we are going to return the last item, remove the last item, we could just say return this dot pop, okay. And then of course we can't have anything that is not a valid index, okay. So anything that is less than 0 or anything that is greater than or equal to this dot length, okay, that is invalid. So we will just return undefined, and let's look at this. So far this is our code, okay. And if it is not one of these, say we are going to return this one at the index of 2, we could set a variable equal to that node, and what we saw before is we had a before variable. So before the item we were actually going to remove, okay, and that was because all of our arrows were pointing forwards, but because we have arrows going the other way, we don't need that variable, okay. And I want to show you something a little bit different here with what we can do with these variables. First we need to declare the variable like this, and we are going to get that variable to the appropriate node using the get method, okay. Now let's look at this with the rest of our code like this. Now we will bring back our linked list like that, and since this is the one we are going to remove, I am just going to push it up here like this. So what we need to do is we need to have the arrow that goes from the 3 to the 23. See this one, highlighted in green there, and point that to the 7 node, right? That is what we want to do. Then we need the one that's going from the 7 to the 23 that I have highlighted and there, and I have that point over there. Okay, in order to do that, watch what we are going to do. We will say temp.previous dot next is equal to temp dot next. See, if you see here, like this, like that, and you will point that to that node. Similarly, we can say temp dot next dot previous, see this one, is equal to temp dot previous. This is the one, like that, and that will move that arrow down. Okay, the only thing we need to do now is the temp dot next and temp dot previous are both equal to null, and that will break data of the list here, like that. So let's put this in with the rest of our code like that. The only thing here left to do is to decrement the length and return that item that we removed. So let's look this in the dev tool, and this is the linked list that we will take as an example here. Okay, and we will try to remove the item at the index 1, okay, which has the value of 1. Okay, so it will return the node with the value of 1, like that. Okay, like that. Then we will left with a list where head points to 0, tail points to 2, and has a length of 2. So come here, and so there is our remove method, and I'm going to scroll up a little bit, and this is where we create our list with 0, 1, 2. Okay, let's zoom out here and run this. So I'm going to open this, and you can see that head points to 0, tail points to 2, and the length is 3. So I'm going to clear this and run the remove method. So it returns the node with the value of 1. Now let's look at the linked list, and I will open this up, and head points to 0, tail points to 2, and it has a length of 2. Okay, so that is our method for remove. Okay, so now let's start stacks and queues. So in this stacks and queues section that we are doing now, there is going to be a lot of borrowing from the linked list section. Okay, we will be able to reuse a lot of code. So this section is relatively easy if you have already gone through the linked list section. So what is a stack? Now my favorite analogy for stack is a can of tennis balls. So let's remove the balls and add them one at a time. When we add something to a stack, we say that we are pushing an item onto the stack. That is a terminology, okay? And if we remove it, that is called popping an item from a stack. So let's say this is tennis ball number 1, and then we push another tennis ball onto the stack. At this point, you can't get tennis ball 1 out without removing tennis ball 2. You can only remove the top item. Let's say we push another item onto the stack. Now the only tennis ball that can be removed is this one. This is called LIFO. Okay, last in, first out. Okay, so let's remove that top one, and we would say that we are going to pop that from the stack. Now we can remove the second one, and because we have removed that one, now we can remove the last one. So now let me give you an example that we would use in computing. Let's say you are surfing the web and you go to Facebook, and then you go to YouTube, and then you go to Instagram, then you check your email. That what we have created over there on the right is a stack, and when you hit the back button, you are popping that top item from this stack to go back to Instagram, okay, then to YouTube, then to Facebook. They are all kind of examples of where we use stacks in computing. And one of the ones that we are going to look at in some details later in this course is going to be a call stack. So a very common way of implementing a stack is to use an array. Okay. And remember, with a stack we are just going to add and remove from the same end. Okay. It doesn't matter which end that is, as long as it is the same end. Okay. So we are not going to use an array in this course because it is already included in JavaScript. Okay, I have already taught that in JavaScript, and that would be just too easy. So we want to do something where we are going to write some code, but I do want to talk about this a little bit, because if this comes up in an interview and they ask you how would you implement a stack with an array, it does matter which end you use. So when you add something to the end of the array or you remove it, remember this is O of 1 operation. Whereas if you do it on the other end, remember you have to index everything to take that off, and then re-index everything again to bring that item back. That is O of n operation. So if you are going to do a stack with an array, always do it on the end, not the beginning. And then you can just think about the stack like this. Okay. Also, an easy way to remember this is with the stack, you pop something from the stack or you push something onto the stack, and that's exactly what those two things are called with an array. Now, like I said, we are not going to use an array, we are going to use a linked list. Okay, now we are going to alter this a little bit to turn this into a stack. But unlike an array, when you create a stack with a linked list, you are always going to use the left side of the linked list as the top. Okay, in other words, the null terminated end is going to be at the bottom. You never want to do it like this, where the null terminated end is at the top. Now just turn it back into a regular linked list and look at why when you remove an item when you remove an item from a link list on the end, it is O of n operation. Why it is? If you add it back, that is O of 1 operation. Okay, so now on the other end it is O of 1 and O of 1 here. Okay, and to remove and add, it is O of 1. Okay, now like I mentioned, it doesn't matter which end you use as long as it is the same end. So for a linked list, this is the better end for adding and removing because they are both O of 1. So that's why our stack, if we use like a linked list, is always going to look like this. Okay, when we created our linked list, we had a method that we created to remove the first item called unshift, or to add something in as the first item called shift. So we can use those for creating methods for pop and push with some alteration. Also with the linked list, we had a head and tail. We will rename these for stack as top and bottom, and we actually don't even need bottom, so we will remove that. So our stack is going to look like this. Okay, so that is our overview on stacks. Okay, so now we are going to build our constructor for our stack. So just like with the linked list, our first step is that we need to create a node, and the node looks like this for the stack, which is identical to what the node look like for a linked list. Okay, and that means that our node class and the constructor in that class doesn't need any changes to it. Okay, this is identical to the node class that we used in a linked list because that is essentially what we are using here. It is just a modified linked list. Now we are going to see what else we can take from the linked list class. So I am going to start this out by saying class linked list because we can just take that out of the linked list class, but we would want to rename this to stack. So now let's see what we can take from the constructor from the linked list and what we can leave the same and what needs to be changed. So here is our constructor, and the first thing we had to do in our linked list constructor is the same thing that we need to do here. We need to create a node. So up to this point, the only change that we have made is changing the name of the class from linked list to stack, right? So just like with the linked list, up to this point we have created a node in the linked list. Okay, then the next thing we had was head and tail equal to the node like that. right? But we don't call them head and tail in a stack. So I'm going to remove these, and we would call them top and bottom. I'm not going to use bottom, so I'm just going to go ahead and remove this, and we will just use top. And then I'm going to say the length is equal to 1, and you could say height, but I'm just going to leave it at length. The one other change that I will make is that icon for the 11 that we have on the lower right should point down instead of across. Okay, and there we have our no code for a constructor for stack, and there was a lot that we were able to reuse from the linked list constructor. Okay, now let's go over to DevTools and run this code. So this is where we create our new stack called my stack, and then the stack class of course is calling the node class to create that first node. Now let's just go over here and run this, and then I'm just going to type in my stack and press enter. Then there is our stack. Okay, we have a stack where the top points to a node, length is 1. Okay, if you open this up, and the top is pointing to a node with a value of 11 where next is null. So it looks like we have created a working constructor. Now we are going to create our push method for our stack. So it's going to look like this. We have that new node up there with the 11, and we are going to push that on. We are going to move top up to point at that, and remember that this looks an awful lot like an unshift from a linked list, so we can borrow from that. So we had unshift, we will replace this with push. So not to be confused with the push method for the linked list that happens at the other end of the linked list. We are renaming unshift to push because this is a stack, and just like unshift with a linked list, our first step with push is going to be to create a new node. Once we create that new node, we need to figure out what kind of stack are we pushing this onto. Is it a stack that has any items in it, or is it any empty stack? Because those are going to be two different situations that we are going to have to code for. So then we are going to say if this dot length equals 0, in other words we have an empty stack. In the linked list, we said this head and tail was equal to new node. Here we are going to say that this dot top equals new node, which does this and would give us our first item in the stack. So the other scenario is that we are pushing this onto a stack that already has items in it. So we are going to say else new node dot next equals this dot top new node dot next. So let's look at that. New node dot next equals this dot top. Okay, and that's add that in there. Then we say this dot top equals new node, so which moves this up here. Okay, and now we have added that onto the stack. Now couple of steps left out. We are going to increase the length by 1, and then we are going to return this with this being the entire stack because the push method is part of that stack class. Okay, so now let's just go over to DevTools and look at this code. So there is our push method here. This is the push method, and if you scroll up, this is our constructor stack class that we have created. Okay, here we have done down here is where we said let's my stack equal new stack with the number 7, and then push down on the 23, 3 and 11 is we have created this stack here. See, this is the stack we have created. Okay, and then we pushed on the 23, the 3 and the 11. Okay, now let's run this. Then we will come down to the console here, and I'm going to type in my stack and press enter. And you can see we have a stack with a top that is pointing to a node. Length is equal to 4, and we will open this up, and top is pointing to a node with a value of 11, and next for that node is pointing to another node. So if you open this up, we can see that the next item has a value of 3, which is exactly what we had in our stack. Over here we have 11 point to 3. We go back, and you can of course keep expanding this out and look at all the rest of them, and that is our method for push. Okay, so now we are going to build our pop method for our stack. Okay, so it is going to look something like this. We are going to pop that 11 node of the top and then move top down to the next item in the stack, which is 3, and then 3 will become the top of the stack. So let's start coding this. So the first thing we are going to have to determine is, does this stack have items in it like this, or is it an empty stack like this, because you can't pop anything off an empty stack. Okay, so we are just going to say if this dot length is equal to 0, then we are going to return undefined. Then we are going to need a variable to point to the item that we are going to return. So we will say let temp dot equal this dot top. That's going to look like this. We are going to have the temp variable point to the node that we are going to return. Then we are going to say this dot top equals this dot top dot next, which will look like this. This dot top equals this dot top like that dot next, and that moves top down to point at the 3 node. Okay, we say temp dot next equals null. So let's look at that. So temp dot next equals null, see, like this, and that breaks that off from the rest of the stack. Then we are going to decrement the length by 1, and we are going to return temp here. And when we return temp, we are just returning this node that we popped from the stack. So there is our code, and let's look at this in DevTools. So there is our pop method, and then down here we have created a stack with 7, 23, 3 and 11. So if we go back over here, that is created this stack. Okay, now I want to run pop from the command line, which should return this node. Okay, so let's go back over here. Now I'm going to come down to the command line, and I'm going to type in my stack dot pop, and I'm going to press enter, and there is 11th node. Now the next node that was in the stack was a 3 node. So if we just type in my stack, this will return the remainder of the stack. So if we press enter, you will see your answer, and the top item should be the number 3. Top item is number 3, and you can see here that the top node has a value of 3. So looks like we have a working method for pop. Okay, so now let's look at queues here. Okay, so queue is just like when you get on a line, and when you get on the line, this is called in queue, and you can queue somebody behind them, and when you remove somebody from the line, that is called dequeue. It is FIFO, first in first out. Okay, and we can in queue a couple of more, then we can dequeue them as well. Okay, see, like this. And now let's look at a couple of data structures that we could use for a queue. We will start with the array. So remember, with arrays, to pop or to push, it is O of 1 to shift, or unshift is O of n. Okay, so with the queue, you need to add at one end and remove from the other end. So it doesn't matter which end you use for adding or removing, so long as they are opposite ends. Okay, for those two purposes. Okay, so let's look at an array. We could say we are going to add from this end, that's O of n, and remove from this end, that is O of 1. Or we could do it the other way around, add from this end or remove from this end, O of n. There is no way to get around having one of the one of these be of O of n. Okay, let's compare this to a linked list. So with the linked list, when you pop an item from the end like this, it is O of n operation. But to push it, it is O of 1 operation. On the other hand, if you shift O of 1 and if you unshift, it is O of 1. So what you don't want to do with a linked list is dequeue from this end, because that is O of n. What you want to do is in from this end, okay, and they are both O of 1. Okay, with the linked list we call these head and tail for the queue. Okay, so I'm just going to change the name to first and last. So what we are going to do is we are going to start with a linked list and modify it to build our queues. Okay, so now we are going to create our constructor for our queue, except our queue is going to look like this. So the first thing we have to do with our constructor is to be able to create a node, and our node is going to be identical to a linked list node value. Okay, and next, so our constructor for nodes in a queue will be identical to what we used in a linked list, and there are going to be other similarities to a linked list. Let's start out with a linked list class like this. We can borrow from this, but instead of calling this linked list, we can call it queue. So let's start building out the constructor here. The first thing we need is to create a node, and then the next thing is the linked list class is we said head and tail equal to the new node that we just created. But in the queue I am simply going to call them first and last. Okay, and we will say the length is now 1. So we will look at this in a moment in DevTools, and we will create a node with a value of 4. Okay, so let's flip over to DevTools. Okay, so there is our we created our code that's look identical to linked list, and in our constructor we have, instead of having head and tail, we have first and last. So now let's try to run this one. Now if you expand this one, and there is our node with a value of 4, and that is our queue constructor. Now let's build our enqueue method. So enqueue is when we add someone to the line. Okay, and except our line is going to look like this, and we are going to add that 7 node like this into our queue. Now that's what it's going to look like if we have one or more item in our queue, but if we don't have any item, we are going to set first and last equal to that new node. Okay, and as we have discussed, we are going to be able to borrow heavily from the push method from the linked list. So if you want to code this, you can start by looking at the push method to get an idea of what you are going to do here. The best thing to do is to try to code this from scratch. So I'm going to go ahead and get into the code here. First thing I'm going to do is I'm going to change this from being push to enqueue. Okay, and the first thing we will do in this method is to create a node like this. Okay, and if the length is equal to 0, in other words we have an empty queue, we are going to set first and last equal to the new node. So that would be a queue look like that, like this. Okay, first and last point to that node. Otherwise, else, okay, that is if we have one or more items, then we will have these 2 lines of code. Okay, let's focus on this one. So the first one, this dot last dot next equal to new node, we will do that, see, like that. And this dot last equal to new node, we will point that last pointer over to the new node. Okay, and that adds that into the queue. Let's put this back into our rest of our code, and we will increase the length by 1, and we will return the entire queue here. Okay, so that is all of our code for this. We will look at this in the dev tool, And when we do, we will create this queue as an example, and we will add 7. We will enqueue this 7 node into our queue. Okay, and we have to make sure that the last is pointing to the value of 7. So that is dev tool, and this is our code enqueue method, and this is our queue that we are going to build 11 3 23. And if you run this one, you have your queue. Okay, and you can open this up to take a quick look. First is pointing to 11, last is pointing to 23. Let's clear this. Then I will say my queue.enqueue 7. So now you have, if you expand this one, now you can see that the last is pointing to value of 7. Okay, that is what you can do here. Okay, so that is, we have our method for enqueue. Okay, so now we are going to write our dequeue method. So dequeue is just going to remove that first item in the line. Okay, and this is very similar to shift with a linked list. And remember, with shift we had an edge case for if we had one node in our linked list. Okay, same is going to apply to queue, and then we have to return undefined if there aren't any items in the list at all. So like I mentioned, it's like the shift method, and you can copy a lot out of this. Once again, I will recommend that you try to write this from scratch. Okay, and the first thing that you would do if you do that is you will change the name to dequeue, change the name of the function dequeue. And as always, we are going to remove something from a data structure. So if it is empty, then you are going to return undefined. Otherwise, we will need a variable to point at the item that we are going to return. So let's say temp is equal to this dot first, like temp, like this. Okay, and if this dot length equals to 1, we will have first and last equal to null. So if this is a situation where you have one item, you will remove it. Okay, we will set first and last equal to null. Okay, otherwise this dot first equals to this dot first dot next, that moves here from here. Okay, and then temp dot next equals to null. So that is temp dot next equals null. Okay, then decrement the length and return the temp. Okay, so that's this node here. Okay, where that is what we will return here. Okay, so we should get the number 11 back here. So we will look at this code in the dev tools, and this is what we will take as an example here. Okay, this is the queue 11 3, and we will remove this 11 node. Okay, so 11 should be returned when we remove this one. Okay, and the first should be pointing to the node with a value of 3. Let's see here. So this is our dequeue method, and this creates our queue with the value 11 3 23 and 7. Now if you run this one, so you will get this one here. Okay, and the first node, that's the one we are going to dequeue, has the value of 11. Let's clear this, and if you run dequeue method, and it returns 11 node. Okay, node 11. Now if you print your my queue again, and we will open this, and now the first node is pointing to 3. Okay, so that is our method for dequeue. Okay, now let's talk about trees. So it is a very good data structure. Okay, so what is a tree? We have already seen a tree, and that is a linked list. A linked list is actually a form of a tree. Okay, it is just a tree that doesn't fork. Okay, so we can use this node here as our starting point for creating a node for a tree. So remember, it looked like this. We had value and next. Okay, Now we are going to turn this into a binary tree node. So I'm going to change the color to blue since we are moving on to a new data structure. Okay, and a binary tree is going to have two arrows. So this is going to look like this: value, left and right. So it's not all that much different than what we created for a linked list. We have left and right instead of next. Okay. And bring in a couple of nodes for that to print like this. Okay, so it will look something like this. It is not that much different than what we have in the linked list. We just have a left and right instead of just having next. Okay. And there is no rule that a tree has to be binary. There is no rule. Okay, it can have 3 items or it can have 10 items, as many as you want. But what we are creating here, because we only have left and right, it is by definition a binary tree. Okay, then of course each of these two nodes that we added can point to more nodes. So it's look a little like this. Okay, so you can say it is a full tree. You can say it is a full tree. A full tree is a tree in which every item has 2 nodes or 0 nodes. Okay, so if we add a node here at the bottom, this is no longer a full tree. Okay, we remove it. Now it is a full tree. Okay, then I'm going to remove these 2 nodes. Now this is still full because everything is pointing at either 0 or 2 items. But it is also a perfect tree as well. A perfect tree means every line that has items in it. Okay, it is completely filled all the way across. So this is also perfect. This is also perfect here. Okay, but if we remove this couple of these ones, it is still full, but it is not perfect. Okay, let's bring those back. So we have our tree full and perfect. It is also one more thing, and I explain this one last because it's easier to explain with an example. Okay, it is also a complete tree. So if we add an item here at the bottom, this is still complete. And if we keep adding items across that row, it remains complete. So basically it's as compact as you can make it given the number of nodes that you have. Okay, but it is no longer full because you have something pointing at one item. Okay, so and the entire line is not filled up, so it is not perfect. Okay, and if you fill all of these, so it is full, perfect and complete. Okay, so a perfect tree will always be full. It will always be complete. Okay, so let's move this over now, remove some of these nodes, and we will look at a bit more terminology here. So this top item here is parent node. This is called child node, which are children. Okay, these two children, because they have same parent, they are also called siblings. Okay, every child node has one and only one parent. Okay, you can't have more than one parent in a tree, so you will never see something like this and have it be a valid tree, because that 4 node, you can't have 2 nodes. Okay, so like this. So these two child nodes can also be parents of these nodes, and these are children of the 3 and 23. So with this bottom line of nodes, they don't have any children, and a node that doesn't have any children is called leaf node. These are leaf nodes. Okay, and that is our intro on trees. Now we are going to talk about a specific type of binary tree called a binary search tree. Binary search tree. Okay, so what we saw in here, we created a binary tree, but it was not a binary search tree. Okay, so the best way to explain them is to just build one out and show how we build this. Okay, so let's say we have a tree that only has one item in at the top, and then we are going to add an item to the tree. Okay, we are going to add this node down here. So with a binary search tree, if this new node at the bottom, the 76 node, if it is greater than 47, it is going to right. If it is less than, it is going to go on left. And of course 76 is greater, so we are going to put it on the right. Now let's add another node. So when we add the next node, we are also going to compare it against the top node. Okay, 52 is greater than 47, so we are going to go to the right. But because there is an item there too, the 76 node, we now have to compare with 76 as well. 76 as well. And when the node is less than 76, we go left. Okay, like this. So let's add one more. Okay, few more. 21. It is. Let's compare with top 47. It is less than 47. So we will write it here. Okay, and then 82. And 82 is greater than 47. Compare with 47, it is, and then 76. So greater than 76 as well. So it will be on 82, right hand side. Okay. 18 is less than 47. We go left. It is also less than 21. We go left again. Okay. So like this. Then 27. Compare with 47. We go left. Okay. 21. It is greater than 21. So we go right of 21. Okay. Which is here. Okay. Like this. So one of the things I want to point out here is that all of the items to the right of the 47 are greater than 47. All of the items to the left are less than. And also if you look at the 21, everything to the left of 21 is going to be less than, and everything to the right is going to be greater than, no matter how many big this tree will get. And that is your binary search tree. Okay, so now let's look at binary search tree big O. So I'm going to bring up a node here and we are going to do some math here. Okay, it's very simple math here. You could say that this is one node, or this is also 2 to the power 1 minus 1. Okay, which is equals to 1. Okay. Okay, you will see why I'm doing this in a second. Because when we build this out to another level, this is 2 to the power 2 node minus 1. So 4 minus 1 is 3. Okay, 3 nodes there. Then 2 to the power 3 minus 1, 2 to the power 4 minus 1. Okay, you can see as it grows, become 2 to the power 10 or 2 to the power 20. Minus 1 is irrelevant. So I'm just going to remove this and we will say this is approximately 2 to the power 4, 4 nodes and something like this, and 2 to the power 1 node. Okay. So if we are going to find something in this tree with just one node, it would take one step, only one step. If we are going to find something in this tree, let's say we are going to find the number 76, then it would take 2 steps. If we are going to find in 27, it is going to take 1 to 3 steps. And in this one, it will take 4 steps. If you try to find 49, here, okay. So that is to find the item. If we are going to remove the item, you would have to iterate through the tree, get to that item and remove it. Okay. It will also take 4 steps. If you are going to add something below the number 49, okay, it will still take 4 steps. Okay. It doesn't matter if you are finding, removing, inserting. This is all going to be 4 steps. So you can call this O of log n. Now this is our best possible scenario. That's not an O, but I'm just going to put this out here. Say roughly speaking, it is O of log n. And remember, O of log n is very efficient, very efficient. Okay. And the term that we used with O of log n was divide and conquer. So I'm going to show you the divide and conquer aspect of a tree. If we are going to find the number 49 and we start at the 47 and move to the right because it is more than 47 to the 76, everything that's to the left of the 76 we are not going to have to look at. We do not have to iterate through, we can completely ignore it. See, like this. Okay. We have cut the tree in half. And when we move down one level again, we are going to do that again. Okay, we are going to do that again until we finally get to the item that we are looking for. Okay, so the vast majority of the items in the tree we didn't even have to look at, and that's what makes it so efficient. Okay, so this is our original tree, and like I said, that this is our best possible scenario, which would be omega. Okay, now we are more likely to see something like this. This would be theta. But we could say that this operates like a log n. But this is not our worst possible scenario. Now our worst possible scenario is like this. Let's say we have a node and the next node is larger than that one, and the next one is larger than that, and the next one is larger than that, and it just never forks. Okay, so you never get that advantage of divide and conquer when you go to find something. It is just operating in a straight line. It is just operating in a straight line, and we have seen in a data structure like that looks like this. It is a linked list. And if you are going to find that 91 node in a linked list, you would have to iterate through the entire list, that is O of n. Well, if you have a binary search tree that looks like this, you are going to find the 91 node. You have to iterate 1, 2, 3, 4 through the list to get to that node. Okay, there are 4 items and it took you 4 steps. That is O of n. That is O of n. And since big O is a measure of your worst possible scenario, technically the big O of a binary search tree is O of n. Okay. Our best possible scenario is O of log n, and since we are probably going to be somewhere in the middle, we treat this as if it is an O of log n data structure. O of log n data structure. Okay. So for lookup, insert and remove, this is effectively O of log n operation. Okay, now let's compare these 3 to a linked list. First we will start with lookup. If we are going to look for the number 91 in this linked list, you would have to iterate through the linked list, that is O of n. And this is going to be closer to log n with a binary search tree. So the advantage goes to the binary search tree. What about if we are going to remove? Same thing, if we are going to remove the node with a value of 91, we have to iterate through the entire linked list. Like that. So that is O of n. And that's a O of n binary search tree. It is going to be log n. For binary search tree, it is going to be log n. Now if we are going to insert an item, see, there is no advantage with a linked list of keeping the list in order because you are still going to iterate through the list when you go to look for something. So you are just putting at an end, and that is O of 1 operation. So this advantage goes to the linked list. This time it goes to linked list. Okay, so let's just look at all of these like this. So insert is better for a linked list because it is O of 1 to put something at the end. Lookup is going to be better for a binary search tree as well as for remove as well. Okay, for remove as well. You are giving up some efficiencies putting the items into the tree to make it faster to look up items later. And the same goes for an array, because an array it is O of 1 operation to add something, and if you are going to look up by value, that is O of n, just like a linked list. So that is our overview for binary search tree, big O. Okay, so now let's build our constructor for our binary search tree. Okay, so we have a node that is going to look like this, which look like this. Okay, so this is going to be the constructor for the node. So instead of having value and next like we did in the linked list, we have value left and right. So now let's start with our binary search tree class and the constructor. Okay, now let's just focus in on the constructor code here like this, and as we have seen before, the first step is to create a new node, and then we are going to pass the node class this value just like that. So I'm going to show this in a tree like this, and so far we just have one node, we don't have the rest of them because these are objects. They all need to have something pointing to them, or they get garbage collected and everything does have some pointing to it except that top node. This is why in a linked list like this we had pointing to that first node. Okay, similarly in the binary search tree we have to have something pointing to that top node, and we are going to call that root. So we need to look like this, root pointing to that first item, right? Something like this. Okay, so this dot root equals to new node, and since we don't keep track of the length in a binary search tree, this is all we need to do. So this is a working constructor, but I am going to completely rewrite this. Okay, let's take a look at what we have done here. We have root, but we also created the first node at the time that we created the binary search tree. Okay, you don't have to do that. You don't have to create this with a node. You could just start by saying root and null. Root is null. You just create the framework for a binary search tree, and the first node that you insert into it, you do it with the insert method, and I am going to bring the code back and change it to make it where we don't add a new node at the time that we create the tree. So line by line we will go through and change this. First, we are not going to need to pass this a value because we are not creating a node at the time that we create the tree. So we can remove this. The entire line here is just to create the node. We can remove that. And this line, this dot root equal to new node, while we are not going to create that node, so we can remove that and just say this dot root equals null. Okay, and that becomes the entire constructor. So let's bring back the rest of our code, and now let's look at this code in DevTools. So okay, so there is our node constructor and our binary search tree constructor. Okay, and that will just create a new tree, and I will run this. And now when we open this, all we have is a root equal to null. Okay, so that is our binary search tree constructor. Okay, now let's talk about insert. Okay, so now this is a fairly complex method, insert method. Okay, so in this one, now first of all we are just going to walk through the steps that you would need to do to insert an item, and then we will actually write the code. So I'm going to bring up a tree here, and what we are going to do is we are going to insert a node with a value of 27 and that open spot to the right of the 21 there. And I'm going to try to replicate the process of walking through the logic that you would have to do to be able to code this. So normally you would sit down with a piece of paper and you would write out all the steps to kind of get an idea of what you need to do to code this, and then you start coding, and that's what we are going to do here. So the first thing we did here is we created a node. So I'm going to add that on the upper left hand corner here, create new node. Okay, and then we have more room for these nodes. I'm just going to move everything over to the right like this. And the next thing we are going to have to do is to take that 7 and compare it to this item here. And when we compare it, if it is less than, we are going to the left. If it is more than, then we are going to the right. So we add that to our nodes. If it is less than, we are going to go left. If it is greater than, we will go right. Now once we made the decision, in this case we will go to left, in this case we will go to left. Now there are a couple of possibilities. Either we can insert this because that spot is open, might be, or that spot is not open because there is already a node there, in which case we need to compare the new node to this node. So I will make another note here: if null, insert new node, else move to next. Okay, move to next node. Now we are going to compare the new node to this new node. We are going to say if it is less than, we go left, and if it is greater than, we go right. In this case it is to the right. Then we are going to say again, if it is null, insert the new node, which is what we have. So we are going to insert this. So the thing that should jump out at you here is that these two if statements were used at the very top, and then we move to the next node. That's an indication that these must be inside of a loop. They should be inside of a loop, and we don't know how many times we are going to loop through this. So it makes sense for this to be a while loop. Okay. So the other thing that you might notice is that we had an arrow pointing to this node here that started up here, and we are going to need to have a variable attached to that pointer, let's say temp. since that's what we've been using in all the other data structures as well. Okay, and then as you move through the tree, temp is just going to point to the next item that we are comparing the node to. Okay, so I will bring this up back to the top, and when we initialize this, we are going to have it set it equal to root. Okay, and that is going to have to happen before the while loop. So we can say write this, see like this, let temp equal this dot root. One of our other possibilities that 27 node, instead of being plugged into a tree that already has nodes in it, we could have a situation like this where the root is equal to null. That can also be a situation. Okay, in other words, an empty tree. In that situation, we just set root equals to the new node, and this is something that we would do before we would declare a variable to do that while loop. So you can do that here like this. And we do have one other situation, we have one other case. So I'm going to bring this down here, and I'm going to replace this 27 node with a 76, and you will see why here in a second. Let's bring the tree back. If you have 76, we are going to start at the 47, we are going to go to the right, and now we have a node that is equal to the node that's already in the tree, and you can see that everything we have done so far is either been greater than or less than. We never got the equals to. We cannot have a value that is equals to a value that is already in the tree. Now there is a way to get around this, and in the interview if they say what if we do want to have a duplicate values in the tree. So I'm just going to take a little tangent here, talk about that. I'm going to focus in on this node. Now remember, this node is like this. So what you can do is add something like count, and a count is 1 when you insert the first one, and if you insert another one, you could say the count for the number of 76 node that you have is 2. It's set to 2 here. We are not going to do that here. Okay, so I'm going to take that back out, and because we don't have something like that, we cannot have a duplicate. So let's put this back in here. Okay, like that, and you are having to compare the new node to each node that you are looking at to see if it is equal. So this is going to have to go inside the while loop. Okay, like this. You are going to say if this new node is equals to temp, you can return undefined. Okay, that is all the steps that we are going to have to do to code this out. Okay, so now we are going to code our insert method, and like I said, we are going to pick up from here. Okay, from here. Okay, so I'm just going to take these nodes and move them to the bottom and put the code in at the top. So first of all, we are going to start out with insert, and we are going to pass it a value, and then we are going to start working through our list. So first thing is to create a node. Okay, and that is our like this. Okay, we can remove this. Now we can the next thing, if root is equals to null, then root equals to null. Okay, so this is the situation where root is null. In other words, we have an empty tree, and we set root equals to the new node, and we do it like this. Now remember, we have to return in there, because if this is the case, we don't want to run any more code in here. Okay, so that is done. We can remove this one. Okay, we can remove this as well. Okay, now then we set our variable temp, and we don't need to make any changes to this. You can simply directly do it like this. Okay, then we go into our while loop. So for our while loop, we are going to say while true. So this is always going to be true. It keeps running unless it hits our return statements. That is how we will break out of this while loop. Okay, so that is here. Then we can say if the new node equals temp, return undefined. That is this situation where we are trying to insert a node in the that is in the same value as a node that we have in the tree. So we will do that like this, and we have to say dot value in this case because we are comparing the value new node dot value. Okay, and equals temp dot value, and as we are iterating through this tree, we are going to return undefined every time, okay, when this condition is true. Then we have this part. This is where it gets interesting. If it is less than, we will go left. If it is greater, then we go right. So we have to have an if statement that is going to start with one or the other. So if new node dot value is less than temp dot value, and what I'm going to do is, this is where we are going to have to build out a bit of a code here, and I'm going to focus on if this if statement, and let's ignore the rest of the code for now. Okay, so like this. Okay, and this other if statement here is really nested inside of this if statement. We are going to say if less than, we are go left, then we have to look up to see if that spot is open or not. Okay, so it is really a nested if statement. So now that we understand that, I'm going to remove this and we will just build out the code. So since we are starting out with the less than, in other words, we are going to go to the left. I'm going to start with a tree where everything is open to the left, and I'm going to bring in a new node, and I'm going to point temp to that 47 node. Now if you look at the if statement, we have new node dot value, and we are comparing this against temp dot value, which is 47, which means that we are going to left. So there are two options. Either the spot is open like that and we are done, or it is not open. So we are going to assume to begin with that this spot is open. That is what I'm assuming, and that is the condition here. We will say if temp dot left equal to null, which means that this is open. We are going to say temp dot left equals to new node, and return this and return this. Okay, this means the entire tree. This means entire tree. Okay, and we have a return statement here because once we insert this, our work is completed. We should be done running our code. Okay, now if that is not open like that, we are going to say temp equal temp dot left. See, like this, temp dot left, which moves temp down to the there, and we do the whole process again. So in this case, temp dot left does equal null, and we would put that right up there. Okay, so now I am going to move temp back up to the top, and we will write the code for doing something like this. Okay, and I am also going to just move that tree over here a little bit, so we have a little room to work. We are going to say else. This else would be if it is not on the left, it is on the right, and I'm just going to remove that 82 node from the tree there, and we can say what it's like to insert something where all of the decisions are going to go to the right, and it is going to be just the reverse of what we did above. So just like that above, either there is a node there like this, or there isn't. So the code is going to be very similar. We are just going to say if temp dot right equals to null, in that case it is null, so temp dot right equals to new node, and see like this, and return the entire tree here. Okay, something like this. Otherwise we have items here, and we can say temp equals to temp dot right, temp equals to temp dot right, temp dot right, which will do something like this here, and see like this, move temp down. Okay, so in this case we will run the while loop again, and then we will say temp dot right equals to null, and then finally place that there. Okay, so that is all the code for this method. Okay, so let's remove our tree like this, and now let's walk through what we are doing when we run through this code. We are going to say if the new node is less than the node that we are comparing it to. If it is less than, we are either going to insert this because the next might be open spot, or we are going to move to the left, which is going to causes us to run through the entire while loop again. Else it is greater than, and we are either going to insert this on the right, or we are going to have to move to the next node on the right and go through the entire while loop again. So let's take a look at this code with the rest of the code in the while loop. And remember, there was an if statement that we already put in there. Okay, I'm going to bring all of this here. So the top statement, if statement, was the situation where the new node was equal to something we already had in the tree. So now let's take this while loop and look at it with the rest of the code for this method. Okay, and that is our entire insert method. So we will look at this code in a moment in the dev tools, and for the example we will build this tree. Then we are going to insert a node with the value of 27 exactly right here. So when we insert this, we will be able to start at the head at 27, go to the left 21, then go to the right, and that node should be there. Okay, so let's come to DevTools and see, this is our insert method. And then if you scroll up here, this is our tree, and in this spot right here is where the 27 would have gone, and we will insert that separately here in a moment. Okay, just run your code. So this is our tree. Okay, now if you expand this one, if you expand this tree here, and you will be able to see we have start root 47, the root value is 47. If you open this, then left is 21, right is 76 as I shown you in the diagram. And you can see the one we opened 21, the left is 18, but right is null. That is the open spot where I want to add. So let's clear this, and 27, my tree dot insert 27, run this, and it has returned my entire tree here. Okay, expand this and expand, root is 47, and you can see to the left 21 node. If you open this one, now with inside 21, left is 18 and right is 27, and that is how our method insert works. Okay, so now let's build out our contains method. So I'm going to bring up a tree here, and I'm going to do the same thing I did with insert, where I write out all the steps and then we code it. Okay, so let's say that we are trying to find out if this tree contains the number 27. Okay, well, if we are looking for the number 27, we are going to start at the root. Okay, and either we are going to have a tree like this that we iterate through and see if it is not, or if there is null. Okay, so the first thing we will do is we will just say if root is equal to null, we are going to return false because that is not in the tree. So that will be our first step there. If root equals null, return false. Otherwise, we have a tree that we can go looking for the node. If the tree does have items, we are going to need a temp variable and say we are looking for the number 27. We are going to compare the number 27 to each node until we find one that is equal to temp. Okay, so we will like this, let temp equals to this dot root. So the other possibility is we are looking for a number that is not in the tree. So let's say we are looking for the number 17. We will go to the left, and that is not equal to 17. 18 is not equal to 17. Okay, we will go to left again. Now temp is null. So binary search tree are null terminated list. And as we are moving through this, we are already know that we are going to need a while loop, but now we are going to say while temp. So basically we are saying while temp is not equal to null, we are going to keep going, we are going to keep running this loop. If we hit null, we know that number is not in our tree. So inside the while loop, we can say if less than left, and if it is greater than right. If it is greater than, then we will go to right, and the third option is it could be equal to, in which case we would return true, that that item is in the tree. Okay, and if temp ever becomes equal to null, it breaks us out of this while loop and we will return false. Okay, so let's take these steps and build out our code. So now let's try to code here, and we will start building our contains method. We are going to pass it a value, the value that we are looking for. And step 1, if root equals null, return false. If root equals null, that is this situation where root is just a pointing to null. Okay, an empty tree. So we will say if this dot root equals to null, return false. Okay, now next, let temp equals to this dot root. So we can do it as it is. Okay, so let temp equals to this dot root. Likewise, while temp, we will do like this. We can just move that up here. Curly braces. Okay, now if it is less than, we are going to left. So if the value is less than temp dot value, I would say temp equals to temp dot left. So the value there, the value that you passed, that contains in the contains method, if it is less than temp value, then the item that temp is pointing to, we move to the left. Now see this one, if you have the value that you pass in the contains method, if it is less than temp, this temp, we are going to say temp equals to temp dot left and something like this. Okay, so like this. Okay, then the next thing is else if the value is greater than. So else if value is greater than temp dot value, okay, then you are going to say temp equals to temp dot right. Say like this. Okay, and that moves temp to the right. Okay, then the next thing, else if it is equal, we will return true, and that codes like that. Okay, now otherwise, if temp is ever equal to null, it will break us out of our while loop and we will return false, and we will move like this. Okay, so that is all the code for that method. Okay, so I want to walk through this code to make sure that it is clear what all this mean. So first of all, if you have an empty tree, we are going to return false, and let temp equals to this dot root. So this is going to set temp at the top. And now let's focus on rest of the code, the while loop. Okay, and we will walk through this one. So let's walk through with the help of an example. So we will have a tree. We are looking for 27. Let's say we are looking for 27. So temp is starting up there at the top, and we would say while temp, and temp is pointing to a node, so it is not null, so the loop will run. And this if statement, the value is less than temp dot value, so we will come here, we will say temp equals to temp dot left here. Then that will cause us to run the loop again. This time we are looking for number greater than. So else if value is greater than temp dot value, that is true, so temp equals to temp dot right. Okay, and which moves that down here. That is going to cause us to run the while loop again. Now if it is equal, we are going to return true. Let's take another scenario. So now this time let's say we are looking for number 17. While temp is less than, okay, value is less than temp dot value, so temp dot left. Now run the loop again it is less than, so we will come here, and it will run again, while loop will run again, and again it is less than 17 is less than 18, so we will go to next again, so left again, which is null. And this time your while loop will not run because temp value is null, so it breaks us out of the while loop, and then we are going to return false here. Okay, so let's bring the rest of the code back here. Now let's look at this in the dev tools, and we will take this as an example. Okay, and we will look for the number 27 just like we did here. It should return true. Then we will also look for the number 17 just like we did here as well, and that should return false. Okay, so let's come here, and this is our contains method here, and this is our binary search tree. Okay, exactly as was in the diagram, okay, that I just showed you. Now let's run this code and run this. This is our binary search tree. You have all of your values here. 47 is the root node. If you open all this, you will be able to get your data. So the first one I want to see is 27. Okay, so it is returning true. It is returning true here. Now if I search for 17, it is returning false. Okay, so it is working properly. So this is our contains method. This is our contains method. Okay, so now we are going to see that how can we find minimum value in our tree. Okay, so let's me show you what we are going to do here. Let's bring our tree, and what we want to do here is that we want to return the node that contains the minimum value in this tree. And obviously by looking at this, you can see that it is going to be the number 18, but how do we determine it? So we are going to start with the root, and then we are going to keep going left, and then we go left again, and then we are going to go to the left again one more time, and that is equals to null. And now we know that 18 is the minimum. We can pass 76 node, and then we can find the minimum value in the 76 node in this subtree here. Okay, so it is the same process here as well. Okay, and on the left hand side of 76 you have null, and that is equals to that is how you will know that 52 node is the node with the minimum value in that subtree. Okay, so you need to find value in subtree as well. Okay, so let's write our code here. I'm going to call this main value node, and then we are going to pass the same node, current node, but in our diagram I will call this current. Okay, this current. Now we are going to pass the variable name current node. Okay, and this will be our current node here. Okay, now we are going to iterate through this here. Okay, and we are going to say while current node dot left is not equals to null. See, that is our condition. Okay, and you can also write while current node dot left, because it will do the same thing. You can write a condition like this. So current node dot left is equal to a node. That means it is not null, right? So the while loop will run, and inside the while loop what I will do, current node equals to current node dot left. So current node and dot left will be transferred to current node, so this will be our current node. Okay, then we will run the loop again. We will run the loop if current node dot left is not equals to null, which is not true. So we will say current node dot left equals to current node. Okay, so this will become current node. But when you run the code again, now this time current node dot left is null. This time it is null. So this condition is true. Now this time while loop will stop, and we will return the current node. Okay, so now let's look at for our subtree. Let's look at for subtree. So if we have this subtree here, and this is 76 current node, and what we can do here, we can say, okay, so then you run this again while current node dot left is not equals to null. So this will run current node equals to current node dot left. If you check the condition again, this time the dot left is equal to null. That breaks us out of the loop, and we will return the current node. Okay, so that is all of our code for finding the minimum value. Okay, and we will see that in the dev tools, and when we do, we will take this as an example. Okay, and we will start off by passing 47 the root, and we will expect that to return 18 node, and then we will run it again, when we pass 76 node, which should return, okay, and which should return 52 node. Okay, so now let's come here and let's take a look at this. So this is our function method for min value node. Okay, and this is our tree. Okay, and 47 is the root. And as you can see here we are going min value node and my tree dot root. Okay, so the root element. So if you run this one, and you can see that this is returning the minimum node. See the minimum value 18. Now if I do, see very carefully, root dot right. So root dot right, and this is a subtree. This is for subtree, and see now you are getting 52 as an answer. So and that is how you can do for subtree as well. If you want to find the value in a subtree, you can do like this. Okay, so this is your method for minimum value. Okay, so now let's talk about hash tables. Okay, so there is actually a built-in hash table in JavaScript, and that is objects. Okay, but what we are going to do here is we are going to build our own hash table. So imagine that this is an address space, and this is actually just going to be an array that we build, and then we are going to put items into this array, but to do so using a hash. Okay, and what I am going to do is I am going to build an inventory for a hardware store. Okay, so the first item we are going to have in our hardware store is going to be nails 1000 quantity, and this would be key and this would be value. Okay, key value pair. Okay, so nails is key, 1000 is value, and when we are going to run this through a hash, it is only the key nails that get runs through the hash. So all letters have an ASCII numerical value, and it is just going to run those letters through a math equation and create a number. So we are going to put this into the hash generator, and we will get our object back, but it is going to do a calculation on that key nail and give us an address. Let's say the address is 2. That is where we will put that object. Okay, so that hash function is going to determine where we put that, but also when we go back to look this up, we will say where is nail in memory. We will run it through the same hash function, and we can go straight to the address in memory where that is being stored here. So it is very fast. So let's talk a little bit more about hashes. There are two characteristics that you need to know about hashes. First is they are one way. So if you take nail and you run it through the hash and it gives you the value of 2, what you cannot do is take the number 2 and have it produce nails. Okay, the string nails. Okay, it is one way only. Okay, the other thing about hashes is that they are deterministic. What that means is if you run nails through this equation and it produces the number 2, the next time you run nails, it will produce the number 2. It will always produce the same number. So these are the two important characteristics of a hash. So let's bring back our hash table. And when we build a method like set, this is going to put something into the hash table. We will have a key and a value. Let's say the key and value is nails and 1000. Okay, what we are going to run this to the hash, and it is going to give us this array that we are going to put into the array. That is our hash table over there, that is labeled 0 through 7. But it is also going to give us an address based on a calculation it does on that string nail, and it produces 2. So that array is going to go right here. And let's just add a couple more here. Let's say screws 800. Okay, and this is going to map to the address space of 6, for example. Okay, let's say 6. Then we have nuts 1200, and run it through the hash, and this give us an address space of 2. So that is going to go right there. but there is already something in that address space. So we don't just want to override the last thing in that address space. What we want to do is to be able to have both of them in here. This is what is called a collision, and there are multiple ways to dealing with this. And now we will talk in detail about how we deal with collisions later on. Okay, so let's just do one more. Let's say bolts 1400, and it will go to address 4. Okay, now we are going to do a different method. Get, we are going to pass that string bolts into our hash function. It is going to produce the value of 4, and we go directly to this address space. And what we want to do here is, when we are looking for bolts, we want to know the quantity and just have it return that value. Okay, but if we say something like nails, and when we run it through hash function, it is going to produce 2. When we go to here, we are going to have to go through the different arrays that are stored at that address space and find the one that is nails, and then returns that value. And we will talk about that in some detail in the get method, but for now that is our introduction for hash tables. Okay, so now we are going to look at couple of ways that we can handle collisions. So I'm just going to bring up our address space here and put some items into it. So a collision is when we have an item that maps to that same spot in memory. And I want to point out that these two arrays that we are putting in here, these key value pairs, are actually being stored at this address space like this within another array. Okay, so there is the array that's the address space, then there is the array that holds the key value pairs at that particular address. Okay, but I'm just going to show them like this. Okay, so this process of putting all of the key value pairs that map to a particular address in the same address space is called separate chaining. And separate chaining is what we are going to use in this course. But let's look at another approach. Okay, and let's say if there is already an item at this address space, go to the next one and see if it is open. If it is, put it there. Then if you have another item that maps to the same address space, we go to another to see if it is open. It is not. Then we go to next. It is not. Then we go to next and put it there. Okay, this is what is called linear probing. Okay, and it is a type of open addressing, and there are multiple ways of doing open addressing. There are all kinds of ways of dealing with collision in a hash table. Okay, the two most common are going to be linear probing and separate chaining. Okay, so let's remove them from here and put it back to separate chaining format like this. Okay, now this is what we are going to build in our hash table in this course. Okay, so I'm going to show another way of doing separate chaining here. Another way is to have a linked list at every one of these addresses, and then we just add to the linked list when we have multiple items that map to that address. Okay, so I am going to change this back to the way we are going to do this in this course, which is going to be separate chaining with a race, and that is a few ways of dealing with collision. Okay, so now we are going to build our constructor for our hash table. Okay, and in this section, in addition to the constructor, we are also going to build out our hash function as well. Okay, hash function as well. So I'm just going to bring up an address space like this, and I'm going to make a change to this because there is 0 through 7, there are 8 address spaces, and you get a more randomized distribution of the items that you add to your hash table, which is optimal if you have a prime number. So I'm going to remove that last item and just make this 0 through 6. So it is going to have 7 items in it, and then we can start building out our class for the hash table and beginning with a constructor. And if you haven't seen this before, this where you have an argument equal to a particular value, this is default if you don't pass it a value. Okay, so you could pass this the number 11 and it will give you an array with 11 items in it. But if you do not pass anything at all, it is going to give you an array with 7 items in it. Okay, so that next line there, this dot data dot map, okay, equal new array of that particular size. Okay, and that is all there is to the constructor. Okay, so now let's build out our hash function, and I'm just going to bring in the whole function and then we will walk through this. So here is the function. So let's take a look at the name here that has underscore. This tells us other developer that might be using your code that this is a method that should only be called by other methods. You should not be calling this directly. Okay, and then you pass it a key. So that is our key value pair. Let's say you have paint, you have 50 gallons. Paint is the key, 50 is the value. So you are going to pass it the string paint. In the next line here, we are going to declare a variable hash, set it to 0, and then we are going to have a for loop. So the way this for loop works and the key dot length, remember key was paint, dot length, it is 5 characters long. So this for loop is going to run 5 times. So we are going to set hash equals to hash plus this. And what this is, it is every letter that has a particular numerical value. Okay, so we are going to be iterating through the word paint. In this case, the first letter is P, has a numerical value, and then the next letter has a numerical value. And every time we loop through this, we are going to multiply this by 23. And the reason I picked 23 is it is a prime number and it makes this more random. Okay, and you can just put any prime number there you want. And the modular operator, what this is it going to give you the remainder when you divide. So you are going to divide whatever this is, come up with the data dot length. Okay, this dot data map dot length, and that is our address space. Okay, and remember, because this is going to be 7, the remainder will always be 0 through 6. And that is what is going to determine what address space a particular string is going to go into. And then we are going to return hash, and this number is always going to be 0 through 6. If you have an address space, that is 7. And that is how the hash function works. And you can do this math however you want, so long as in this case there are 7 address spaces. Okay, 0 to 3, 0 to 6. It is just have to always return something that is going to be 0 to 3, 0 through 6. So there is our code. So let's go over to DevTools. Okay, and there is our constructor that is just going to create our empty array. That is our hash function, and we are not using that here. We are only going to use that when we create other methods that put things into the hash table or remove things from the hash table. Okay, and this is where we create our hash table. Now let's try to run this. Okay, so let's zoom in on this and let's open this and open this. And you can see that data map is just an array with a length of 7. Okay, so that is our hash table constructor. So now we are going to do our set method for our hash table, and we are just going to bring up this address space here and our hash function, and then we will set an item, in this case bolts. That key bolts is going to get run through our hash function and it is going to produce the number, let's say 4. Also our set method is going to produce this array with a key and a value, and we are going to put that at the address of 4. So I'm just going to remove this and then we will get into the code. So our set method, we are going to pass it a key and a value, and the first thing we need to do is to figure out the index where we are going to store this key value pair. Okay, so we are going to have a variable that we call index, and then it will be equal to this dot hash, and you pass it the key which gets run through that hash method, that is going to produce the number 4, and that is going to be our index. So that variable index will be set to the value of 4. Okay, so the next thing we need to do is build this empty array that we will push the key value pairs into, and we will just do it like this. So this line here, this dot data map at the index of 4 equal to this empty array. Okay, that is what we will do, and this is the step that we only want to do if there isn't already an empty array in there. So if we were going to insert something else at the index of 4, we wouldn't want to do this step, so we will wrap this into an if statement like this. So this is basically saying if this is completely empty, only then we will do this. Now we can push in our key value pair, and we will do it like this. Okay, let's walk through this dot data map index, and which is 4 dot, we want to push the key value pair, the array with these two items, which is this one. Okay, see, like this, that is pushed into there. Now let's look at adding another key value pair to the same address. We will run the set method, pass it a key and a value. In this case it is going to be this one. First of all, we will run the hash to see what the address is going to be, and the index for washers with the hash method that we are using is also going to return 4. Then we will move to this if statement. Is there already something at the address before there is, which means we are not going to do this step, and we are going to move to this step, and it is going to push the key value pair washers 50 into there. And then just I am going to add one more key value pair at the index, let's say 6. There is one more line of code that we need to add, and that is to return the hash table. Okay, and when we move over to DevTools, we are going to use this code, and we are going to build an empty hash table with 7 items in it, just like this. And then we are going to use this set method to put all 3 of these key values pair into the hash table, and then we will take a look at the hash table. Okay, so let's come here. Okay, there is our set method that we just created. Then the hash table that we are going to create here it is just going to be an empty hash table. Let's zoom out, and let's run this. And if you open this, is an empty hash table. See, it is an empty hash table with a length of 7. Now clear this. Now I will just use the up arrow. Okay, we will say lumber 70 and washer 50, and let's say bolts 1400. Okay, so let's clear this again. Now I'm just going to show my hash table. Okay, now if you expand this one, you can see that we have 2 items at the 4 index. These are our items, washer and bolts. And down here at the 6 index, we have only 1 item, that is lumber. Okay, and that is our method for set. Okay, so now since we have completed the set method, now we are going to talk about get method. So I'm going to start by bringing up this address space here. I'll bring it up on the bottom this time with bolts and washers, and this to represent our hash method. So if we say get washer, it's going to go into the hash method, and it is going to return the number 4, just like it did in the set method. And then we can go to the address of that 4 search through these key value pair at that address. And what we want to do when we look for washers is we want to return the number of washers that we have and return the number 50. But if we say something like get lumber and we put it through our hash method, it is going to return the number 6. We go to the number 6, number isn't there, and this will return undefined. Okay, so let's start writing the code. So we are going to say get a particular key, and just like we did in the set method, we have to get something by the index. So we will have a variable called index, and we are going to use the hash method to determine what that index is going to be. So we pass that the key, it is going to calculate what the address is. Then we go directly to that address and search for our key value pair. The next thing we have to do is determine if there is anything at that address. So we will say if this dot data map at that particular index. If we are talking about the index 4, there is something there. If we are talking about numbers index 6 and we look for number, there is nothing. If there is not, then we are going to return undefined. But if there is something there, that when the if condition will be true. Okay, so then what we will do? We will loop for that. We will do a loop here, okay, for looking for a particular value. So this part here, this length is the length of this array. Okay, here this array, so that has a length of 2. It has 2 key value pair in there. So as we are looping through, we are going to say if, and we will walk through this line. Index is 4 and I is going to be this first key value pair, and 0 is going to be the bolts, the first value in that array. Okay, so let's say we are looking for washers. So we will do this again, and we can say index once again 4, but and I is going to be this next key value. 0 is going to be washers. Now if it is equal to the key, and what we will do is return the value that is associated with the washers. Okay, like this, and that is going to return the number 50. But if we go through this for loop and we don't find what we are looking for, then we are going to end up returning undefined. So that is all of the code for this method, and we are going to build this hash table just as you see it on the bottom here with bolts and washers. And then we will use the get method to get these items, but we will also look for an item that is not in there, just like we did for lumber. Okay, so let's go to DevTools, and this is our get method. This is the hash table, okay, with bolts and washers. Now let's run this one. So this is our hash table. Expand this one, and you will be able to see here we have a data map, and you can see at the index of 4 we have 2 items, and at the index of 4 we have these 2 items, these key value pairs, bolts and washers. Okay, now I am going to say get bolts, and see it is giving us 1400. Get washers, and it will give me 50 here. Okay, and if I do something like lumber, it will return undefined. It will return undefined here. Okay, so this works for all of our test cases here. Okay, and that is our method for get. Now let's talk about keys method. So in the keys method, what we are going to do here is to take all the keys that are in the hash table and return them in an array. So I am going to bring up our hash table here. We are going to have a couple of items in here. Okay, so in order to return all of the keys, the first thing that should be obvious is we are going to have a loop that will start at the beginning, and then start going through looking for items. And when it gets to an address that has items, we are going to need another for loop to go through this array to return the keys from these key value pairs. Okay, so first of all we have this keys function. Let's start coding. Okay, so now we know we are going to return an array with these items, so we will have let all keys equal to an empty array. Okay, then I also want to mention that we are going to have 2 for loops. So the first for loop is going to go 0 through 6 through the length of the array that we have called data map. Then we are going to have a second for loop to go through these items, and that is going to look like this. So as we are going through that first for loop, we are going to have like this. Now that doesn't have anything if the first index, so we don't want to run the second for loop at all. Okay, so what we are going to do with the second for loop is we are going to wrap this with an if statement. We are only going to run the second for loop if there is something at the address. Then we are going to move across until we finally get to the index of 4, where we have a couple of values. Okay, and the statement will be true, then we will run the second for loop. And when we do, we will push those items into that all keys array with this code here. Okay, and then the only thing left to do is to return the array. So we will look at this code in a moment and dev tools, and we will try to build this hash table just like you see here. Okay, so as you can see, this is our key method, and this is going to build the hash table that we just saw. So now let's try to run this one. Now this is our hash table. Okay, and in the hash table you have your data. Okay, you can see here. See here, 4th index, the address of 4, we have 2 items. Now open this, and we have bolts and washers. Okay, now let's run our keys method. See, and this is returning an array with bolts and washers. Okay, so I'm just going to set one more item here. Let's put lumber in here. Okay, and now use the keys again. See, now you have lumber as well. Okay, so that is what you can do here. This is your method keys. Now let's look at the big O of hash table. So I'm going to bring up a hash table here, and each address has a linked list instead of the arrays that we have been using, just because this is easier to look at and present graphically. And I'm going to bring up this box which represents our hash method. So when we run a hash on one of these keys, that equation is going to be the same number of operations, which means it is constant time. So the hash itself, the hash method, is O of 1. Okay, so if we are going to set a new item, a key and a value, and we run that key through the hash method, and we get a particular address, say 2 in this case, and we push that item on, that's O of 1 operation. Okay, and also if we do a get screws, in this case we put that into our hash method at the index of 6, we can find that in one operation. But what if screws is not down there where we can find it in one operation? Say we have a situation like this. Now when we say get screws, it's very quickly to get the index of 2, but then we have to go through the entire linked list to get to what it is, what that we are looking for. So you might say that this is O of n as our best possible scenario. Okay, but when we are dealing with the hash table, especially the built-in hash table, which is objects in JavaScript, there is going to be a much larger address space. The hash function is going to be very efficient at randomizing the addresses where things get assigned. So it is going to look something more like this. Okay, you might have some collisions, but it is going to be very rare. And because of that, finding something by the key of the key value pair is O of 1 operation. Okay, and that is the important thing to understand for hash table big O. Okay, so now let's talk about graphs. Okay, so we are going to go over a little terminology here before we get into this. So this is a graph, and you will hear this referred to as a vertex or a node. Vertex is actually the proper terminology, but you will hear people refer to this as a node sometimes. Okay, and I'm going to bring up another one of these. Now let's connect these two, and this is called an edge or a connection. Edge is actually the proper terminology, but you will hear people say connection, but this should be called an edge. Okay, now I'm going to bring another vertex here, and one of the things about graph is this new vertex can connect to this vertex, it can connect to this vertex, or it can connect to both of them. Okay, there is no limitation to how many other vertices a particular vertex can connect to or have edges with. Okay, so what do we use these graphs for? Let's say that we want to go from here to here. Okay, this would be like a map app, like a GPS on your phone. Obviously the wrong way to go would be to go this way and then this, then up this way. Okay, because there is a much faster way to just go one hop like that. Okay, so one of the things about graphs is when we can't weight these edges like this. Okay, now the most efficient way to go, because you want to go the least cost path, would be to go this way. Okay, you don't want to get this way because there is probably more traffic on that road. You can say wait. Okay, there is something we also use in routing protocols on a network. You might have two very fast links and a one very slow link. Okay, so it would be better to have that extra router hop to be able to send your data. Okay, that is another example of a graph. So there is another aspect of edges that we are going to look at here. Let's say this is a Facebook and you and friend. The friend is a friend with you and you are friends with them in Facebook. Okay, with normal accounts. Okay, okay, just normal friend. You are friend with each other on Facebook. Okay, so there is a bi-directional relationship. If you have all bi-directional edges, it is generally represented with a line with a line without arrows. Okay, assume that if there aren't arrows, that is bi-directional. Okay, so now let's change this. Instead of you and a friend, let's say it's you and a celebrity on, okay, say Twitter, on Instagram. Okay, now this is a one directional relationship on those platforms because you are following someone, but that doesn't mean they are following you back, right? In this situation it is most likely that they are not following you back. So that is a one directional relationship. Okay, now in this course, the way we are going to build our graphs is that all of the edges are going to be bi-directional and they are not going to be weighted. But I want to show you that those are possibilities and those are things that we do with graphs. Okay, I also want to point out that we have seen a couple of graphs in this course. A binary tree. Okay, a binary tree is a type of a graph that just has a limitation that it can only point to two other items and each of the connections are bi-directional. Okay, and in the tree section we mentioned that we had seen another tree and that was linked list. So linked list is linked list are trees and trees are graphs. Therefore a linked list is also a graph. Okay, but typically what we think of a graph, it is something like this. Okay, that is our graph. Now there are a couple of ways that we can use to store a graph. Okay, and one of them is called adjacent matrix and the other is in adjacency list. Okay, so let's look at adjacency matrix first. Let's say we have this graph here. Okay, the adjacency matrix for this would be look like this. So let's build this out. Let's start with a points to E and B. Okay, so in the adjacency matrix A points to B and E. We would put ones and those spots and then A can't be possibly, so it is 0. Okay, A can't possibly, and A cannot possibly do with C and D, cannot point to C and D, that is why it is 0. Okay, so that is how you represent A in the adjacency matrix. Then B is pointing to A and C, so B is pointing to A and C. Okay, and because it is not pointing to others, so others will be 0. Okay, and then I will just build out the rest of these like this. Okay, that is what our adjacency matrix would look like for that graph. So on this axis here, that is the vertex and this is what it points to or not, right? And like I mentioned before, I can't point to A and also B can't point to B and so on. Okay, A can't point to A, B can't point to B, so all of these diagonal will be 0. Okay, or they will always be 0. And if the graph has all bidirectional connections, the matrix is going to be symmetrical. See, like this, across that across that this one matrix, it will be symmetrical, it will be a mirror image. Okay, but let's say see what happens when we make one of these connections directional instead. Okay, we will just take the one that is between A and B and focus on that. So first let's look at what it means for this to be bidirectional in the matrix. See, when we say A connects to B, that is this one here. Okay, and then we have if the connection is going back from B to A, that is the other connection. See this one here. Okay, B is connecting to A. But if we just say that A connects to B, then in the matrix we have to remove this one from B to A and change that to 0. This one we have to change to 0. So as soon as we have any of these connections that are directional, the matrix is no longer symmetrical. Okay, so I'm going to change this back to bidirectional in our graph, and then I'm going to change this one to 1 again. Okay, so now everything is symmetrical again. Okay, also if we wanted to make this graph weighted like this, instead of having the matrix be all ones, we can change it to where we store the weights in the matrix. Okay, so I'm going to change these all back to ones and remove those weights from the graph. Okay, and that is our quick overview of the adjacency matrix. Okay, now that we have looked at the adjacency matrix, this build out an adjacency list. So I am going to bring up the same graph that we used before. I am just going to represent this in a adjacency list instead of a adjacency matrix. Okay, and this is going to be very simple. Okay, so we are going to store this in an object. Okay, so we are going to start at the top 3 with A. It is connected to B and E, and in the object we will represent the vertex A and its edges like this. Okay, so A is a key, the edges will be B and E. Now let's just move the graph like this. So B will be A and C. Okay, B is connected to A and C. C is connected to B and D. D is connected to C and E. Okay, and E is connected to A and D. Okay, as simple as that. Okay, so that is what you can do here, and because this is so simple, this is what we are going to use in this course to represent our graph. And this is our quick overview of adjacency list here. Okay, so now we are going to look at the big O of graphs. So we are going to represent this graph as a adjacency matrix and a adjacency list, and then we are going to look at the difference of big O between doing various things between adjacency list and adjacency matrix. So the first thing we are going to look is space complexity. So within adjacency list, we are going to store the vertex of the edges, and I am going to highlight these edges like this, B and E, in the matrix as well. We are going to store those, but in the matrix you are also storing everything which is not connected as well. So you have to store both in matrix. That makes matrix more inefficient and list more efficient in space complexity. So that is the space complexity of both of them. For the matrix, it is number of vertices square. That is a space complexity for matrix. Okay, whereas for list, it is storing all of the vertices and all of the edges here. So vertices plus edges, and that is the space complexity of the adjacency list. Okay, now if we are going to add a vertex, let's look how we do it in each one of this. We will start with the list. If we are going to add a vertex, slide it here like this. Okay, so it is very easy to do with the list here. Now let's look at the matrix. We have to change the matrix to look like this. It would be equivalent of having to create a new row and column. Okay, so in terms of time complexity, it is number of vertices square, but it is 1 for this one. Now if we want to create an edge between them like that, let's look it here, starting with this one. Remember, this is between B and F. So like this, push here something like this, okay, on the B, and then B on the F. Okay. In case of matrix, if you are this value here and some value here, this value, okay, it is also simple with the matrix. So the big O of each of this is 1 here. Okay. Let's bring back our diagram here. Now let's say we want to remove an edge. Let's look at this, starting with the list here first. Now when the edge is between B and F, so we are going to start with B and we have to complete through the array and look for an F. Now the array can be very large. Okay. So, and the vertex can be connected to a lot of items. Okay. So we have to iterate through everything to that F. Then we have to do the same thing for F as well, where we have one value here, but once again you can have a lot of values in the F as well. Okay. If you want to remove like this. And in the matrix, we are just going to do 0 here and change this one to 0 here. Okay. So the advantage on this one is actually for matrix, adjacency matrix, because for 1 is a time complexity for matrix, but it is edges for list here. Okay. Now the next thing we are going to look at is removing a vertex. Okay. So let's start with list here. So it is very easy to remove this vertex like this. The problem is you have to go through each of these vertex like this and remove all of the edges which are connected with that one. Okay. And then you go with this one, then you go with a list of vertices. Okay. Do you have any F's inside this one? And that means I have to go with every vertex and every edge to be able to remove all of these F's here. Now if you have bidirectional, that is a shortcut which makes it more efficient, but still you have to go and look with a lot of different vertices and iterate through the arrays with edges. And with the matrix, what you can do, you can remove this simply. Also, it is very efficient for list, but for matrix it will be vertices square. Okay. So you have to touch every one of them, which is going to be better than the adjacency matrix. So now let's do the other comparison on this. So I want to talk a little bit more about matrix. As we discussed before, not only you are storing the values, but you are also storing which edges are not available. Okay. So the bigger the tree is, the bigger the problem it becomes to store all of these values. The bigger your tree becomes, the bigger it creates the problem for storing all these values. Okay. So for example, let's say if you are storing a lot of Facebook users data, okay, and if the billions of people are on Facebook, now even if all of them are not connecting with others, that data will also be stored. For each and individual user, to all of those to whom it is not connected, that will also be stored, that data will also be stored here, right? To whom they are not friends with on Facebook, a singular user. So that is the problem here, and that is why we are using list here, because adjacency list is more efficient and it is more lot simpler to code here. Okay. So that is our overview on graphs big O. Now we are going to add a vertex to our graph. Okay. So vertex is going to look like this, and eventually we are going to have something that look like this. but in order to be able to have this, we are going to have edges, and that will be a different method for creating edges between the vertices. So let's start with that, which is actually going to look like this. So I'm going to bring this down to the bottom, and we can start writing our code, and we can start with the class graph, and I'm going to write out the constructor here as well. The constructor is simple enough that it doesn't make sense to do a separate video for it. Okay, so I just include it in this one. This is the entire constructor. We are just creating an empty object, and I'm calling it adjacency list, and that's it. Okay, so the constructor is just going to create this. Okay, the add vertex method is going to do this and put it into that empty object. Okay, so let's build the add vertex method here. Okay, so we will pass it, in this case, the letter A. Then we will add it to our adjacency list object like this. Okay, we set it equal to that empty array, and that creates the vertex. But we are not allowed to have duplicate vertices, so we will have to do something like this. If statement, if this dot adjacency list, if there is already a value, then we are not going to do that. Okay, also within the if statement you can return true, that we are able to add that vertex, otherwise we will return false. Okay, now we will take a look at this in DevTools in a moment, and we will create that vertex with a value of A. Okay, so let's come to DevTools. Okay, so this is our constructor that creates that empty object and our add vertex method. Okay, then down here we are just going to create a new graph, and it will be empty. So let me run this. See, this is our empty graph. It is empty. You can expand this one. You can see that this is adjacency list is empty. Okay, so let's clear this. Now I will call this, we will add a vertex with the value of A. It is returning true, which means we are successfully able to add vertex. Okay, so if I run this again, see, it is showing the false here. Okay, it is going to return false because the second time around this is a duplicate value, and that is why it is not adding second time. Okay, so I'm going to clear this. I'm going to say my graph and press enter, and see here, expand this one. See, now we have that new vertex with a value of A. Okay, and that is our method to add vertex. Now after adding vertices in our graph, now let's add edges between them. Okay, so let's say we have these two vertices, 1 and 2. That is going to look like this, and we can connect them with a new edge like this. Okay, and it's actually going to look like this. Okay, that would be 1 and 2 connected to each other. So let's remove this edge for now and actually build this with our code. We will say add edge method, and we are going to need a vertex 1 and a vertex 2 that we are connecting to each other. In this case, vertex 1 is going to be the value 1. Okay, and the key is going to be 1, and vertex 2 is going to be like this. Okay, so then what we will do to say vertex of 1, the array that is attached to it, we are going to push onto that array. Okay, the value of vertex 2, which in this case is actually 2. Okay, and then we will do it other way. Then we can say on vertex 2 we are going to push on the value of vertex 1, which in this case is the value of 1, like this, which will look like this. Okay, and that's add the edge. But one of the things that you cannot do is create an edge between vertices that do not exist. So if you try to add an edge between 1 and 3, that is not going to work because we don't have a vertex with a value of 3. So we will wrap this in a if statement like this, and we have to make sure that vertex 1 and vertex 2 actually exist. And then we can do those two other steps to actually push those values into those arrays. And then inside of the if statement we will say return true, and otherwise we are going to return false. Okay, So let's take a look at this in our dev tools. Now this is our add edge method, and we are going to create a new graph like this. Okay, and create those two vertices 1 and 2. If you run this one, this is the answer you will get. You can see that we have a graph with two vertices 1 and 2, but they are not connected to each other. Okay, those two arrays are empty. So I will clear this, and now I will write something like this. Okay, my graph dot add edge with a number 1 comma 2. Okay, and press enter. It is returning true here, which means and let me do one more thing here, one more time, 1 and 3, and it is returning false here as well. Okay, so which means that 1 and 2 are attached to each other, 1 and 3 are not, because 3 does not exist. Okay, now I'm going to say my graph here and press enter. Open this one and this one. See, now you have created a edge between 1 and 2. They are connected to each other. That is how you can add an edge. So now we have seen that how we can add an edge. Now let's look at how to remove an edge. So that is going to look like this, and the diagram will just remove that line in the object above. Okay, that is equivalent of doing this. Okay, so I'm going to bring these back for now, and we will write the code to actually remove those. So we will say remove edge, and it is going to be between vertex 1 and vertex 2. So I'm going to do something we haven't done in this course to this point, which is I'm going to say adjacent list vertex 1 is equal to adjacent C list vertex 1. Okay, then dot filter, and you can wrap these on two separate lines like this. Okay, or you could have a one big line. So filter is a method that is built into JavaScript for working with arrays, and you pass this as an argument, a function. Okay, this is called a callback function. So what we are doing here is saying return everything in the array that is not equal to vertex 2. Okay, so in this case that is just going to remove this item. Okay, but if we have 100 items in here, it would return the 99 that are not equal to 2. And then we are going to do the same for the second vertex like this, and we will say dot filter this, and we want to return everything that is not equal to vertex 1, which removes the one that from array. Okay, so just like we had in the add edge method, we couldn't add an edge between two vertices that didn't exist. In the same way, you cannot remove an edge between two vertices that doesn't exist. So I'm going to wrap this in a if statement. Only do this if vertex 1 and vertex 2 both exist. Only then you have to do this. Okay, so we will remove those items, and then we will return true. If vertex 1 and vertex 2 do not exist, then we will do return false. Okay, so we will look at this code in a dev tool, and we will build this graph, and we will look at it. Then we will remove the edges between A and B like this, and then we will look at that to make sure that it worked. So come to dev tools. Now this is our method remove edge. Okay, and down here we are creating that new graph A, B and C, and we have edges between them, between all of them. Okay, so if you run this one, you will get your graph. Okay, and you can expand this one and expand this one. So see, we have A, B and C vertices, and then they are connected to all each other. Okay, so let's clear this, and I will say remove edge A comma B. Okay, like this. So it is returning true. Now I'm also going to try this with A and D, because D does not exist, so it will show false here. Okay, now clear this, and we will say my graph, and I will press enter. And now when we open this, you can see that A and B are no longer connected to each other. Okay, which means we have been able to remove the edge. Now we are going to remove a vertex. Okay, so if we have this graph and we are going to remove D, not only do we have to remove that vertex, we have to remove each of one of these edges as well. So we remove the edges first, then we remove the vertex. Okay, remove edges first, then remove the vertex. Okay, so now let's try to do this. Now let's try to work on this. Okay, so we represent this like this. This is the same thing. Okay, so let's focus on this because this is what we are really going to dealing with when we write our code. Okay, now I had mentioned in the Big O video that there is an efficiency that we can use in removing a vertex. If everything is bidirectional and the information that we need to make this more efficient is all contains in this array right here, because what we can do is we can pop this item from this array. We will set it equal to a variable, and we know because this is bidirectional that C has an edge with D, and we can go find that and remove it. And then we can do the same thing for B and come up here and you can remove D from here as well. Okay, and remove it. Then do the same for A and from here as well. Remove the D from here. Okay, and this case D is connected to everything else in the graph, but you could have 1,000 other vertices and you only have to go these three to remove the edges with D. So that is a huge efficiency. Once this array is empty, all of the edges that have been removed, now you can remove the vertex itself and you will be left with this as your graph, which would also look like this here. Okay, so let's get into our code. We will say remove vertex and we have to pass it whatever vertex we want to remove like this. Now I'm going to use a while loop here to loop through the array that is associated with the vertex that we are going to remove. We will say while this dot adjacency list for that vertex dot length, which means while the array still has length. To put it another way, as long as the length of the array is not 0, we are going to run this. Then we will have a temp variable here and we will set it equal to whatever we pop from that array. Okay, now once we have that piece of information, we can actually use the remove edge method that we just created in the last section, and we can do this. See this? So you need to have the two vertices that you are going to remove the edge between in order to use the remove edge method. So there is the first vertex that you are removing, and then there is the item that you popped off of that array. That is all the information you need to be able to remove that edge, and you can just go through this while loop until you remove all of those from the array. Okay, so it would look like this. Okay, pop that C. So temp is going to be equal to C, and then the vertex that we are removing is D. So C and D will be passed from remove edge, and it will be removed from here. Okay, and C for B, and the same for here as well. B for this B, then A, and then A from here, D from A as well. Okay, so now we have an empty array, and when we have an empty array, we are going to break out of this loop. Then the only thing left to do is to delete the vertex. So that is going to look like this. Okay, and that is going to leave us with this, which is going to look like this. Okay, so this is our code. Now one of the things I haven't done to this point, and I did this on purpose, and see if you caught this, you cannot remove a vertex that does not exist in the graph. So that means that needs to be the first thing in this one, that if this doesn't exist, we are going to run undefined here. Okay, and If it doesn't exist, you have to return undefined. Otherwise, you have to return the vertex. Okay, so you can write here, return this here. Okay, return the graph. So when we go over to dev tools, we are going to look at this code, and we are also going to build this graph and remove the D vertex and all of the edges that go with it, and we will be left with this graph. Okay, and we will check this. We would expect to see something like that as the final answer. So in the dev tools, this is our remove vertex method, and this is where I am creating my graph that we showed in the diagram, A, B, C and D vertices and the appropriate edges. Now let's run this code. Okay, so you will have this graph here. If you open this, see, this is the initial adjacency list. Okay, and now we want to remove the D vertex, and when we will do that, we will remove these as well, these D from these A, B, C and as well. Okay, so let's try to run this method, remove vertex. Okay, so D is the vertex I am trying to remove here. Okay, now if you run this one, see, it is returning your graph again. Okay, and if you expand the graph, now before expanding the graph, let's see one more thing with the invalid index. Okay, E here and like this, and if you press enter, see, it is returning undefined, because we should expect. Okay, now let's write the graph here, and if you expand this graph and expand this one, see, we have removed D vertex and all the edges along with it. Okay, and see, we have removed vertex here. Okay, so now we are going to see recursion, and this is a very good topic here. Okay, recursion. Okay, so my favorite definition of recursion is that it is a function that calls itself until it doesn't. Okay, so let me show you what I mean. Let's say I have a gift box here, and let's say in order to open the gift box, we have to run the open gift box method. Okay, and there are one of the two things that we are going to get when we open this gift box. Either we are going to get a ball, I am going to make it an orange ball. Okay, or we are going to get another gift box. Okay, if we get a gift box, we need to open it, and we open gift boxes with the open gift box method. Okay, and when we run this, we are either going to get orange ball, or we are going to get a new gift box. Okay, and we will run the open gift box method again to open this one, and let's say this time we actually get a ball. Okay, so let's walk through what this code might look like, and I want to emphasize here that this is a pseudo code. Okay, this is not real code that you can run. This is for example purpose only, for the simplification. Okay, so please do not go write this code and expect this to work. Okay, this is a function that we are going to use here. We have open gift box function. Let's walk through this. We will say if it is a ball, then return the ball. Okay, otherwise it is another gift box, and we are going to need to run the open gift box function again, which means the function is going to call itself. Okay, so there are two key rules that you have to understand with recursion. First, the process of opening each new box is the same, or the process of doing whatever you are doing with recursion has to be same. You are doing the same thing. In this case, we are constantly opening gift boxes. The other thing is that each time we open a box, we make the problem smaller, or whatever you are doing, each time you have the function call itself, it has to be operating on a smaller and smaller problem. Okay, let's walk through this function. So in this case, we have a gift box, and we are going to run the function open gift box, and then we are going to say is this is a ball. If it is, then we will return the ball. Otherwise, we will say we know it is a gift box and we are going to have to run this gift box again. Okay, this function again, which is going to create another instance of this function to open the second gift box. And we are going to say, is this the ball? In that case, it is not. So again, it is another gift box. So we have to open the gift box and we have to create another instance of the open gift box function. Okay, so this time when we run this if statement, this time it is a ball. It is a ball. So that causes us to not run this line of code. So we stop creating new instances of the function open gift box. Okay, and we do that because this was finally true. So now let's remove it and we will talk about another concept here. When we open a box and it has the ball in it, this is called a base case. That is when our if statement was true. If it is another gift box, this is what we call a recursive case. In this case, we need to have the function call itself again. And when we have another gift box, that's a recursive case. Then we get a ball, finally get a ball, that is a base case, and that is when we stop opening gift boxes. Okay, now let's focus on this if statement. Always have to have some condition that at some point is going to be true and cause you to stop having the function call itself. If you do not have this if statement here, you end up with a situation where you call the function and then that causes you to call the function again, and it will keep happening. Okay, it will keep, it will cause itself again, call itself again. Okay, and you will end up in a infinite loop here. Okay, and that is something you can call stack overflow. Okay, so this if statement is important. A couple of key mistakes that a student can make in a recursive function, that they will have an if statement that is never true. So in this case, 1 is never greater than 2. So this if statement is never going to be true. So you are going to end up in an infinite loop where you end up with a stack overflow, and this once obvious. You can just look at it and figure out that this is never going to be true. But sometimes we have things in a if statement that are much more complex, and if you end up with stack overflow, this is one of the places to check. Okay, one of the other things that you have to have this is if statement is you have to have a return in there. If you do not have that and you have something like console.log hello, so you run this and this if statement is finally true, it will console.log hello, but because there is no return statement, you go to next line of code and go back into that infinite loop of adding new instances of the getBox function, and you again end up with a stack overflow. Okay, so it is required that you have a return statement in there. Okay, so that is our overview on recursion. Okay, so now I am going to talk about call stacks. This is an important topic to understand if you want to wrap your head around recursion. Okay, so we had a data structure called a stack, and we use the analogy of a can of tennis balls, right? It is only the top ball that you can have access to at one time. So you remove that one. Now the second tennis ball we can remove that one, and now it is only when those you can go to the bottom one. Okay, so I'm going to keep this structure of a stack here. I'm going to move it over to the right, and we are going to use it as a call stack. So I'm going to explain the call stack with code that is not recursive, just to explain the call stack. Okay, then we will get into some recursive code that uses the call stack later on. Okay, so there is some code here. I'm going to call this function function1, and it is just going to console.log out the string 1. So when you run this function, it goes onto the call stack. That function does. Okay, and I'm going to run it. It is going to console log out 1. Now once it is done doing that function, 1 is done running and will be removed from the call stack. Okay, and okay, and let's say if I write function 2 inside this one, if I write function 2 inside this one, okay, something like this. So function 2 is going to look like this, and it is just going to console log out 2. But before it does, if I have, let's say, something like function 3 inside this one, okay, and when function 3 runs, that get pushed onto the call stack, and it looks like this. Now function 3, we are just going to have it console.log out here. We are not going to have it another function. Now when it guns done writing the 3 to the console, this function is done running. And once it's done running, you can pop that from the call stack. Now you can see that function 2 is at the top of the call stack. You can look at it like this. We were waiting for this line of code to complete function 3 before we move to this line of code, right? Okay, now we can console log out that too. And now function 2 is done. We can remove that from the call stack. Likewise, function 1 was waiting for function 2 to be done, and now we can console log out the 1, and now we can remove function 1 from the call stack. Okay, so notice we call function 1 first and function 3 last, but the 3 printed to the screen first and the 1 printed to the screen last. They are in reverse order of which they were called, and that is due to the order that these were put on the call stack. That is going to determine the order that these are going to be console.logout. Okay, so bring our code back here and let's look at this in the dev tools. There is our code here, our 3 functions, and this is what we call function 1. So now let's try to run this one. Okay, so you will get your 3, 2, 1, just like we would expect it to be. Now let's clear this. So the real thing that I want to show here is this. Up here, right here in the corner, you will see this show debugger, and if you click on this and we get this screen here, the thing I really want to care about, I am going to close some of these call stacks and breakpoint at this point, and I'm going to come over here and let's say where it says function 1. Okay, I'm just going to click on this and it creates a breakpoint, and we can see that because it is highlighted, but we can also see it here. Okay, let's close this. And now if I run this one, okay, that breakpoint is going to make it where that line at 15 is now highlighted, and what it allows us to do is to walk through the code one step at a time instead of all of it just running. So up here, that button is for us to step through. Down here we have function 1 is highlighted in green. That means that is the next line of code that is about to run, and when I click on step button, it is going to run that line of code. See, now on the call stack it is function 1. Then over here inside of the function is about to call function 2, and I'm going to click step again. That puts function 2 in the call stack, and the next line that is about to run is this one, function 3. So click on this one and see, now you have function 3 has been added to the call stack, and you can see that console log now is the next thing that is about to run. So if I click on this one, see in the output you can see 3 here. When it gets to the curly braces at the end of the function up here, that means we are about to end that function and remove the function 3 from the call stack. So we will click this again, and function 3 is now gone from the call stack. Now the next thing is we are going to console log out 2. Now we have console logged out 2. Now we are at the end of the function 1, and if I click this again, see function 2 will pop out from the call stack. Now we have console.log1, and you click on this and console logged out 1 here. See, now we are at the end of the function 1, and when I click on this, the function 1 will be removed from the call stack as well, and now that has been removed, and that is our overview of the call stack. Okay, so now let's try to learn factorial. Okay, now factorial is something which is used a lot inside recursion. Okay, so what is a factorial? See, this is 4 factorial. That is how it is pronounced. So basically it is 4 times 3 times 2 times 1. So let's bring this up here and look at why it is such a great problem for recursion. These last 3 numbers returns 2 times 1, which is equal to 3 factorial. Okay, so you could say that this is 4 times 3 factorial, right? And 3 factorial, that is the same as 3 times 2 factorial, and 2 factorial is the same as 2 times 1 factorial, and 1 factorial, well, this is just 1. Okay, this one is different. Okay, this one is our base case. Once we get to 1, we can stop doing this breakdown that we just did here. Okay, and one of the things we have already said about recursion, and we saw this in the gift box example, is that each gift box has to be keep getting smaller, and when you finally get to what it is that you're looking for, so getting to that 1 would be the equivalent of getting to the ball. So I'm going to shrink this down here so we have some room for some code, and I'm just going to bring the code in. It is kind of hard to go through a recursive function line by line, so I'm just going to bring this in, and then we can talk through how this is going to work. So our function is going to be factorial. We are going to pass it the number 4, that is going to be the n. If we ever get to the point where n is equal to 1, we are just going to return 1. So n equaling 1, this right here, equal to 1, we return this one. Okay, otherwise we are going to return n, in this case 4 times factorial of 4 n minus 1, that is 3. So we could look at it like this. It is 4 times 3 factorial. So I'm just going to put this code up here in the corner, and then we will walk through this step by step. So we are going to run the factorial function, and we will pass it the number 4. Then we are going to go back up to our function here and look at it if statement. If n equal 1, we are going to return 1, and but that is not the case here. It is 4. So we are going to return n times factorial of n minus 1, and that is going to look like this. See, like this, 4 into factorial 3. Okay, and they will be like that. Okay, then we are going to do that again. Is equal to 1? No, it is equal to 3. So we will do the same like that. See, 3 into factorial 2. Now we will go look for 2. If statement again, is it equal to 1? No, it is 2. So once again we will do this. Okay, so 2 into factorial 1. Now we have 2 and 1 in there. Now what we are looking for in if statement is n equal to 1. So yes, this time it is. So we will return 1. Okay, and that is here, this one. This one is this one here. Okay, so now look at these steps here. So the return 1, that is being returned to this function, that it's been waiting for this to return, right? Now this can calculate 2 times 1, and it can return 2 to here, and that becomes 3 times 2. Then we can return 6 here. Okay, and then 4 times 6, 24. We can return to the original function call, which is 24. So see, like this, 2 into 2 times 1, 2. Okay, comes here, this comes here, 3 times 2, 6. This comes here, 4 into 6, 24. Okay, and 24 comes here, and that is returned to the main method, main function. Okay, that is our answer for factorial of 4. So let's look at this another way, the get box method. This was factorial 4, this was factorial 3, this was factorial of 2, this was factorial of 1. The boxes keep getting smaller, and in the end you are getting your 1 here back. Okay, like this, and we will return 1 here. See, like this. Then comes here 2. Okay, 3 into 2, 6 comes here, 4 into 6, 24 comes here, and like this. Okay, Now I'm going to go over this one more way, because recursion is one of those things that you have to look at it a few times to be able to get it. This is called call stack. We are calling call stack with factorial 4. Then we have factorial 3. And then we have factorial 2. Then we have factorial 1. Okay. So then 1 is going to return an item to 2, which means it's done running. Then 2 is returning something to factorial 3. Okay. And then now this will return something to factorial 4. Okay. And see, it will keep popping up the items from the stack. Okay. So that is what you can do. It gives you 24. So now let's look at this and DevTools. So there is our code, and we are calling this number 4. You can zoom out, you can run this, and you will get the expected answer, that is 24 here. Okay, I'm going to clear this, and once again you can go to show debugger, and I want to show something, and that is when I create a breakpoint here. Now I'm going to run this. So our call stack, as we step through this, you will see factorial put on the call stack, right? That is factorial. You can see here, you can see up here that n equal to 4 up here. But on the call stack itself, it is just saying factorial 4. And when we run through here, it is going to call another instance of the function. Okay. So I'm going to click this. Now we have factorial on the call stack a second time. It will show you that n is equal to 3 this time. But the call stack itself is just showing factorial twice. Now I'm just going to step through this. N equals 2, n equals 1, and we have, see, these 4 factorial 4 times. Okay, you can't tell by looking at the call stack which one of the factorial it is, because they all just say factorial, because we are calling the same function over and over. Okay, that is why they have the same name. But if you click on this, see, it is n equals to 1, n equals to 2. See, if you click on the factorial, you will be able to see that which factorial it is, n equals to 4. Okay, like that. So that is what you can see here, that which argument you are passing here. So we will just run this here step again. Now you can see that it is highlighting the if statement is going to return 1, and we have popped that first item from the call stack. Okay, now we are for number 2, now number 3 and 4, and then when we pop this one out from the call stack, the only thing left is to return the number 24 down here at the bottom. Okay, so that is here. Okay, now I wanted to do one more thing here, and factorials is, it is amazing how fast they can grow. So 4 factorial is 24. If you have factorial of 8, see, this goes all the way to the 40,320. If you have factorial 20, see, you get this really huge number here. So they grow very, very fast. So it's a fun function to play around and see how fast those numbers grow. And that is our overview of factorial. Okay, so now let's start with bubble sort. So bubble sort is going to be our first sorting algorithm. It's probably the easiest one that we are going to do. Okay, so I'm going to bring up an array like this, except I'm going to show it like this. Okay, and I had previously shown arrays as being green. Okay, and what I am going to do with the sorting algorithm is I am not going to show them as green until they are sorted. So anything that is unsorted, we will make them blue. Okay, like this. And to explain bubble sort, so it works like this. We are going to start with the first item. I will highlight that in orange, and we are going to compare the first item with the second item. And if the first item is bigger than the second item, we are going to switch them. Now we are going to compare the second item with the third item, and if it is bigger, we will switch them, but in this case it is not. So now we move to the third item, and we compare with the fourth item, and then fifth item, sixth item, and so on and so forth. Okay, now the sixth is sorted. Sixth is sorted. That is the correct spot for the sixth. Okay, whatever the largest item is, we are going to bubble that all the way up to the top. So that took 5 steps to get that all the way to the end, and the sixth item array. Okay, then we start over and we compare with 4, 2, 3, and then like this. Okay, now the 5 is in the correct spot. Now the second biggest item has been bubbled up to the top, but that only took 4 steps. So each time we go through this, it will take fewer steps, but it is still pretty inefficient. So we will do this again, and like this, see, 4 will come to third place. Okay, so that is the correct spot for this one. Then I will it will take only 2 steps, so like this, and then like this. Now 3 is at the right spot. 9, and for the last one we will do with these two, and if they need to be switched to, we will switch them, otherwise we will not. So these two now are at the correct spot. So now I'm going to go ahead and mix these back up like this, and we will pick up here and we will code this bubble shot. Okay, now let's do the coding for bubble shot. Now we are going to pick up from here. Okay, and I'm going to shrink this down into a corner here, so we have room for our code. And this will be our function bubble shot, and we are going to pass it the array that we are going to sort. And as we discussed, this is obviously going to be a for loop inside of a for loop. So this is the first for loop. So we are going to set I equals to array.length minus 1. So remember, the first time we went through 5 times, right? Even though we have 6 items, and then we are going to decrement each time, because the next time I only want to go through 4 times, then 3 times, etc., for 2 times. Okay, like that. Then for the second for loop, we are going to go with j is less than I. So this makes it where the first time through we are only going through 5 comparisons, and then the next time 4 comparisons, then 3 comparisons. Okay, because we are saying j is less than I. Okay, so for the comparisons, we are going to say if item at j is greater than j plus 1, so this will be j for the first time through our loop, and this will be j plus 1. And in this case, we are going to switch them, and this is what the code we will use. Okay, so let's walk through this. We are going to say temp will be equal to array, so that would be our temp equal to this value. Then array j will be array j plus 1, so this will take this value. Okay, and then j plus 1 will have the value of temp. See, like this. Okay, so that is switch those two values. Okay, then after we get done through the for loop, the only thing left to do is to return the array. Okay, so let's take a look at this code in DevTools, and for the array that we are going to pass it, let me put it back here. Okay, that is the example I will take. Okay, so in the DevTool, now this is here, this is what we have, this is our function there, and that's the array that we are going to sort. So the only thing we have to do is to click run, and see, we have our array that gets returned 1 through 6. Okay, and that is our code for bubble shot. Okay, so now we are going to look at selection sort. Okay, so once again we will start with an array that looks like this. Okay, but with selection sort there is something different we have to do here. We have to keep track of the indexes. So I am going to bring up indexes for each of these. So this is what we are going to do. We will start with this first item, and we are going to have a variable called min for minimum, and we are going to store the index of that first item. Then we are going to start comparing that item to everything else in the array. So we will go with the next item. 2 is smaller than 4, so we want to store the index of 1 in min. Then we move to the 6, and so on and so forth with everyone. Okay, and if you come to 1 here, now that one is lower than 2 item that is in min, so this will be 4 index will come to min. Okay, and then we move to the end here, so this one is lower. So at the end of the loop here, we have come to the end of the loop, and we will move this one to the end of in the starting of the place like this. Okay, and when we do like this, so index of 0 after the switch is sorted. Okay, so I will say it is green. Then we will start with the next item. So 1 will be minimum, 1 index will be minimum. Okay, and then we will compare it with others. So as you can see, 2 is the lowest number remaining. So we will loop through this and we are not going to change that min item at all. And now that item at the index of 1, we know that is in the correct place. So I will color that green here because it is sorted. Then we will start with the 6 here, and the minimum index will be 2. Okay, and I'm going to move to, okay, and now what I'm going to do, I'm going to compare with others. So that is larger. Okay, now 4 is lower, so 4 will be index, and then 3 is lower, so 5 will be index. Okay, so the smallest number was at the index of 5 will be switched with this one, and then we have third one in sorted. Okay, and for this one, let's go. If the 3 minimum is 3, then minimum will be 4. Okay, because 4 is smaller. Okay, so 4 is minimum, so I will swap with 4. Okay, like this. Okay, now 5 item minimum is 4. Okay, so I will compare with these. So that means these are at the correct place. Okay, so now we have a proper sorted. So let's bring them back. Now we will start coding for selection sort. Okay, so now let's code for selection sort. So we are going to pick up from here. Okay, and with this array, let's shrink it down, and we can write our code here. Okay, so this is our method selection sort. Okay, and we will pass an array here, and I'm going to create a min variable that we used in the last section. Okay, and then we are going to have our for loop. In this 6 item array, we only had to go through this 5 times, so we are going to have it run the length -1. So let's bring this up here. I is going to be 0 when we first start. Okay, it is going to be our first item. So when we set min equal to 0 index, when we are walking through the example, we were really setting it equal to I. That is basically it means. Okay, so the first thing that we are going to do is set min equal to I, and this is the I from the for loop. Now we are going to do our for loop that is inside the for loop, and we will have let j equal I plus 1. So if this is I, then this will be I plus 1, that is j. Okay, so we are going to set min equal to I, which is 0 index. Then we are going to say if the item which is at the index of j, if it is less than the item at the index of min, which is 0 index, we will set min equal to j. So let's code that here. Okay, and bring our code like this. So see, this is here. If the value of j is less than the value of min, we are going to set min equal to j. So let this put it like this. In this case, now one index will be min. That is two value. Then j will keep running with all of them. Until it finds anything that is stored at less than the value of minimum. Okay, so now this will be j. So fourth index will be j. Okay, then we go to last one and we will compare with this one. So then a looping through the array will be completed. Okay, now we set min equal to 4, and then we need to swap, see, I with min, I and min. That is what we have to swap. Then item at the index of 0 is sorted, and we will color that green. So let's do that here. Okay, for swapping, let's write the code for swapping. See, this is the code after the for loop. After the inner for loop is completed, then we will do this. Okay, so that is what you can do for swapping here. Okay, now there is something you have to add here. What we have to add? So see, when the second time this will be I and this will be j, now you can just look at this and see that 2 is going to be the lowest item there. So we are going to start min equal to 1 index. directly one index, not the 0 index. Okay, and then j will loop through all of the remaining items. Okay, and nothing is going to be lower. So that means min will remain one index, and I is also equal to 1. Now we know that the item at the index of 1 is at the correct spot, so I'm going to color that green here. But what about swapping? Should I do swapping here? I mean, should I run these 3 lines of code? It doesn't make any sense here, right? Because they are the same item, right? We only want to run these 3 lines only when I and min are not same index. They are not same value. So we will wrap it into a if statement like this. Okay, if I and min are not equal, then run these line of code. Okay, so that is our rest of the code. The only thing left to do is return the array. Okay, but of course once we get down to this line, we will have to run through all of this and we will have a completely sorted array that looks like this. So we will look at this code in the dev tools, and we will look at the 6th item array that we started with, that looked like this. This will be our initial array. Okay, so in the dev tools, this is our program which I showed to you. Okay, and this is our selection sort function calling. Okay, so if you run this one, see, it has properly sorted the array for me. Okay, so this is our method selection sort. Okay, so now let's take a look at insertion sort. So let's bring up an array here. Okay, and insertion sort always starts with the second item. Okay, and then we compare it to the item before it, in this case the 4. If it is less than the item that is before it, we switch them like this. Okay, and then we move to the next item. In this case 6 is not less than 4, so it will stay at the same. For the 5, 5 is less than 6. Okay, so like this it will happen like this. Now it will compare with the 4. It is not less than 4, so it will come here. Okay, then for 1 it is less than 6, 5, 4, 2, see, all of them. And finally it is smaller than 2 as well, so it will come here. Okay, and then one more item, it is less than like this, so it will come back here. Okay, and that is all they are sorted, so I will color them green. Okay, so that is how the insertion sort works here. Okay, and now let's try to write the code for this one here. Okay, so let's do the coding for insertion sort. Okay, so we are going to pick up from here, okay, with this array with only these 2 items out of order, and let's shrink this down like this, and we will start our function, and we are going to have a for loop. So we are going to set I equal to 1 like we talked about. Okay, we will start with the second item, so index will be 1, and we are going to move through to the array, okay, with for loop. Then we are going to set temp, we will have a temp, and we will set temp equal to array I, so that value, that item at the second position. Okay, so whatever item we have available in the I, that would be assigned to temp. Okay, so this is temp, second item is temp. Okay, then we are going to have our second for loop. This is the one that we are going to compare everything before that item with, and I want you to notice that I am using where instead of let. If we use let to declare the variable, we can only use the variable inside the for loop. We are going to need this outside the for loop as well, so I am going to use where, and this is I. Okay, this is I. So j, this will be this one, I minus 1. J will be I minus 1. Okay, so j will be item to this one, point to this item. Okay, now let's say we are working with this 3, since it is the only one that is out of order. Okay, now until we get to 1, we need to actually move it. Okay, so we'll start with this one for example. This will be j. So what we are going to say here is that while j, the value of j, for if it is greater than temp, and this is the j and this is the temp, in this case it is greater, what we are going to do? We are going to move that j plus 1 to j. Okay, so we are going to set the next index equal to what was sorted at j. Okay, then we are going to say j minus minus, which is going to move the arrow here. See, like this. Now we will run through the for loop again, and now the item that is at the index of j is not greater than temp. That breaks us out of the for loop. Then we say at the index of j plus 1, that open spot, we are going to set it temp to equal to. Okay, like this. So there is one more thing that we have to look for, and that is to explain the switching the 1 at the 2 if like this. Okay, and now let's say we are starting with this number and we compare it with this 2 here. We are going to say j equal to the 2. Then we are going to see if the value at j is greater than temp, and in this case it is. So we are going to move that 2 over here like this, and then we are going to run through the loop again, and when we do, we are going to set the j minus minus, which is going to move j over to the index at -1. And obviously this is as far as we want to go with this loop, so we have to add something to this for loop. See, like this, which is we have to say also j has to be greater than -1. If we get to the point where the j is less than -1, then it is a problem. Okay, so we will directly come to this line and we will say at the index of j plus 1, and now j is -1, so -1 plus 1 0, which is we will have temp at the 0 index. Okay, so that is what you should do as well. Then you can simply return the sorted array. Okay, so we will look at this code in the dev tools, and we are going to use this array as an example. Okay, so here this is our function, and we are going to run this insertion sort on this array. Okay, so run this one and run this one, and you will get your sorted array here. Okay, so this is our method for insertion sort. Okay, so now let's talk about merge sort, which is our first sorting algorithm that uses recursion, and it leverages the idea that if you have two sorted arrays like this, these are two sorted arrays, combining two sorted arrays is fairly easy. So what merge sort does is this mix this up like this and move this to the okay, let's move it to the top here. It will take this array and it will cut it in half. Okay, and then it will cut in half again, and it will keep doing this until we have single items arrays, because a single item array is by definition sorted. Okay, then what we can do is take two of these and combine them into one larger sorted array. See, like this. Like this, we will continue doing this all the way across, like this. Then we will take these two arrays and combine them, and then combine these two. Now we can take these two sorted arrays and make them one larger sorted array out of this. Okay, now when you first look at this, you think that looks really inefficient to break all of this down into a single item array, but it is actually an incredibly efficient sorting algorithm. It is as efficient as you can make a sorting algorithm actually. Okay, so that is our quick overview on merge sort. Now we are going to do an intro on merge here. Okay, so what is merge? Merge is a helper function. Okay, and that we are going to use in merge sort. So merge is going to look like this. We have two sorted arrays, and then we are going to put them one big sorted array. But let's look at the steps we have to do to make that happen. One of them we are going to use I, and the other we are going to use j, and we are going to compare I with j. and whichever one is lowest, we push that into a new array. We will call that array, let's say combined array, something like that. And then we do it again. We compare I and j. In this case, j is lower, and then just we keep doing this process. So j is going to be the lowest here all the way to the end, and then we are done running through that array. So this is going to break us out of the loop. Either one of these is going to be 0 items. We are going to break out of the loop, and then we are going to have a different loop which says while just this one array has items in it, we are going to push all of them into until that array is also empty. Okay, and of course we will have one more which says other one has items in it. So the same thing we will do with other array as well if you have another array. Okay, that is our intro on merge. Okay, so now we are going to code our helper function merge. Here are the two sorted arrays that we are going to combine into one array. Okay, let's keep them here so that we have room for our code and bring this in. So we will just say merge and pass it the two arrays. Then we are going to create a new array that we are going to put these arrows into, called combined. And I'm going to create two variables, I and bring it to that where, and j, which will bring it to another arrow at the bottom or to that. Okay, and what we are going to use here is a while loop. Okay, so this is basically saying while either of these arrays have length, while either of the arrays have a length that is greater than 0, we will run this while loop. Then inside the while loop we will say if I is less than j, I'm just going to highlight that in here, okay, in the diagram below, and in this case it is less than j, we are going to push I into that new array that we are calling combined, like that. Okay, then we are want to increase I by 1, which will move it to over to the next item. So when we look at I and j this time is less than I. Okay, so for that we will say else, and then we are going to push that item into the new array. See, like this. Okay, and we will do j plus plus. Okay, so which will move that arrow over here. So we can run through this code. So like this, then like that, and then like that. Now j is gone. Now one of the arrays is empty, which is going to break us out of this while loop. Okay, then we just need to finish looping through array 1. So let's remove this code and bring in another while loop to loop through that array, and say like this, I plus plus, and then I plus plus, and then do this for this one item as well. Okay, that one has been pushed into the combined array as well. That breaks us out of this while loop as well. So the other possibility is that instead of array 1 is still having items in it, it was array 2. So we will just do a while loop for that as well. Okay, that's the opposite of the while loop above. Then we are going to return combined array, and we will have this closing curly braces. Okay, and that would be our remaining code. So let's come to dev tool. This is our entire merge method. Okay, and this is these two arrays I want to merge. So let's run this one. Let's try to run it here. Okay, and as you can see, this is our combined array 1 through 8 here. Okay, that is our merge method. Okay, so now we have written our merge helper function. Now we are going to go through the steps of writing merge sort. Okay, so the big thing merge sort is going to do is break items in half, and break them in half, and break them in half again and again and again. Okay, now the putting it back together, that's what we just wrote the code for in the merge function in the previous section. Okay, So that is going to take care of doing this thing here, and then this, and then this here. Okay, this will be done by the merge method which we created earlier, and merge sort is going to do this recursively. Okay, so there are two big things that have to be true when we do recursion. First, it has to do the same thing over and over, break arrays in half. Okay, breaking arrays in half. And the next thing is that there has to be a base case, is that when the array dot length is 1. And once we have gotten to this base case, that is where we use the merge function to put the arrays together. Okay, so with that in mind, let's see and try to code for this one. Okay, so now let's look at the coding for merge sort. So let's bring up this function here now, and we are just going to pass this an array. And as we discussed in the last section, the base case is when we reach an array that has a length of 1. So if we are going to say if array dot length is equal to 1, we are going to return the array, and that is going to be that array with the length of 1 that we are returning. Okay, now that we have the base case, the other thing we said merge sort does is it breaks arrays in half. So now we are going to write the code to break array in half. I am going to create a variable called mid, and we are going to set it equal to math.floor, and we are going to pass array.length divided by 2. Okay, so math.floor, all it does, it makes this into a whole number. Okay, so for example, if the array length is 3 and it is divided into 2, which is 1.5, with 1.5, so we have to floor is going to change that into a 1, because obviously the index always has to be a whole number. Okay, then we are going to create new arrays. One we are going to call left with the left side of the array, and the other we are going to call right, that contains the right side of the array. And this is all we need to do to break arrays in half. So let's say we have this array here. These 3 lines of code would do this to this array. If these were sorted, we could return merge. Okay, on left and right, these 2 new arrays that we created. But the problem is they are not sorted. These need to be broken in half again. So merge sort is the function that is we use to break arrays in half. Okay, so we take both of these arrays, left and right, and we use merge sort on each of them. Okay, and this is the part that is recursive, and that will break this in half, left and right, and then do the same for this one as well. Then we have reached our base case and start running these 1 items arrays here. Okay, now merge can work with these. Now these 2 will get combined, and the reason for that is that they were the last to go to the call stack, so that is going to run first. Okay, that's get popped from the call stack, and then we run it on this side, and then it runs again, and these are combined. And that is all of our code for merge sort. Okay, so let's look at this in a moment in the dev tools. Okay, and this will be our example array here. Okay, so in the dev tools, this is our method merge function. Okay, merge helper function, which we have written previously. And if you scroll down, then this is merge sort function. Okay, here, and this is the calling with 4 items array that we had just seen here. Okay, so if you click on run button, see here, as you can see, it is our sorted array 1 through 4. Okay, and that is our function merge sort. Okay, so now let's talk about big O of merge sort. I'm going to bring up an array here. The first thing I want to talk about here is space complexity, because with merge sort you have this original array like this, and you break this down into 2 arrays like this. You have actually created 2 new arrays, left and right. Okay, and you still have the original array, but now you have these 2 arrays as well. So you have So you just double the size in memory, and that is keep taking up. As you break this down, you still have these 8 items in addition, in addition to the original arrays that you have available. So the space complexity is O of n. You originally had 8 items in an array, then you had to create 8 new items, okay, and that is O of n. Now let's look at the time complexity. When you break these down like this, you have 1, 2, 3 steps to break this down. Okay, so we have seen this before. If you had 8 items and it takes you 3 steps, that is a log n operation. That is a log n operation. Okay, but when you put them together, if you think back to our merge function, you are having to iterate through each array to put these back together. Okay, so if you have this, you have to loop through both of these. So to put them together, to put them back together in a sorted array. So breaking this apart is O of log n. Putting it back together is O of n. And that is where we get the O of n times log n operation. And it looked like this on the graph. Okay, see this one, these ones. Okay, because when it comes to sorting algorithms, O of n squared are pretty much, and O of n log n are pretty much two options. Okay, there are exceptions to this with sorting algorithms that sort only numbers because there are some efficiencies with just numbers. But if you have an algorithm that is going to sort all different types of data, O of n times log n is as good as it is get. This is the best you can get. Okay, now it doesn't look like there is a huge difference between these, because on the axis on the left it is only goes to the 75, but if you start having to go to 1000 or 1 million, there is a huge difference between these two lines. Okay, which makes this much better for most situations than bubble sort, insertion sort, and selection sort, the original ones that we did. And the time complexity for them is O of n square, and that is our merge sort big O. Okay, so now let's start quick sort. So I'm going to bring up an array here like this, and except I'm going to show it like this here. Okay, and the way quick sort works is we are going to have a pivot point, and we are going to make that first item that for the pivot point, and we are just going to compare every item in the array to that number. Okay, so we will start at the 6. Okay, and I'm going to show that gray here because it is greater than this one. Okay, then we have 1 which is less than this one. Okay, so the item which is less than, we are going to exchange it with the first item that is greater. Okay, like this. Okay, then we move to the next one that is greater. So this is less than here. Okay, we exchange it with the first greater than item, and we do this again. Okay, and exchange that, and then the 5 is greater than 4, so we will show that one in gray, and we have one step left. Okay, we are going to swap that for with that last item that is less than, like this, and now the 4 is sorted. So I will color it green here because that is going to be where it is we sort everything in here, and everything that is less than 4 is on the left, and everything that is greater than the 4 is on the right. Okay, so now what I'm going to do here is we are going to run quick sort again on just this section of the array, and then we are going to do it on this other side as well. So let's focus on the left side first. The 2 is going to be our pivot point now. Okay, and we are going to compare the 1, and the 3 is greater than, so we are going to do like this. Okay, and then now the 2 is sorted, and then we will run this recursively on these two, and because there is only one item in each of these, we know that those are in the correct spot. See, like this. Okay, on the other side we will take 6 as the pivot point. Okay, 7 is greater, 5 is less, so we will exchange and exchange it again. Okay, so we will exchange the 6 with the 5. So 6 is sorted, and now 5 and 7 are sorted as well. Okay, and that is our overview of the working of quick sort. Now let's do the pivot intro here. Okay, So pivot is going to be a helper function, which much like the merge function was a helper function, okay, for merge sort. Pivot is going to be a helper function for quick sort. Okay, so I'm going to bring up an array and do it like this. Okay, and what the pivot function is going to do is this: we are going to have a pivot item and we are going to highlight that for there it is going to sort all of these, and then it will swap like this. That is all it is going to do. So let us put this back here and go through the steps that we need to go through to make that happen. So I am going to go into a little bit more detail in this one here. Okay, and now let's bring up some variables to explain this more properly. So let's say we have this pivot point here, and this is, let's say, our I. Okay, the next item over here. Okay, that is going to be I in our loop, and this is going to be a variable called pivot, our first item, and then this will also be swap. Okay, this is where we are going to start being set out to pivot. Okay, so we'll start out by looking at the first item that is pointing there I, the 6, it is greater than, and then we move I to the next item. Now anytime you have something that is less than the pivot variable, we will move the swap. We will move the swap up to here, and then we will use that to swap these two items. Now I will go to the next one, 7 greater, 3 is smaller. So because 3 is smaller, so swap will move to next position, and then this will be swap like this. See like this. Okay, then you go again, so 2 is also smaller, so 7 will be swapped with 2 here. Okay, so 5 is larger, so I will not do the swapping here. Okay, and now we are done with the loop here. Now you can remove I. So if you see swap and pivot, you can swap. You can swap the swap variable and pivot variable. Okay, and normally when we are working with an array at the end of the method or the function or whatever we are doing, we are returning that array. So but that is not what we are going to do here. We need to return that swap variable. Now this is everything the pivot function is going to do, but I am going to show you why we need to swap that. Because when we run quick sort on this side, we are going to be running on the index of 0 through swap minus 1. When we run it on this side, we are going to run it on swap plus 1 to the end of the array. Okay, so that is why we have to know what that index is where swap is available. Okay, and that is our overview on pivot. Now we are going to write our pivot code. Okay, so we are going to use the same array like this, and I am going to shrink it down so we have room for our code. Now one of the things that we are having to do in a couple of different places in pivot is swap two items. So you can do that with these 3 lines of code like this. But since we are going to use this twice, I am going to make it its own function. We are going to pass it an array and the first index and the second index of the item that we are going to swap. And this is going to take care of that. So this is going to make our pivot code a little bit cleaner. Okay. So let's start the pivot code itself. Okay. Now we have 3 arguments here. The only one out argument that you have to pass it is the array. Okay. Because there are 2 by default, they are going to need to be, when you pass it the array anyway, the index of the first item in the array is going to be 0 and the last item is going to be length minus 1. Okay, that is why they are same. So you don't have to worry about this when you are passing the array to the pivot function. But the reason we have this is we saw that we are going to run quick sort after the first time through on a subsection of the array, and we have to know the first and the last index of that section of the array that we are working on then, and that is why we have to do like this. So I am going to bring up our first variable pivot, that is going to be this. So the variable is pivot index, to emphasize is that we have this one. So I am just putting pivot to make this better. Then we are going to start out with the swap index being equal to the pivot index. See, like this. Then we will have our for loop, and here is I, and the I is going to be pivot plus 1. and we are going to run the loop until we get to the end index. So then we start doing comparisons. If the value at the index of I is less than the value of the pivot index, we are going to do in this case that is not true. So I am going to show it gray, okay, and move the I. In this case it is less than, and when that is the case, we are going to do two things inside of this if statement here. We are going to move swap over like this, and then we are going to use that swap function like this. We pass it the array, the swap index and I, and it will swap those two items. Then we are going to keep going through this for loop until the array is going to look something like this, okay. And the next thing is we are going to call that swap function and switch these two items like this. And now there is one thing left to do, and that is to return that swap index, which means this function is addition to rearranging all of the numbers to be like we have at the bottom on the screen. It is also going to return the value of 3. So this is our code for pivot, okay, and this is going to be the result we will get here, okay, when we start like this, okay. So let's look at this in dev tool. So there is our swap function and our pivot function is here, and we are going to run pivot with my array, which is this one, okay, and I'm going to run this one, and it is going to return the number that is index. But let's also look at my array, and there is the array. See, 4 is in the middle. Everything on the left is less than 4, everything on the right is greater than 4, and that is our function for pivot. Okay, so now let's code our quick sort. I am going to bring up our array like this. So right out of the gate, when we run pivot, we are going to have our pivot item like this, and we are going to sort it like this. It is going to return the index, this index. What we have to do with quick sort is to continue doing that on this side, and then this side, keep breaking this down until we have sorted everything, okay. So I am going to put our array back the way it was, then shrink it down into the corner like this. So I am going to bring up the function in like this. Just like the pivot, you only have to pass it an array to begin with, okay. It's only when we start calling this recursively that we have to worry about that left and right. So in our first line of code that I'm going to bring in here, we are going to store that index that pivot returns like this, and we are passing pivot these 3 pieces, a piece of information, okay. It is rearranging our array like that, but it is also returning that index we are storing it in, okay. So the final 4 value which is in the middle, that is piece of information, and that index we will return here in the pivot index, okay. We can now call it recursively like this. So if you look at our diagram at the bottom, it is these 3 items that it is being called on this in this situation, and we have it call it again because left is 0 and pivot index is -1. That is the last index here, okay. Then we also need to call this on the items on the right, that we would do that like this. I will bring up that bracket to represent this, okay. So on here, now let's look at a little bit further. First start with left hand side. So we will have this as pivot. 1 is smaller, so swap, okay, we will swap, okay. Then we are going to call it again. But in this situation, you don't want to call quick sort again because you already know that these are in the right spot. That is going to be our base case. Let's do this over here as well. 6 will be pivot, 7 is greater, 5 is smaller, so switch like this, and then we will have now we know that these two are individual, so you do not need to perform quick sort. Also that is our base case, okay. So Now the thing we need to do here is have some kind of if statement. So to make this work, we are going to do this if statement where we say left has to be less than right. So in what we just saw here, what was left and right were the same item because there was only one item left. When that happens, we are not going to continue having quicksort call itself. Okay, and now once we get to that point, we can just return the array. Okay, so we will look at this code in a moment, except we will start with an array that looks like this. So let's go to DevTools. Okay, this is our swap function that we created, and this is our pivot function. And here this is our quicksort method, and this is our array that we are going to sort. Okay, now if I run this one, see, it is returning me the sorted array here. Okay, so that is our code for quicksort. Now let's look at the big O of quicksort. So I'm going to bring up an array like this, and when we run pivot, it brings us to a point like this. Okay, it brings us to a point like this. So the first thing I want to point out about this is we didn't have to create any new items here. Okay, we just move things around within the same array. Okay, so there is different than merge sort that creates a new items and therefore doubles the amount of space. Okay, that it takes up memory. With this, you are working only within the original array without duplicating any data. So from a space complexity perspective, this is O of 1, and this is an advantage of quicksort over something like merge sort. From a time complexity perspective, in order to move all of these items around like we just did here, that was O of n because we had a for loop that went from the beginning of the array all the way through to the end. And if you look at how many times we had to do this, this was 1, and then we did it 2 and 3. Okay, this is going to be log n. So what we just did here is O of n times log n, and we look at this on the graph like this. It is much better than O of n square, but the problem with this is what I just showed you is actually the best case of quicksort. The worst case is not O of n times log n. So now let's look at the worst case here. The worst case is if you have already sorted data. So if we take that first item there, we make it pivot point, we are going to compare that to all the other items in the array, and that is not going to move. So I will color that green. But what we normally do with quicksort is we run quicksort on all the items on the left of it, all the ones that are less than, and then it run also on the right. Okay, it is splitting of that array that makes it efficient, right? But in this case there are no items on the left, everything is on the right here, so there is no splitting of the array. And the same is true when we look at 2, we compare it with everything else, and there are only on the right items on the right for 3, 4, 5, 6 and so on. Okay, all the way to the very end. So in this circumstances, this is actually O of n square. Okay, that is our worst possible case, and that is the big O measure. Okay, so our best case or average case would be O of n times log n, but our best case is O of n square. So if you have a sorted or almost sorted data, this is not a good sorting algorithm. But if you have random data, this is an excellent sorting algorithm. It's very fast, and the space complexity is O of 1, which is better than merge sort. If your data is sorted, it would be better to use something like insertion sort, even though that is an O of n square as its worst case. If you are using sorted or almost sorted data, it is very efficient. It is actually O of n. Okay, in that case. So that is our overview of quicksort big O. Okay, so now let's talk about tree traversal. We are going to look at a couple of different ways of doing that. Okay, and first we have to talk about what is tree traversal. So traversing, if you had something simpler like a linked list, would just be going through each item, okay, from beginning to end, and you might take all of these values and add them to an array and then return that array. But if you have something like a tree, it is more complex because there are different ways that we can approach this. So one of the common ways of doing this is we just start at the top node, then we go to the next line 21 and 76, and then we go to the next line and we go across here. This is called breadth first search. Okay. Another approach that we could have is, instead of starting at the top, we could all the way to the bottom, and in this case we are going to go all the way to the bottom to the left, and to do that 18 node first, and we have gone as far as left as we can. So now we will go up, then we will go to down to right, and we have done everything on that side of the tree, and we can come back to the 47. And because we are doing left first on that other subtree that we haven't visited, the deepest node that we can get is the 52 node, and we will do that one next, and then finally come down to 82. Okay, this is called depth first search, and we are actually going to write 3 different depth first search functions. Each one is going to return these in a little bit different order, but breadth first search and depth first search are going to be the 2 broad categories of tree traversal. So now we are going to walk through the steps of doing breadth first search. Okay, and then we will do the code for it. So let's bring the tree here, and in breadth first search we are going to start at the top, then we are going to fill these in each across each row like this, and push all of these into an array and return that array with those items, okay, returned in that particular order. So now I am going to bring up a couple of arrays here, one that we are going to call Q, and the another one we are going to call result, and the result array is going to be the one that we return at the end of this. So in order to get these in the right order, we are going to need to use both of these, and we are going to push that top node first into the queue. I want to emphasize that this is the entire node. This is not just the value from the node. Okay, and I'm going to store it like this. I am going to keep it blue here, so we emphasize that it is a node. Okay, then we are going to shift that item out of the queue, and we are going to take the value and push it to the results array. Now when we put this in the results array, we are not putting the entire node in there, we are just putting the value. But because we put the entire node in the queue, we have the value, and we have the right, and we have left. So we can say for the 47 node, what is to the left, where that is going to be 21, and we can add that to the queue. To the right we have 76, so we are going to add that to the queue. Okay, so we are going to have a loop that removes items from this queue until the queue is empty. When the queue is empty, we will have visited every node in the tree. So the next step here is we are going to remove that 21 node from the queue, and we are going to shift that off, and we are going to do 3 things. We are going to take the value and put it in the results array. Okay, then we are going to look at the left to the 21, which is 18. We will push that into the array. We will look to the right, that is 27. We will push that into the array. Once we are done going left and right, the next step is we are going to shift to that 76. Okay, the values goes into the results array, and then we are going to go to the left of 76, which is 52. Push that on here, and then we will go to 82 and go to the right. Okay, so that is what you can do. Now when we remove the next item from the queue, we shift off that 18, the values goes there, but left and right is null. There isn't anything below that 18 node, so we will go directly 27. There is nothing in the left right to 27. The same goes for 52, the same goes for 82. Okay, so now the queue is empty. We can remove the queue array from the picture, and here what we are going to return is that results array. Okay, so let's look at the order that these numbers came up. 47 is the 47. The next two, 21 and 76. Okay, and then, and you can see the tree is exactly like this one. See the other tree. Okay, and that is called breadth first search. Now let's code for our breadth first search method. So let's bring up our tree like this, and I'm going to put this down in the corner there, and we will start writing our method. We will say breadth first search, and we will need a variable for whatever the current node is that. Okay, that we are popping off that array that we talked about in the last section. Okay, and we are going to set that equal to the root to begin with, and we are going to need our queue array like that and our results array like that. Okay, see like this. Okay, then one of the things we have to do before we even get to that loop where we are looping through and putting in things inside the queue. Okay, if we need to push is current node which is root in the queue into, is we need to do that. And remember, we are pushing the entire node with the value and left and right into the queue. Okay, so we are going to represent it like this so that you can remember it, that it is actually a entire node. And we will start our while loop, and we will say while queue dot length. While in other words, while the queue has length, or you could say while the queue has a length that is greater than 0. Okay, because once it is 0, that will equate to false. Okay, I'm just going to focus on this while loop like this, and we build it out. We will say current node equals queue dot shift. So when we shift this out of the queue like this, I am going to make this green to match the 47 in the diagram. Okay, that makes that the current node. And we are going to do a couple of things. First, we are going to take the value from that current node and we are going to push it into the results, only the value. And then we are going to go left and right. We will say here, if there is something to the left, then we will push that node that is on the left current node dot left into the queue. See like this. And then we will say if there is something on the right, we will do the same thing here, where we push the current node that is on the right, which is in the case 76, and that's everything for our while loop. So let's run through this while loop a few more times. So let's look at these two steps. We will shift 21 like this, and we will move that value. Okay, from this point onward, I'll just take these two lines and combine them into one step and just move that from value. Okay, so I will say if there is something on the left, and there is something on the left which is 18, so I will put 18 here, push that into the queue. If there is something on the right which is 27, so I will put it on the queue. And then the next one, we remove the queue 76, see like this. Okay, that is those first line here, first two lines here. Then once again you will check the condition and you will bring 52 and 82 here. Okay, and then after that, now we will go for 18 here. So when you pop 18, shift 18, okay, then there is nothing on the left or right of the 18, so there is nothing on the so you will directly jump to 27. There is nothing on left or right of 27, so we will move to 52. The same goes for 82 as well, nothing on the left or right. So now we have our queue is empty, and we stop the running the while loop because it is only runs as long as the queue has some length. So remove that, and the only step that is left to do is to return the results array. So let's bring our entire code here. This is our entire breadth first search method, and we will look at this code in a second in DevTools, and we will do this as an example. This is the example we will take here. Okay, and we should expect to see this as an answer. Okay, so come to DevTools here, and this is the same. This is the code here. Okay, we have breadth search first method. Now it is a binary search tree class, okay, by which I am creating the tree, but this is the function which I taught you in this section. Okay, now this is how we are creating the binary search tree, okay, that we will build. And okay, this array is we should get as an answer, we should expect to get as an answer this one. Okay, so now let's see that the order of the array, it should be the same order here, right? They should be same. So let's try to run this one, and this is our binary search tree. We have our value 47 21 76. Okay, and then you can expand if you want. Now clear this one, and now if I run my BFS function, see, you are getting this as an answer. You have 47 21 76 18 like this. Okay, the answer that you should expect here. So that is how you can write the code for binary breadth first search. Now let's look at depth first search, and first we are going to look for pre-order here. Okay, we are going to work on pre-order. Okay, and later we will also look at post order and in order as well, but this one will be for pre-order. So let's walk through what pre-order looks like. I'm going to bring up a tree here, and remember, we are just going to take these and write them to on what order we are going to do it in. So pre-order is going to start at the top and write that to the array, and then it is going to the left. It's always going to the left first. If it can, it goes to the right, that 21 to the array, and then 18. Okay, then we can come back to here. Okay, and we can go to the right again. So now 47, that top node has everything on the left. Now it is going to start to the right. Okay, so it will go to 76, and the 76 node is going to go to the left because we are going to go left first, then and then after left is completed, then we will come back here to the 76 and go to the right, which is 82. Okay, so 80 to the array will be added. That is pre-order for depth first search. Okay, so now let's code our depth first search pre-order method. So I am going to start with this tree here, and this time I am going to have a call stack, as we are using the method here. This will be easy for you to understand, okay, to track how this is working. Okay, so we will have start building this out. We will have this DFS pre-order, and the first thing we have the results array, this like this one here. Okay, so the next I am going to bring in our entire function here. Okay, and we will walk through it. So this function is traverse. Okay, function is traverse, and then we are going to pass it a node, and we are going to take this off as current node. Okay, and when we pass the root node, which is current node, okay, it is going to take its value and it will push it into the results array. We are going to push current node dot value. So the current node is going to be the root node to begin with. Then we will have this condition, and this is where we have the left node. Okay, and we are going to do the recursion here, traverse, calling traverse again. Okay, so if there is something on the left of the current node, then call traverse of that node that is on the left, and there is one on the left. Okay, 21 node, and then we are going to have, if there is on the right, we will again do the recursion, and we will do the traverse current node dot right, which is 76. Okay, so after this function everything will be completed. You can traverse your root with the root here, which pushes 47 onto the call stack, and remember, this is going to be called traverse here. Okay, but if you look at the call stack, we have 47, and you can say this is the instance of the function traverse that we are calling the node, which is 47. Okay, and that is how we will keep track of this entire thing. So let's run our function, the first line of the function. Let's start from here to understand it more properly. Okay, the value of that current node, which is 47, so 47 we will push into the array. Then we come down to this one. If there is node on the left and there is 21 node, we will call traverse on that node on the left, and that pushes this one into this one. See 21 like this. So the first line we are going to run of the traverse function is this line again. Okay, so results dot push. So that means 21 now will be added into the results array. So every time you push the value of a node, I am going to take that node orange here. Okay, I will color that node orange. Okay, now we are still at 21. Okay, now we are still at 21. So we will check, is there something on the left of 21? Is there something on the left of 21? Yes, there is. That is 18. That is 18 here. So we will push 18 on the call stack. So for 18 we will push into there like this, into array. Then we will check, is there anything on the left to the 18? No, there is nothing on the left of the 18. So that means this time the above recursion will not happen, this below recursion will happen. We will check whether is there something on 18 of right. There is nothing, so that will also go outside. So 18 will go outside of call stack. Okay, now we are come back to 21. So on 21 again, we have already done the left part. Now we will check the right of 21. So the right of 21 is 27. So I will put 27 in the call stack, and we will run this line, and it is going to push 27 here. See like this. Okay, now there is nothing on the left or right of 27. So 27 is over. 27 will go outside of call stack. Now 21 is also completed. See, 21 is also completed. For 21 we have also run for left and right. Both of them we have completely done here. So 21 will also go outside of call stack. Now we came back to 47. Now if you remember for 47, left is already done. Now we are on the right of 47. So on the right of 47 we have 76. So 76 will come here, and then for 76 we will push this 76 value here. Now for the 76 we will check for the left. Okay, it will look left, and on the left we have 52. So 52 will go into call stack, and we will push 52 here into this one. But now we will check, there is nothing on the left or right of 52. There is nothing on the left or right of 52. So 52 will be gone from the call stack. We came back to 76. Now on the 76, left is already done. We go on the right. Now on the right we have something called 82. So 82 will come here. 82 will come here in the recursion, and we will inside 82 we will push 82 here. Okay, now there is nothing on the left or right of 82. So 82 will be gone. Recursion of 82 is completed. Now we come to recursion of 76. That is also completed. And now come to recursion of 47. That is also completed. 47 left or right is also completed. So that will also go from the call stack. Okay, that is how the recursion will work, and you will have your entire results here. Now what you are going to do, your original results. Okay, your original results we are going to call traverse on that. Okay, this dot root, and we are going to return the results here. Okay, so results will be returned here. Okay, and that is your code for this pre-order. Now we are going to build this as an example here. Okay, and we will get this as an answer. We should get this as an answer here. Okay, so let's come to dev tools. So this is dev tools here. Now this is our the same code that I just explained to you. Okay, our pre-order code here, and scroll up, you will see this is the tree that we have built here. Okay, and we will expect to get this as an answer. Okay, so if you run this one, you will get your binary search tree as an answer. Okay, which will have all of the values that you want to work on. See, and if you run pre-order, see, this is the answer. You will be able to get, this is your final value that we should get here. Okay, so this is your answer here. Okay, it does matches your initial answer, expected answer that you should get here. Okay, so that is our method for depth first search pre-order. Now let's start depth first search post order. Okay, and we are going to walk through the steps of this. Okay, so this is our tree, and we are going to start at the root. We are not going to write that number to the array. We are going to visit that one, only visit. We will come back to it, and we are going to go to the left 21, visit that node. So go to the left 18, visit that node. Now 18 is going to try to go left, and there is not an item on the left of 18. So So we will go to right and not there as well. So 18 now will be returned to the array here. 18 will be the first item that will be array here. Then we will come back to 21 here and we will look on left, right. Okay, so right of 21 is 27. So 27 is going to try to go left and try to go right. There is no items there, so it will write its value to the array. Now we come back to the 21 again, and because left and right both are completed, now we will write 21 to the array. Okay, because 18 and 27 both are there. Okay, now we come back to 47 again. Now go to the left of 47, that we have now on the 76. Now we always go left, so left 52. Now for 52, left and right both are nothing on the left and right of 52, so 52 will go to array. We come back to 76 and we then go to right here, okay, which is 82. Okay, 82 left and right there is nothing there, so 82 will be written to array. Then we come back to 76, and because both left and right are completed, so we will write 76 as well for 76. Okay, now from 76 we will come back to 47 here, and 47 also 21 and 76 also completed, so 41 will also be written to array here. So when you compare post order, which is what this is to pre-order, okay, the one that we did previously in pre-order, we wrote the 47 to the array first, okay, and in post order we write 47 at the array last, in the array last. Okay, so that is our quick overview of the depth first search post order. Now let's look at the code for depth first search post order. Okay, so this is our tree and this will be our call stack, and we will write our method dfs post order. Okay, now first we will create our array results, okay, just like we have in pre-order, and like this, bring up like this, and then we are going to bring in the function that we had in pre-order. This is the one we used in pre-order. Now to change this to post order, what we will do, we will simply do this. See, we are simply going to rearrange the order of these things that get called here, and just like we did with pre-order, we are going to call the traverse, this function here, like this, with this dot root, and then using that call stack. So we will have, first of all, at the root you will have 47 there, and we will check is there anything on the left. So we will do the recursion. Yes, there is on the left 21, so 21 will go into call stack. Then to the left of 21, is there anything? Yes, there is 18, so 18 will go into the call stack. Now is there anything on the left of 18? Okay, no, there is nothing on the left of 18, so we will check right of 18, nothing on right as well, and then we will push it into the results array. See, like this, we push 18. Now after pushing this one, your 18 is completed. So you can pop 18 from the call stack. Okay, now then we come to 21, back to 21, and on the 21 now we will check the right. So on the right of 21 we have 27, so 27 will go into call stack. Now we will check is there anything on the left or right of 27. There is nothing, so we will directly push 27 to the array here. See, like this. Okay, then now 27 is also completed. Now we will come back to 21 again. So 21, in 21 left or right both are completed, so we will directly push 21 into the array here. See, like this. Now 21 is also completed, so that will go outside of the call stack here. Okay, now we come back to 47. For 47, left is already completed. Now we will go to right of 47, which is 76 here. So 76 will go into our call stack. Okay, and then what is 76? Left of 76, which is 52. So 52 will go into call stack. Now there is nothing on left or right of 52, so we will directly push 52 into the array here. See, like this. Now 52 is completed, so 52 will go outside of call stack here. Okay, 52 is completed. Now we again come back to 76 one. So on the 76 one, okay, left is already completed. Now we go to right of 76, which is 82. So 82 will go into call stack. That means 82 function is running. Okay, and then in the 82 function, left or right will be completed, and then we will push this one 82 because there is nothing on the left or right of 82. 82 is completed. Pop 82. Now we come back to 76 again. It is at the top here, and we will directly push 76 here because that is completed. Now we come back to 47. So on 47 also both left and right are completed. So we will push 47 into the array as well, and we will pop 47 node from the call stack as well. Okay, like that. Okay, and now we will do the now the traversing is completed. The entire traverse function is completed. Now all we need to do is to return the results. Okay, see, that is what we can do here. Okay, so that is what we will do. That is our code here, and this is our example that we will use here. So, and this is the answer that we will try to receive in the output. Okay, so now we will try to see this, all of these things in the dev tools. Okay, so this is our DFS post order method. Okay, that I just explained to you. Okay, if you scroll up, this is the tree, the example tree which I just showed you, and this is the answer that I should expect here. Okay, so that is the output we should get here. Now if you click on done button, so you will get your binary search tree. Okay, and then after that, if you try to write your method here, but before that, clear this, and now if you try to write the method DFS post order, see, you will be able to get the answer in the same order as you should have been expected here. Okay, as I explained to you in the same manner. Okay, and that is your method for depth first search post order. Okay, so now let's talk about depth first search in order. Okay, we will bring up our tree here, and what we are going to do is we are going to start at the top as always, and we are going to visit that first node, and we are always going to the left first. So we will go to 21. It is going to go to the left 18. Okay, 18 is going to go to left, but there is nothing on the left of 18. So the next step is we are going to write the value of 18 to our array. Okay, now we will color that orange. Then the 18 is going to try to go to right. There is nothing there. So we will come back to the 21. Now 21 is already gone left. So now 21 will go to right. 27. Now it is go to left. There is nothing. Okay, it will try to go to right. There is nothing here, and it will all the way come to 47. Now 21 is already completed. Left side is already completed of 47. So we will go to 76. And the first thing we always try to do is that if we can go to left, we go to left 52 and write that value. Okay, and we come back to 76. Then we go to 82 here. Okay, because it is always go in this manner, left, center and right. Okay, so now this is the order that we are able to get here in the array. We should get in the array. Okay, we start at the 18, that is the lowest number in that tree. Then it is 21, then it is 27, and it goes from lowest to largest. Okay, highest. That is the order here. That is why it is called depth first search in order. Okay, so now we are going to write the code for our depth first search in order. Okay, and now let's bring our tree, our call stack, and this is the function DFS in order. Okay, and first of all we will have our array results, see, like this. Okay, now after this we are going to bring our method traverse. Okay, as we used previously as well. Now this should be our order. See, this will be our order here, left push right, left push right. So the code will be same, it is just the order. We will simply rearrange the order, and then we will call the same method with the root here. Okay, so root 47 will go in call stack. Okay, of the call stack. Then first of all we will go to left. So 21 will go into call stack. Now inside the 21 we will go to left again. Okay, we go to 21, which is 18. So we will come to 18. Now there is nothing on the 18 of left. There is nothing there. So we will push 18. See, now we are pushing 18 first. So first of all 18 will be pushed. Then we will check the right of 18. So there is nothing on the right of 18. So 18 is completed. 18 will go from the call stack. Now we come back to 21 function. 21 here. Now we already, now we can push here. We already go to left. So now we will go push. So 21 will be pushed here. Now we will check the right of 21, which is 27 here. So 27 will go into call stack. Okay, now go to the left and push. So there is nothing left of 27. So we will push 27, and now we will check the right here. Okay, on the right there is nothing of 27, so 27 is completed. 27 will go outside of call stack. Okay, now 21 is also completed because it is already completed, so we will get 27 outside of call stack. Now we come back to 47 here. Now for 47 left is already completed. Now we will go to right of now we will actually yes, first we will push 47 here. Okay, and then we will go to right here of this one, so which is 76. Okay, so we come to 76. Now for 76, first of all we will go to left. So on the left of 76 we have 52, so 52 will go into call stack. We are called 52. Now inside 52 we will check left here, there is nothing on the left of 52, so we will push 52 into our array. And now we will check on the right of 52, which is nothing, there is nothing, so 52 is completed. Come back to 76. Now in the 76 left is already done, so we have gone to we will push, so we will push 76. Now we will go to right of 76, which is 82. So 82 will be called, and 82 here like this, call stack, in the call stack. Then there is nothing on the left of 82, so we will push 82 into our this one like this. And now in the right there is nothing on right, so 82 is also completed. Then we come back to 76 is also completed, so we will call stack outside of call stack. And then 47 is also completed, left and right, so 47 is outside of call stack. And that is how we get our this method, this results here. Okay, and now we only need to return the results, okay, that we got here, and that is our final code for this one. And we will go to DevTools, and this will be our example. This is the, and we will expect this as an answer. Okay, this array as an answer. Okay, so let's go to DevTools here. Now this is the same code which I just explained to you. Okay, in order method, and this is the array that this is the tree that I will try to create here. Okay, and this is the answer I should expect, this array. Okay, so if you run this code, then this our tree is being created here, and now if you run dfs in order, see, so you will be able to see that this is the answer that you are able to get here. Okay, so that is the expected answer I should get here, as I explained to you here as well. So this is our method for depth first search in order.